I'm Professor Ira Pohl of the University of California, Santa Cruz, and I'm going to be your instructor for the next number of weeks, where we're going to do C++ for C programmers. I'm going to explain a little bit about what the course is going to do for you. The course is organized in 2 4-week segments. The first segment is going to take you through the basics of C++. Today we'll get through C++ as a better C. We'll even try to understand what better means. I'll also be assigning you homework today. And your first homework assignment, which will be due in a week, will be to convert some C code that'll be posted to C++ code. So you'll be able to do that right after our discussions today. The next 2 are graph theory programs. Now, I will explain these algorithms. One is the shortest path algorithm, and the other is a minimum spanning tree algorithm. But I am expecting the people in this class to already have a year's experience, both in programming in detail in C, or an equivalent language, and roughly the background that you would get in freshman, sophomore year of computer science. So there we would expect you to understand elementary data structures, things like lists and stacks, and to have some of the basics in studying algorithms, including probably some of what we will be implementing. So for many of you, this may be revisiting something you've already seen in your student days. But by the end of the first 4 weeks, you should be proficient at a professional level in using the C++ language if you already came in knowing C. Now, for getting through the coursework, we're going to have quizzes that'll be at the end of some of my recorded segments, and then there'll be one final. Okay, so let's start. What does it mean for one thing to be better than another thing? It's not really that simple an idea. Was Willie Mays better than Mickey Mantle?
Night to remember. Candlestick Park, San Francisco, May 5th, 1966. Claude Osteen pitched, and there it went. The 512th home run of Willie's legendary career.
In an epic 7-game struggle, arch foes the Yankees and Dodgers battle for the World Series crown. Mickey Mantle climaxed a season in which he won the triple batting crown.
When I was a kid growing up in New York, we had 3 great center fielders. Mays was a center fielder for the then New York Giants, Mantle for the New York Yankees, and people probably forget the third center fielder. He was Duke Snider, the Duke of Brooklyn. Now, arguably, Mays and Mantle are 2 of the greatest players who ever played, but all day long in the various bars and coffee houses in New York, there would be the discussion. Would I rather have Mays or would I rather have Mantle? We also have ideas on food. You can use butter or you can use margarine in some contexts. They're frequently interchangeable. Which is better? What would that mean? And then finally, the question we're going to try to answer in the class is C++ better? Is it better than, for example, Java? So, quiz. Why don't you see what you think? In what sense is margarine better than butter, or vice versa? Why don't you think about that and write in an answer. So here are some of the things you might have thought about. Calories. Well, roughly speaking, if you look it up, mostly it's a tie. Margarines tend to be 35 calories. That may be surprising. They don't typically save you anything on butter. Some margarines are healthier. They have no fats in them. Some margarines contain no cholesterol, whereas butter is made from animal fat. So if there's a health factor, if you have something like diabetes or heart disease in your background, it might even be prescribed by your doctor to have certain kinds of margarine. But as we know, going to a nice French restaurant, it's going to be butter. Butter is better. Chefs like butter. Butter has more vitamins. Bottom line, not an easy question. A lot of context. Okay, so let's now return to our main subject, C++. It originated with C. As we said earlier, most of you have programmed in C or an equivalent language for at least a year, and you're competent. That's an expectation in the class. C has a deep history. It's been around for quite a while. C, traditional C, as you can see in this slide, was invented by Dennis Ritchie. And Dennis Ritchie was working with Ken Thompson, and they were working on something that most of you will know about, the Unix operating system. In fact, they both invented the Unix operating system and received the highest award that you can get as a computer scientist, namely the Turing Prize, for this work. So they were a two-person project at Bell Labs, 1972, and they were writing an operating system. And they had originally been writing it in a language called B, and B had come from another language called BCPL, and so on, back to Algol, which is a foundational language invented in 1968 by International Group of Computer Scientists as a standard for algorithmic languages, and probably in some ways the most influential single language in the history of programming languages. Now, Dennis and Ken just had this language for their particular project, and we call such a language a systems implementation language. It wasn't really meant for wider use. It was meant almost as a personal language, and you'll see, or you'll know, that there are many obscure things in C notation. Well, one of their guiding principles was type as little as possible. So the language was incredibly terse. It had many strange operators. Those operators conformed to the operating system and the architecture of the small microprocessor they were working on. It was a PDP. Now, that was such a successful project that people wanted to expand on it. And Brian Kernighan and Ritchie then wrote up the language, and that's called KNRC, and that's one of the most influential programming books in our profession. KNRC, which was fairly primitive, it had relatively little type safety, morphed into something called ANSI C in the 80s. So as people expanded the use of C, especially professional use of C, there were standardization committees, and there were major improvements made. ANSI C, which showed up around 1985, remains in wide use. Later, the committees continued to meet, and there is a newer version of the standard. But I would say the bulk of C work still done in industry is basically the 1985 standard, and that 1985 standard is documented in Kernighan and Ritchie edition 2, which many of you might have. So why go to C++, where we have such a successful and important language? C++ was a language written by Bjorn Strustrup, and he was also at Bell Labs. Now, Strustrup had come from a tradition in Denmark of object-oriented programming. He had learned his programming in a language that was developed by Norwegian computer scientists called Simula 67. And he just felt that was a better methodology. But that wasn't going to be supported at Bell Labs. If you wanted to do work at Bell Labs, you worked in C. It was okay to extend C, so there were many what you might call preprocessors that added, extended a version of C with ideas from other communities. So there was, for example, a form of C that had a lot of concurrency, called concurrency. It had concepts taken from Ada. So Bjorn, in that tradition, invented something he called initially C with classes. And he added that on with a preprocessor. And it got very successful, just like C had. And so it escaped its roots, which was, in effect, this very vibrant basic research laboratory, Bell Labs at AT&T. And so Bell Labs decided it would support a industry product and allowed Bjorn to ship and support C++ version 1. And that was 1985. And the language developed much as the language like C developed, with support from industry and with ANSI standard committees, modifying the language, building it, and improving it. And so by 1996, when there was a major ANSI standard, the language grew to be fairly large. So C versus C++. C is small. C is primarily a systems implementation language. C++ is large. C supports imperative programming, sort of classical programming where you write little functions, and functions are the way you compartmentalize your programs. And C++ is what you might call the Swiss Army knife of programming. It has a tool for every occasion. So it also supports two very important forms of programming: object orientation Again, you might want to think Simula. And it supports something called generic programming, which I'm going to make a big deal about. So you probably won't have a lot of experience with generic programming, and that's one of the benefits that you're going to learn in going over the material over the next few weeks. So I'd like you all to think about, from what you know of C and C++ so far, very little, what might you think makes C++ better than C? After all, this is our first topic. So A was invented later, so it comes up 10 years later. B, Bjorn Stroustrup is a better language designer than Dennis Ritchie. They both were at Bell Labs. C, C++ has more features than C. D, simpler. What would be your choice? Give you a minute. Well, programming languages, some people think Algol 68 was one of the best languages ever invented, and that's Algol 60, excuse me, or Algol 68, another language that was a very elegant language. It's not always true that better comes later. Dennis and Bjorn are both excellent computer scientists. Dennis won the Turing Prize, but he won it mostly for Unix. The answer I was expecting, what I would consider the best answer, is a sort of semi-logical answer. C is a subset of C++, and C++ has more in it and has better libraries. So if you want to think more is better, not everybody thinks more is better, but that would be the general argument. And it certainly is not that C++ is easier. C++ is far harder, even the proponents of C++ would not make the case that you would have an easier time learning C++ than C. A more interesting comparison is Java versus C++. Java shows up in 1995. Java is invented at Sun. The Sun people have great affinity for another old language called Smalltalk. Smalltalk was a language invented at PARC, which is a very famous Xerox lab, and among other things, probably is the source of inspiration for the Mac. Lots of things connected with the personal computer, the graphical user interface, they all come from PARC. So Smalltalk, which was a pure object-oriented language, inspired Java, which also has a C connection. It has C-like syntax, unlike Smalltalk, but C++ has this inherently imperative methodology coming from C, system implementation language, low level, and Java is meant to be purely OO and high level. So the inventors, chiefly Gosling at Sun, just felt that they could do better. Java has a JVM, a virtual machine, and Java provides universal semantics. So the old thematic thing was write once, run everywhere. That's a good thing in industry, much less in development costs. You don't have to do everything individualized to the platform. C++ originally compiled to C. So C was this very efficient SIL, and it had different compilers depending on the platform, and indeed had slightly different semantics depending on the platform. So it could be tuned to the platform. So it was frequently the most efficient higher level language that existed on a platform. C++ wanted to maintain that advantage. So there's no hidden overhead. So one of the benefits for Java is you get garbage collection. You don't have to manage memory. Memory leaks go away, more or less. Whereas in C++, you have to have a sophisticated notion of memory and memory management. But you don't get a hit in runtime costs. So you have a very interesting comparison between Java and C++, and that remains a raging argument in the programming language community. Now, I do expect you to know some of the basics of OO. You don't have to know Java, though some of you are coming from knowing Java. So knowing Java is a positive in the sense that lots of stuff in C++ that's OO looks very much like Java. But you do have to be careful. Some of the stuff that looks almost the same has important differences. So you must keep in mind that when you learn the C++ version, even if the syntactic construction looks the same, you have to make sure you know what the runtime semantics are for the C++ construct. Object orientation knowledge is something I'm expecting. If you're a little rusty there, read the Wikipedia article. It's a very good article on the basics of OO. But that's how we intend to develop our software, one of the key methodologies we will be using in the C++ community. Okay, quiz. From what you know about object orientation, which of these ideas best fit OO? Is OO mean that you're using recursion? Does OO mean data and operations are bound together? Does OO mean that type safety is critical? Does OO imply that automatic garbage collection is available? So take a second here at this break and answer this quiz. So let's discuss the answers. Object orientation is not about flow of control, but of course your background should have let you to use of recursion. So again, you should be comfortable with using recursion. The second answer was what I consider a best answer. An object is a data type, and it's bound up with its operations. And think of a data type that you have in the base language. You have something like int. And in the base language, you have operations like plus and times. Now, in an OO language like C++, there are things, you just have a certain set of basic native types. And the crucial thing that makes OO languages so powerful is they allow type extensibility that allows you to program naturally with the new types. So if you think about C++, there isn't a native type there, but in the standard library, you can get a complex number type. And the complex number type, once it's included in the language, once it's built properly, allows for operations like plus and times in a natural way. And somebody who works in a community, such as a physicist or an engineer, that uses complex numbers will just routinely use that complex number package very effectively. And an OO type could be a windowing system. So you could have somebody write a window and then have natural operations on window, like making them larger, making them smaller, putting them in the background, allowing for text mode, adding in things like menus. So it's a nice way to build software. One of the things in programming language history, when people tried to have universal languages, what they invariably ran into was either they made the language so big that it was unmanageable or unlearnable or inefficient, or they couldn't track everything that was useful. So the early attempts to have universal languages, such as PL1, while they were remarkable languages and systems, PL1 being invented in the mid-1960s by IBM, were essentially failures, largely failures. And that then led to object-oriented languages. Well, actually, first data abstraction languages such as Modula and Ada were quite successful as well. They share a lot with object orientation. And these languages let you have a coherent kernel. So in C++'s case, that coherent kernel is C. In Simulus 67's case, the coherent kernel was Algol 60. And you could be a proficient programmer in C, or in the Algol 60 case, and then readily extend the language to a new domain, such as complex number. That's what's meant by object orientation. Type safety is usually a good property. It's a good property of many languages, including OO languages, so it doesn't define them. And the same thing can be said about garbage collection. It can be built into an object-oriented language. It's very useful. It's also in languages such as Lisp and Common Lisp and Scheme, but it's not a requirement. It's not the essential feature of object orientation, which is really type extensibility. Okay, so in this next segment, we're going to show you a C program. And this is a C program that if you like to play craps, which you can do legally in Las Vegas, this lets you properly compute the odds of getting various dice outcomes. So we're going to compute probability as a C program. And then what we're going to do is show you how to convert it to a C++ program. So this is your first hands-on stuff that you're going to actually come away with. You're going to already be a C++ programmer after this little lesson. And again, I'm expecting everybody here to be a C programmer. So among the things you should know are standard libraries. Anytime a standard library has a function, that's the function you should use. That's what the community expectation is. I'm going to be talking a lot about community expectations. Good programmers fulfill community standards, community expectations. So we need I/O. This is the I/O library. We need some basic functions like the random number function. That's going to come in here. And we need some timing functions as well from the standard timing library. All of these commands are what are called preprocessor commands. One of the things we're going to find out is that we don't want to use we want to use the preprocessor less. And we're going to explain why. But for the moment, this should all be familiar. Here's your use of the random number function. A dice has 6 sides, right? We have the little dice that we're rolling. It has pips on it between 1 and 6. And 2 dice give us outcomes between 2 and 12. Not a great drawing of a dice, but in our main program, we're going to do what I'm going to call, because we're going to do a lot of this, so this program is prototypically a simulation. And with simulations, we want to do things that are random. We don't want the simulator to always be working in the same way. We don't want it deterministic. Well, there's a little contradiction there. A computer is a deterministic device. How do you get to simulate randomness? That's actually a deep theory. My neighbor, Don Knuth, down the road at Stanford, world authority on it, he wrote a whole book on semi-numerical algorithms, talked at great length about writing code that looks random. So there's a whole deep theory of randomness. We're not going to worry about that. We just are taking some expert code, which is a pseudo-random number generator, and figuring that it, in effect, looks like what would otherwise be a true random process. One of the things we do is we call on the system clock, and this seeds the random number generator. We don't want the program running the same way each time. It'd be like going to Las Vegas, starting on a slot machine and always seeing the same outcomes. The casino doesn't want to see that, so it has to have a mechanism for starting at a different point in the sequence each time. That mechanism is to call the seeding function, call a systems clock, and the clock is going to be a readout at different times of day that'll have different numbers. So it'll start you at a different place in the sequence. And then we're going to run a whole bunch of trials, and I'm going to leave this to you. You can run the code at home on a C compiler or a C++ compiler. But in effect, all the outcomes are going to be stored in here, and these outcomes are going to be dice 1 and dice 2. So if dice 1 is a 5 and dice 2 is a 6, you're going to get an outcome for getting 11. So if you want to know traditionally, when you first roll dice in craps, you get a 7 or 11, you win. And if you wanted to know how many outcomes, or the likelihood of getting 7 or 11, to know what the payoff should be for that, you can run this simulator and look at the outcomes for 11, look at the outcomes for 7, and get a sense of that probability. This is just going to build that set of tables, and then here it prints it out. So what did we get in the C program? We got standard libraries. We got macros, and we had this special symbol that introduced the preprocessor commands. And then we saw the special function main. While main is not a keyword, it is reserved for starting the program. We'll always have a main function. That's where the program will start. That's where the thread for the program will start. And main, by the way, in C and C++ is an int, and if it's otherwise not specified, it implicitly returns 0. So depending on your company's style guide, you may want to always have an explicit return 0, meaning the program terminates correctly and passes a 0 value back to the operating system. So that's C. Okay, so in this next segment, we're going to see how to do C++. So here's your first C++ code. And this should be just transparent. As I say, you should jump off right after and do problem 1. So ignore the dots, but in my C++ version, I'm going to have rest of line comments. In the C community, we generally had initially multi-line comments. The thing about rest-of-line comments is they're more flexible, and they're generally a little safer. Now, I have to give you a little warning here. What's the warning? Some of you are going to say, wait a minute, I used this kind of comment in C already. And yes, indeed, in the C standards that exist now, that comment style is now available. But when the languages started up, this was novel to C++. So it's C++ style. So there is a little bit of slurring over what the differences in the two languages are. Many of you are going to be using the GNU compiler. The GNU compiler combines both C and C++. And it's not always clear where one starts and the other stops. So what I am going to be talking about is more classically what was C versus what is C++. Now, again, we have standard libraries. And in the C++ community, we tend to drop the .h. .h was a notation reminiscent of meaning that you had a header file. In C++, we just give the name. So IOStream is the IO package. And then if I see a little c in front, these mean import what would also be a library in C. So C++, again, superset, C++ can use all the C stuff. And if you need a C library, a classic C library, it's available in the standard libraries for C++. And it's generally written as C with the same name taken from the C library. Now we have something called namespaces. New idea. A namespace is, again, a context, an encapsulation. Let's say I'm IBM, and I'm writing software, and I have special stuff that's IBM stuff. I may wrap it up in a namespace and call it IBM, my namespace. This namespace is std, STD stands for the standard library. But IBM could be using namespace IBM, where IBM wants to have its own libraries. And you can mix and match, so you can have different namespaces involved in the same program development. You could have the Oracle libraries, the IBM libraries, and the standard library. Or you can have your personal programming libraries. So namespace is another context. It's, again, a naming convention that's on top of the existing naming conventions of the C language. Okay. And then this using directive, this using statement, just lets the program know that the expectation is I'm going to be using the namespace STD. And I'll explain in a second why that's a convenience. Now here we replaced in the other program a sharp include, what was a macro. So in that other thing we had sides being 6, but that was a macro. And this is a definition. And this definition uses a keyword const. So we're saying that this is a constant of type int, and now this designation, this identifier name, has typing. And it again has context, so that the compiler can check everything with language rules, as opposed to a macro preprocessor substituting 6 wherever it saw size. And that substitution is a textual substitution that is independent of the language rules. And again, you have to take my word for it, programming methodologists, when they've studied the use of textual substitution as opposed to language context, find that more errors are made when you allow preprocessor textual substitution. So this replaces a preprocessor textual substitution with a language rule, a language declaration for the same purpose. Similarly, where we had macros for little inline coding segments, we now have a keyword inline. So inline is a new keyword. It's a compiler directive. And what it's telling the compiler is, hey, I have some function called rsize, and here's its code, but I don't want function call. Why don't I want function call? Because function call costs me money. It has runtime characteristics where the code has to go to the stack, has to initialize the stack, and has to call some complicated machine level instruction, which is maybe some milliseconds. So I can replace that by pure inline code. That's exactly what the macro was intended for, but here again we're now using the language, so we get language characteristics enforced. All the rules of function apply as opposed to textual substitution by a macro. So what were the C++ improvements? Now here's my sales job. I'm selling this in terms of Bjorn. Nota bene. Okay. So it's just the semi-erudite term meaning note well, nota bene. Some of these are adopted in modern C99. Again, so I'm aware of that. So the difference is there's been some convergence as things have proved themselves really worthwhile in C++ that don't necessarily change the structure of C. A few of these things have been adopted. Almost all the old C libraries are still available, usually with that C lead-in. Inline replaces code macros, and you've got to, again, be a programming methodologist or read the literature about where mistakes get made. But macros are a big place where mistakes get made. And then we've also seen less-aligned comments. So far, those are our improvements. Now let's look at the main part of the program. If we look at the program, it looks somewhat like the C program. Again, why? This is initializing, seeding the random number generator. And now we see another thing that I want you to, a big takeaway. Instead of printf, there is this cout. Cout, if I hadn't had the using directive, could also be written this way. This is the scope resolution operator. So again, this is one of the new things in C++. It gives you more context than C gives you. It allows you to use multiple libraries from different namespaces. But because of using, I don't need that. So using, I always throw in using the standard library because in most cases that's what I'm going to use. And in most cases I don't want to have to type in all those extra characters. Cout is going to be on your computer, typically your screen. So if you say cout, enter number of trials, popping up on your screen you'll see the phrase enter number of trials. What's this funky little \n? That's a new line. So if you recall, that's the same in C. Anytime you have a \, that's an escape, and then \n, \t. It's a tap character. There's \bell where you can ring the bell on your computer. So cout has the syntax that uses this operator. This operator in the C community is a bit shift. But in C++, it retains bit shift only when the arguments to it make it be bit shift. And these arguments, cout is what's called an O stream. So we have an O stream followed by this operator, and this operator is what's called overloaded. Overloaded meaning has a new meaning. So one of the things we're going to be able to do in C++ is function and operator overloading. Key new idea, an interesting idea. We'll see what its value is. Here's one of its values. The I/O system in C++ expects bit shift to be used in terms of I/O because it tends to not be used very often for bit shift. So this is saying, look at a string value. The double quotes means this is a string value. It knows that it's a string value, and it knows how to print a string value. Later, we're going to give it values that are integer or float. We'll know how to print those as well. Another thing we see here that's new is an interleave declaration that's not at the head of the block. So this declaration is interleaved, and starting to really use all of this screen space. It's okay. And then we have an input statement, which can be compared to scanf, except that the input statement says, take from, in this case, the keyboard. So you type in at the keyboard how many trials you want in the simulation. And that's a cin. And again, this is a much easier scheme. It's type safe, it's convenient, it's easy to understand, it's intuitive to doing I/O. Okay. Let's take a little quiz, a very trivial quiz. We've already heard this. Again, why srand? Why calling that standard function? srand initializes the random number generator. Don't want the same results each time in the simulation. The clock returns a process time in terms of number of clicks. It's a large unsigned number. It's fine-grained and different when main starts running. Again, during this class, I'm going to show many different simulation programs. So I am going to expect that you will get a fair amount of familiarity with this kind of Monte Carlo processing. It's very important and very useful, as you'll see. Okay, so let's summarize some of the C++ advantages. Type safety. When I say CN trials, what is known is that CN is an I stream. And trials is an int type. So the language understands, the compiler understands from CN, the standard input, which is the keyboard normally, I'm expecting some typing that is going to be interpretable as an integer. Otherwise, I have an error. But I don't have to put any formatting characteristics. So there's built-in implicit type safety. Type safety is always a good thing in programming. It's a way at runtime to catch errors. Notice we had mentioned in that previous slide that there were declarations that could be intermixed with the executable. That doesn't mean I want you necessarily to not put declarations at the head of a block. That's still a very useful style guide. However, when you're writing longer programs, it's useful to have your declaration nearer to where it's used. That just makes the program a little more readable. So if the code is a small amount of code, I would stay with the idea of putting all your declarations at the head of a block and commenting them right there. But if you have a more lengthy thing and you have a need for putting something right near where it's used, that is a very useful idea and frequently makes longer pieces of code more readable. There was also, though I didn't go over it in that last slide, the use of new. And if you review that, new is a memory management. And the memory it's getting is heap-based memory. So again, most of you should have 1 to 2 years of computer science background, either professionally or at school. When you are running a program in which, for example, you have main, and you're allocating variables, you allocate them off the stack. So when you declare a simple int at the head of main, that memory allocation is automatic, and deallocation is automatic. It comes off what we call the stack. However, when you don't know what kind of memory you need yet, and it has to be part of a calculation at runtime, then we use an alternate memory allocation strategy, and that's called memory allocation off the heap. And there's separate memory, a global chunk of memory that can be used to take memory off the heap and return memory to the heap. And there, in C, if you remember, there was a term or a standard function called malloc, and there was also a function called free. These are replaced by new and delete. And again, we will see, because of things like type safety, there is more implicit information available to the C++ compiler in using these new operators. These are keywords built into the language rather than standard functions that come from the standard library. And it does provide improvements. So here's C++. Here's the rest of that code. Again, this is where we're computing. If we rolled 5 plus 6, that would be our outcomes for 11. We would get a probability for it. And then I have a funky little thing sitting here that you won't have noticed as well. And I have an interesting piece of code here. So let's look at those two pieces of code, because they're also relatively new for if you've never programmed in C++. So this is what you call your standard iterative statement. This is your idiomatic for statement. It says, iterate with a variable j starting at value 2, where j is less than a certain number of dice times sides. So we have 2 dice, 6 sides, and then each iteration is plus 1. So we're going to go from 2 to 2, 3, up to 12, and do this calculation. But this initialized segment of the for statement allows for the declaration of a local iterative variable. So that's nice, that's new, because we generally don't really care about our i's and j's being global if we're just using them for iteration. So this again localizes something. Localization drives down complexity. So this is another improvement, a small one, but another little improvement that we're allowed to have these local declarations inside for statements. Cout, which is type safe, prints a string. So we'll see on the screen j equal, and then some value. So it might be j equals, let's say the starting value will be 2, and then we'll see probability, p, equals, and then we'll do this computation. So this is another thing. There's something called static cast. Static cast is what is called a safe cast. C++ replaces old-style unsafe casting in C with 4 different kinds of casting. So C casting is deprecated, meaning obsolete, shouldn't be used. The compiler may still let you use it. If you remember, a C cast would look something like this. Double, here's some expression, and that would mean convert that expression so that it's treated in the domain double. That's the same thing happening here. Here's the type that I want to convert to. But instead of just allowing an arbitrary forced conversion, this is telling me only convert if you have a rule-based conversion that you consider safe. If the conversion was not considered safe, then there would be an error. So this is going to protect you from non-standard conversions. And again, it's an improvement. Why do I need that conversion? Because otherwise these two things would be integer. And if they were both integer and outcomes would be less than trials, then all your probabilities would be 0. And your probabilities aren't 0. So if there were like 5 outcomes out of 20, you want this to become the number 5.0. And now this is no longer an integer divide, and you would get 0.25. And end-L is another way of saying new line. So this is again in the IOStream standard library. It's called an IO manipulator. It's something that can be put in an IOStream, and it tells the IOStream to skip to the next line. Okay, so all that shows you various kinds of improvements, and it's pretty much what I want you to take away today in using this for your first homework assignment. These are all things that you're going to make use of in converting your first C assignment. Let's summarize with what advantages we have. Safe casts, like static. There are going to be three other kinds of cast. One will be, for example, very dangerous, reinterpret cast. That means force the thing to look at it this way and just look at the bit pattern and whatever that bit pattern is on the local machine, reinterpret it. Generally speaking, in most companies, you're going to need manager approval for that cast. It's something to avoid. Generally speaking, just a bad idea. So in a way, it shouldn't be used, but it's there. There may be some very obscure, critical need for it, and it's available rather than have to return to, in effect, that's like returning to the bad old days of an unrestricted CCast. For statement can include a declaration in the initializer, so we frequently see things like int I or int j equals some initial value. This is most typical. Typically, you start your loops with a 0, and del is an I/O manipulator. So again, those are little improvements over the C language that you can immediately use, and you can immediately become a C++ programmer. Now, Bjorn, he's currently a professor at Texas A&M, distinguished professor there. He's still working on the latest versions of C++, and he has the classic book defining the language, very, very detailed at this point. But from his perspective, as the chief architect of the language, he more or less said, I believe C++ is better because I don't think purity is a virtue. To think Java as pure OO, Simula as somewhat hybrid, Smalltalk as pure, and he's saying purity is not necessarily a virtue. The single strength of C++ is exactly that it supports several effective styles of programming, several paradigms, and combinations of styles. Often the most elegant, most efficient, and most maintainable solution involves more than one style. Swiss Army knife. Think Swiss Army knife. Okay, what do we learn so far? More type-safe than C with more elegance. And then here is your first homework assignment. This is what you need to convert. And I'll see you next time. Okay, today we're going to continue with our main theme. You as a C programmer can almost instantly become a C++ programmer, and that C++ will improve your programming because C++ at a first take is a better C, and the migration from some of the standard C techniques to C++ techniques are very natural and easy. And you saw that our first assignment, which is to convert a C program to C++, you'll be able to benefit by what we go through today to add a few other features that you can do in that conversion. So that's our chief agenda for today. So why is C++ better? First off, C++ is more type-safe. Types are the critical underpinnings of a programming language. They're the domains that the programming language works under. So if we're in the native language, we have types already like int. But we also have types like double. We further have types like char. And we have, for example, pointer types. Now, when we declare a variable to be one of that type, and we mix these types in a program, we don't want a double, which has a certain bit configuration, to be reinterpreted as a pointer or an int. That's just going to be terribly misleading. Now, when C was invented in 1972 as a system implementation language, very low level, the two programmers who were using it, Thompson and Ritchie, knew exactly what they were doing at the machine level, and they wanted a lot of efficiency, and they even wanted the ability to hack code readily, maybe make a transfer between domains when they knew it to be safe. But now, when we're going to C and C++ as general purpose programming languages, coding large systems, having large teams of programmers on a project, we need as much type safety as possible, because type safety can be caught by the compiler using language rules that's enforcing type safety. So that's one dimension of improvement in C++ over C. Now, C has not been static, so some of you may know that there is a standard, C99, and it has improved type safety. But C itself was designed to be compiled to a local architecture, and that architecture, the language, the compiled code, could be highly optimized for that particular platform. And because of that, the rules of the language were a bit loose. It let the compiler writer for that platform choose a scheme that, again, could be optimized for that platform. So at a simple example, an architecture on one machine might have 8-byte integers, and on another machine, an integer may be naturally 2 bytes. The compiler writer could choose what the size and the range of the int was, so that when you would go to run a C program across different platforms, you might see different behaviors. C++ makes a big step towards a considerable amount more type safety. C++ has generated more libraries. Libraries are very important in making a language and a system powerful. Why? Professional libraries, first off, can be very heavily tested, so they can assure that they're correct, and they provide instant reuse of code. Reuse, again, is if there is a silver bullet in software engineering development, it's reuse. So libraries provide reuse, and reuse is among the magic bullets, if there is a magic bullet, in software development. And C++ expands the number of libraries, the scope of the libraries, the domains for those libraries. And later, we will be talking a lot about the standard template library, which is a major addition to the language and gives you far more capability than you had in C. So a third property of C++ that's better than C is that it de-emphasizes the preprocessor. The chief use of the preprocessor in C++ is to include libraries. But other uses, such as the sharp defines, where in C and in the C community it was appropriate to sharp define global constants and sharp define macros, goes away. That's no longer good practice in the C++ community. Again, we'll revisit this, but in software engineering, software methodology, it's found that the preprocessor which does not contextually obey the rules of the language, but instead is something involving textual substitution, creates more opportunity for error than having equivalent facilities that are in the language and can be checked by the language rules. So again, here's a place where C++ has importantly improved on C. Finally, C was never intended as an object-oriented language. It's sort of a classic language from the era of the 60s and 70s. It's a language that's small, which is a good thing, and it supports imperative programming, which is a reasonable thing. But later, in doing large programs across many domains, one found that the object-oriented paradigm was a critical paradigm to developing large-scale software across many domains using the same kernel language. So object orientation is added to C in getting C++. So all of these things make C++ better, and all of these things can be readily learned by people with a significant C background. So far we've seen in programs we've already designed that we've used inline and const, and the inline and const material replaces the preprocessor. So sharp defined for macro gets replaced by inline as a keyword that modifies a function. And that informs the compiler that it should still retain all of the function semantics, nevertheless try to avoid function call overhead. Const is again a modifier to a type, and C++ tries to injects const into the typing system so that the compiler can help in checking const correctness. So by understanding what variables are non-modifiable, the compiler again supports correctness. We have safe casts in C++. The typical cast that involves an understood conversion is given the keyword static cast type. We have another form of encapsulation, namespace encapsulation. And again, in the development of programming and programming methodology, what's been discovered over the 50, 60 years now that there have been big digital computers, lots of programming heavily applied, that each generation of language design provides further encapsulation tools. Encapsulation means that you can build something in a self-contained way, check it out and debug it, and then plug it in as a module into something bigger. And the more effective ways that you can isolate something from its other interactions, the better you can design and keep the code bug-free. And this is just absolutely vital to writing now systems that may have as much as 100 million lines of code, systems that weren't even thought about when we had the earliest digital computers post-World War II. A very famous quote by John von Neumann, who was one of the principal founders of the modern digital era. He's a great applied mathematician who worked on things like the Manhattan Project in World War II, and sometimes we call a modern computer a von Neumann computer because he was part of a team that conceived of storing programs along with data and executing the programs out of memory. And von Neumann thought that those machines, which he viewed as scientific instruments, might have 20 or 30 codes, programs, and that would be it. That would be the extent of their usefulness. So you could hand tune them, write these codes. They wouldn't be that long. Maybe they would at most be 1,000 lines, and then you were done. And of course, that was a total misconception. He just couldn't foresee the usefulness, and especially the usefulness beyond numerical science application that computers would be available for. Okay, another thing that we're going to immediately make use of is our IOStream I/O, again, that blends some convenience with type safety, avoids the use of printfs and scanfs where we have to tie things up with special formats. And we're also going to, we also have the capability of declaring anywhere in a program. And again, the usefulness of this is localization. You want something near where it's used, especially inside a for statement where you typically want some kind of local iterative variable. In the case of a for statement, you like to see something like for int I, and I is going to be what you iterate over in the vicinity of that for statement, and it just stays there. Again, it's a localization, which is a good thing. So take the following quiz, and I'll give you a minute to look it over and answer these questions with const double pi equal 3.14159. Does true or false? Does this create a non-mutable variable pi? Is it equivalent to sharp define of pi 3.14159, which is the preprocessor alternative? And C, are both of the statements, the above statements, true? So take a second. So you've filled in your quiz, and let's look at some answers. Const double pi equals 3.14159 semicolon is now a declaration. That declaration has its context. So wherever it's been declared, the language will have its definition in that context. So we don't have to worry about a misplaced textual substitution. Now, this does create basically a const. A const is a constant, non-mutable variable. Pi is a variable. It is a variable of type double, but it cannot have its value changed in that scope, so it's entirely safe. The old style, which is B, is it equivalent? Well, at a superficial level, it's equivalent, but the answer is false. It's not an equivalent. Sharp define means that pi is a macro, and the macro substitution is going to occur throughout pi file scope. So if for some strange reason there is a pi somewhere outside of the context that you meant to use const, will still be substituted with that 3.14159. Again, this can lead to far more errors because the textual substitution is not matched up with things like blocks and classes and functions, the contexts in which you are going to declare a variable. So both are not true, and so that last thing is false. So our next topic is to show an example in C. We're going to show an important example. It's going to be trivial, but still it will, it's one of these helper functions that everybody learns to write, and you're going to want to swap two things. The function wants to swap two things, and typically that might be two ints or two doubles or two chars. And everybody learns as a C programmer, so again, this is review to you, how to do that in C. The critical thing is to remember C is a call by value language. Call by value means that arguments passed in to a function, while they may be altered internally in the function, when they come out and the function passes control back to wherever it was called, are not changed. Those arguments are handled locally, but the actual parameter itself would have been unchanged. So when we're doing a swap of an I and a J, and we want the values to change, in a call by value language, we have to use what's called indirection. Since we don't have what, and we'll turn out to have this in C++, we'll have an easier way to do it. C++ will indeed add value here as well. So the classic way you will have learned this, and we'll see it in the code, is to use pointers. And this is always a big stumbling block for beginners because it's a sort of meta level, and you have to get used to knowing what an address is and distinguishing the address of the variable from the variable and from the variable's contents, and that does slip people up. But this is something you should all be familiar with, and if you had trouble with it in the past, I think you'll appreciate that C++ makes it easier, but you also need to go back, experiment, make sure you fully understand this. So we'll first do this as a C program, and then we'll show you how to convert it. So here's a classic swap, and we look at these declarations, and the way you read those declarations is star is a pointer. So this really gets read as pointer to int. It's part of its data type. So J is a pointer to int, as is I. So we are really passing in two addresses. Pointers are variables which can take addresses. The addresses also have to be an address of something, like an int. Why do they have to be an address of something? Because knowing an address still doesn't let us interpret the contents stored at the address. We have to understand what the bits that are stored there mean. And the bits will mean different things if they're from different domains. So doubles have a different way of being read from ints and chars. So again, this is the classic C idiom for passing parameters that need modification. What happens is internally you create a temporary variable, and then you, in this case, the stars here, star means dereference. So that's saying, look at the address represented by J, go and steal its contents, whatever is stored there, think of it as a letterbox, whatever is sitting in the letterbox, and shove that contents in the address that I represents. So contents is being moved between two addresses. And then finally, in the standard swap, you have to keep track of, you need a third variable, that's what temp's for. So there's an address of an item, which we might call the address that I points at, an address of an item that J points at. We've created a temp. And if initially 5 was here and 6 was there, the temp is going to get 5. And then 6 is going to end up here, and then the temp value is going to be shoved into 5. And so we're going to end up with I pointing at something containing 6 and J pointing at something containing 5. That's something, again, that should be reviewed. So this is an assumption that you've already been programming in this language for a while, and you have facility with this concept. Now, what if I want to change the domain of swapping? In the C language, if I now want, instead of swapping integers, swapping double, I have almost the same prescription, but there are a couple of things that change. One of the things that I need to make sure of is I have to give the swap of the double a new name. So I can't have it named swap. I, of course, have different arguments appropriate to the domain. And then the code looks almost the same, except again, we have a type that's different. So what gets changed is the function name, because in C, within scope, all function names have to be unique. Otherwise, it would be ambiguous in the C language. And we have to write the code specific to the type. And we're going to see later on in C++ that we have very powerful mechanisms for code reuse that allows us even to just write one swap function, keep that one swap function with the name swap, and have it apply to arbitrary types. That's going to be very powerful and won't involve any more programming difficulty, and in some cases maybe easier than what you would have to do in C. So here's the use of those swap functions in a C program. And again, this is review, so this should be an idiom you fully understand. Here's how we print out stuff. So here we print out M and N, and we need to know formats for it. So this is going to print 5 and 10. Then we're going to perform the swap. And in the swap, we use ampersand, which everybody should know is the address operator. So this is going to say, M is a variable, but I need, because I want, in effect, values to be changed. Under the rigorous call by value semantics of C, I have to pass in addresses there. The addresses won't be changed, but the contents of what the addresses point at can be changed. And that was the whole business of using pointers, the underlying pointers. So this gets us the type we want. It's a pointer to int. It's an address of an object int being stored at the location representing M. Similarly for N, and then a swap occurs, and then if everything worked right, the resulting output would be 5 and 10. And then the same thing would happen with double. And so double would have 5.3, 10.6. And again, with double, you're seeing that we're using long floating point, these formats, in order to do our I/O. Again, it's something you have to learn when you're doing the C language, because the C language is not necessarily type safe. Now you can see what happened, just repeating what I just told you about. M started with 5 and 10. Swap was called with addresses of M and N using the address operator. And then at the end, using temp as the intermediary in the function call, you get 10 and 5 occur. You get the switch or the swap with 10 and 5. So, summarizing, C, when you want what we might call in general programming methodology, call by reference rather than call by value, has to be, uses simulation with pointers. We have call by value, of course, but because we're using pointers in direction, we get the effect of what would be called in other languages call by reference. Okay, so now I'm going to try and persuade you that the C++ version is a lot better. Well, to start with, C++ directly has a form of call by reference. So it adds to call by value with the call by reference mechanism. So we don't have to artificially create call by reference. So looking at the C++ version, we're going to see a number of interesting things. First off, in our C++ version, we're going to use C++ I/O. And this I/O is going to be type safe and convenient. Type safe, I think you will find it to be intuitive and convenient. We also have this way of contextualizing where we're using a namespace, and we use the namespace std because inside IOStream are things like cout, and they've been defined inside this namespace, and that means that their full real name is std. This is called the scope resolution operator. So that's a new thing. It's not in C. It's just a way to get more complicated names. And by using namespace std, I don't have to refer to C. I don't have to give you the full name. It knows that it should append std in any identifier and search for it, if that's available in a declaration, then use that. And now we have several things going on. We have inline. So our swap is going to be efficient. New feature, inform the compiler that we should make this highly efficient. And here is call by reference. So this is to be read as reference to int, not value of int, reference to int. And same for j. And so when things are passed there, they will automatically choose to use the variable locally without copy. And so what's passed in is actually directly manipulable. And whatever happens to its contents, when you return from that function, those changes remain. So you get no call by value overhead, because call by value implies making a local copy, and so you sometimes get efficiency by call by reference. That'll be very important later on when we deal with large-scale aggregates. And on top of it, we get to modify parameters without having to use dereferencing and addressing operators. So this looks a lot simpler, this switch. And then these values do indeed get changed. Now, a further interesting thing is I don't need two names. C++ has overloading. The fact is I can have more than one swap function in the same context. Now, why won't that be ambiguous? This would be the natural question. Earlier languages, like Algol 60 or C, wouldn't allow two functions in the same context to have the same name. it would give you a syntax error. It would say that's ambiguous. We have what's called signature matching. So the compiler provides an automatic means of differentiating between the two swaps. And it says, well, if I'm swapping doubles, I'm going to use this. If I were to swap ints, I'd use the other. As long as I can make this distinction, and these things are called signatures, so overloading involves discriminating by signature, and the signature is the types and number of arguments the function uses. Okay, let's see how that works. Here's our main. Now we're in C++. And again, lots of it looks like C, so it's not a huge transition. It's not like you're writing vastly different code from what you wrote as a C programmer. But we're going to take advantage of what I've told you makes it easier to use C++ and makes it type safe. So again, we have our set of variables, our m's and n's for the ints, our x's and y's for the doubles. But here, instead of a printf, I have the cout. And I didn't need to say, as I told you before, I didn't need to say standard : scope resolution cout, because the using statement informed the compiler that it should look for anything with standard in front of it. And now we have what looks like a natural operation. It's sort of like, think of the cout as screens. So the cout is secretly the screen. And then stuff is going to, you can think of this as flowing. Stuff is flowing to the screen. And what's flowing? First, there is the text inputs. So on the screen, here you're going to see inputs. That would be written out. Now, this is normally bit shift, but this operator is given new definitions, again, via this mechanism called overloading. And m has the value 5. So the next thing that would be printed is 5. There's actually a colon here. Then we see a comma, the string comma, and then we have n is 10. And unlike printf, in C++, the I.O. package in I.O. stream understands the type and then has default formatting for that type. So it recognizes that this is an int type, and since it's an int type, or an int value, it's going to apply its rules, its formatting rules. So you don't need to give it formatting rules. It just assumes through its knowledge of typing, which it's keeping, that a certain behavior is expected. Again, that just simplifies your job and in fact avoids errors. And then the swap function is again what looks like something simpler. You're just passing in the variables m and n, but you're passing them by reference. This was passed by reference, as opposed to passing by value. So the actual contents will be manipulated, and then again, you're going to see later on, as your printout here, you will see 10, 5. Now, how does it know to use swap of double? Well, x and y are doubles. So it does what's called a signature matching algorithm. It says, I don't use int. I'm going to use the double version because it's passing me double arguments. So it has no problem. There's no ambiguity. And that keeps down the name pollution. I don't have to choose to have a whole bunch of different swap names. If swap is strongly related with doing the same thing, but doing it with different arguments, I can keep that name, and it's much more readable code now. It's just simpler to handle. So what we found in C++ is, through the miracle of overloading and the signature matching algorithm, we've automated the ability of the compiler to select the appropriate function. The two routines to make that, to avoid an ambiguity, must have different types, or they could have different numbers of arguments. And in this case, there were different types, so it was able to select properly from the different types. So summarizing, having the same name for conceptually the same activity, in other words, using overloading, promotes readability. Readability is among the most important characteristics, a hallmark. It's an absolute hallmark of writing good code. And if you're going to do peer grading of homework submissions, you should absolutely make readability the principal guideline in assigning a grade. Overloading based on signature and later the use of generics. So we're going to talk a lot more about generics. And generics are going to be associated with a new idea called a template. It's again an idea in C++ that's very powerful. Will even make reuse more powerful in the language and give rise to a much simpler, both conceptually and in numbers of lines of code, a much simpler code base to do, and a more powerful code base. Okay, let's take a little quiz on what we've just talked about. So standard scope resolution operator cout is found in what header file? Inline can be used when declaring what? And again, a type question, what is the difference between long, 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 and int as types? So standard cout is found in IOStream, along with the overloading of the operator, semantics for overloading operator bit shift. Inline can be used when declaring functions, and it's a speed up. By the way, inline doesn't always get you inlining. It doesn't always get you inlining because you may have a function that's too complicated for the compiler to inline. And the compiler should inform you when that happens. But you can always ask a function to be inlined. Do you always want a function to be inlined? No, not necessarily, because inlining a function can lead to code bloat. And it really should be relatively small functions that get inlined, because the proportion of overhead from function call to the actual code body of a big function is very, very minimal. Most modern processors have very, very efficient ways to do function call, to give you a stack frame and load up the local arguments and do all of that. They've been designed to make function call semantics efficient. So you should really stay away from it except for very, very small functions. And again, what's the difference between the types, long, 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 int? They all allow, C++ allows for longer types than at least existed in the standard C language in 1985, though I think many compilers now incorporate this feature. So the idea in C is you have For example, a short, which might be your shortest integer type, maybe a short on a standard architecture would let you look at plus or minus 32,000, and then you'd have an int, which would let you look at a couple of billion, and then next up would be long and long, long, which may or may not be the critical requirement is that each type be at least each up the chain, each longer type be at least as long as the previous type. So there could be a compiler in which long, long, and long are essentially the same. That would be legal. So we're turning to our next main topic, the next place we can improve. And this gets you a lot of code reuse, a lot of time saving. And this is the use of generics. So where have we seen generics? I've just sort of stole the dictionary definition for generics. Relating to or characteristic of a whole group of class, meaning general, being or having a non-proprietary name such as generic drugs. So that's probably common usage. We all heard the term generic drugs. Frequently we go to the doctor, he'll say, oh, well, you should just pay a lot less, and here's the generic, having no particular distinction. So that's what generics in the general vocabulary means. Generics in C++ means programming using templates. And the critical person behind generic programming, especially generic programming in use in the C++ community, strongly influenced by Alex Stepanov. And Alex is a very remarkable person. He was originally trained as a logician. And if you think about logic, logic tries to do things that are the most general possible. It likes the most general rules. And if you've ever looked at, in your background in computer science or mathematics, at something like first order predicate calculus, which is a very common tool by both mathematical logicians and some computational theorists, you will see statements that say, for all x, there exists a y such that the following is true. You know, canonically, if you try to go back to the Greeks, you hear little tautologies like all men are mortal, Socrates is a man, what can you infer? You can always infer that Socrates is mortal. So somebody studying these very sort of grand notations that could be applicable to anything was wondering why in a programming language like a Fortran in an early day, or an Algol, or a Pascal, or an Ada, or then a C, why were you always rewriting code that was almost the same, except it's sort of like a recipe. You would have a recipe, and you could have the recipe for chicken, but you could also do exactly the same kind of cooking on beef or duck. So why not just say, this is a recipe for boiled meat, and then just whatever that particular main ingredient was, you have that one recipe, and now you can use it for, you know, again, lots of people fry fish, and they're not so worried about frying fish, whether it's trout or bass. They just know, well, you fry fish, and if it's this thick, then you have to fry it for so long. And if it's that thick, you fry it for less. And if you cook it, you want to put a little lime or lemon juice on it. So everything except for what the main ingredients are stays the same recipe. And that just makes that recipe more generically applicable. That's where generic comes in. So Stepanoff was looking for mechanisms that allowed you to code generically. Now, historically, you could do generic coding in many of these languages, especially languages like the AI language Lisp. Lisp was, in some ways, a typeless language, and so it was the responsibility of the coder to know that they were manipulating things properly, and so that they wouldn't get anything wrong in terms of type, and they could write code that could act on anything. Lisp had this very fancy data structure, the linked list built into it, and then you could do a lot of processing, storing things in these linked lists. And so it was very powerful and very concise. It was especially useful in the AI community starting in the 60s when it was invented by John McCarthy. So people who used it really wanted advantages of it in these high-performance languages like C. But the problem is that C required typing information. So you have an efficiency problem. The way you get genericity in a language like Lisp is you sacrifice some amount of low-level efficiency. So that was the tug that was going on in Stepanoff's mind. How can he keep the universality of a generic recipe and still make it efficient? Because most people, especially in the non-research community, the business community, need efficiency. Professor McCarthy used to say, oh, I'm not going to worry about efficiency. I'll just wait a few years and the machines are going to be half as expensive and 10 times as fast. And at some level, that seems to be right. But whatever you're doing, the next generation wants to do something 10 times larger. So there's nothing like enough machine speed. It's never that way. There's always something more you want to do, and you can always overstress your machine with something bigger. So Stepanoff conceived of using what was called templates to combine genericity with efficiency. So here's a very simple example. And we're going back to our swap. We're going to see why this is such a powerful concept. We have the new keyword, template. Along with that keyword, we use angle brackets, a keyword called class, and then an identifier. And conventionally, at least when we talk pedagogically about templates, we'll typically use something like T, or if we have more arguments, we might use something like T1 and T2. And it is by convention something we capitalize. It doesn't have to be, but that's capital is a convention there, because it alerts us to the fact that this is what I call a meta variable. It's going to be substituted for. The substitution is going to be with an actual type. Such as int. And we look at the code body and it looks the same as what we wrote in those earlier swaps, inline, void, swap, and here we would have said int, and here we would have said int. Everything else is the same. So basically, for very little effort, that's this extra line of code, we have what's now a universal swap routine. So here's our prescription. Here's how we write these generic routines. You take a normal function. So what I want to have you do in programming trying this out is first take a function you already know that works. And you know it works for whatever you think is a canonical type that you need. For example, you want to sum something. Maybe you want to sum an array of integers. Well, you also might want to sum an array of shorts or an array of doubles. So you take that specific type, the one you're comfortable with, write it out. And then what you do is you change it in a very minimal way. Once you see that that function runs, you add this template class T and substitute T wherever the type is a metavariable. Now it will be the responsibility of the compiler to do the proper substitution. So let's look at it. Let's see how main changes once we have templates. So we had overloading already, and now we're having this new feature, genericity, templates. And I'm going to show it with 3 different types. In fact, one of the types itself is going to involve a template. So C++, being object-oriented and generic, allows us to do coding that wasn't available in C. And one of the things we can do in C++ is typically in a library, and indeed there's, we would include the library sharp, include the standard library for complex numbers. So in this example, I'm going to swap integers, I'm going to swap doubles, and I'm going to swap complex numbers. And the complex numbers themselves are a template, and their argument to a template is the type double. And why is that? Because there could be other numerical bases for complex numbers. Think of a complex number as a real and imaginary part. That's normally what it is. And I really am not going to expect you to go revisit high school algebra or college calculus, but as some of you may remember, you use this little I notation for an imaginary number. And some of you said, oh, I'm not going to deal with mathematics anymore once I saw that. But it's just for purposes of the example. It just shows how powerful C++ is, that it naturally adds complex arithmetic. And indeed, there are languages in which complex arithmetic is basic, modern Fortran, because it's so heavily used in scientific computing, while the original Fortran didn't have complex numbers as a basic type. Later, standard Fortran added complex numbers to the basic type. But C, as a systems implementation language, never had any reason, raison d'etre, a purpose to add complex numbers. But numerical scientists, once they saw the ability to add types, new domains, jumped on C++ as a powerful language and added lots of new numerical packages with their underlying domains and their underlying types. So again, it makes perfect sense to swap things. And what's swap? Well, the compiler says, well, I have a definition, a template definition for swap. So these are 2 integer types. So the compiler writes out this code replacing T. T is replaced by int. And then the code for that type is compiled. So every time the compiler sees a signature that matches up with the meta variable T, it goes and writes the code for that meta variable and compiles it. So one thing to keep in mind is you might get what's called code bloat. You might get a whole bunch of routines for as many times as you need to write code for swap. But you're only doing that because you need it anyway. So this is automating what otherwise would be your work. And it's automating your work in a very powerful way, in a way that hopefully is going to lead to far fewer errors as well. So again, we have cout, properly overloaded, and here's our double, and the same thing's going to happen. Swap is going to be rewritten with t becoming double. The compiler is going to do that. And here, same thing, but t is going to become complex. And cout also knows, cout, this operator, also knows, because of type safety and the semantics that were put in the library, how to properly write out complex numbers as well. So we get that benefit immediately once we understand how to use C++ templates, how to use C++ I/O, and the fact is we get it in a meaningful, type-safe way. So that really makes all of this more convenient and more powerful. The compiler uses the template to write code appropriate to each set of parameters. The parameters are int, the compiled code becomes swap int int. The same thing would happen for the other two signatures. Each distinct signature is going to be mapped into a template. Now, what if you needed swap for a signature for which that template code wouldn't work? Let's say you needed to augment something where you were doing a swap of two strings, and for whatever reason that wouldn't work because you needed something that would use, in effect, a string copy and not just a kind of assignment. You can specialize and have a specific function for that swap. The specific non-template function takes precedence. So if the compiler, that just is ordinary overloading. So you can use ordinary overloading, specific instances of signatures, along with generic instances. Okay, here's a quick exercise. If you understand all these ideas, show you how powerful it is. Take what you know about summing n numbers using a C array, try and write that code, for example, for int or double, debug it in C++, and then change it to a template and make sure that it all runs. Okay, so take a break. So here is the generic version of writing a routine that can sum any kind of array. The array name is data. And in this case, we use as our variable for the generic summable. We're not using t, which is very common. And we're using summable because, as with any kind of identifier, it provides documentation. And it's telling us that the type that we replace summable with has to allow for this operation. This operation must work. What could it mean if that operation doesn't work? Well, if that operation is not defined with a particular type, let's say you have some fancy type of string and you did not define a plus equals operator overloaded on that string, then what is going to happen when the substitution of the code for that type occurs, you will get an error. Now, it should be a syntax error because the error will be that it detects that it has no available operation. That's the best kind of error. The unfortunate kind of thing is, what if it's a plus equals that isn't the intended arithmetic use of summation? Then it's going to work, and then you're going to get something at runtime. That's what you've got to be afraid of with with templates. They can be overly general, and if the code makes sense, something will run. And this is a reminder. You use summable here to remind you that the replacement types must have this arithmetic idea of summation. So templates are very powerful. Templates, while they're generic, that genericity doesn't necessarily mean that every possible type under the sun can use it. It means that the types that you should use it for should be meaningful in terms of the code you're writing. Some things are going to be near universal. The notion of swapping two things, that's probably going to be near universal. But the notion of adding things means that things have to be summable. So again, if you want to go back to your analogy of whatever your basic recipe book is, yes, certain recipes can use arbitrary fish in frying them, but then you wouldn't want to use the same recipe on lettuce, some other ingredient, where that kind of ingredient would be damaged by the recipe, would lead to something that was unexpected. So we're going to take up C++ functions and generics, and then our other big topic is going to be graph algorithms. And graph algorithms are, if you haven't studied this in your background, if you recall, I said most of you should have at least the equivalent of 1 year of computer science, especially data structure topics. And graphs are one of the critical data structures in all of computer science. And the critical homework in this class is going to involve homework on graphs. So that's going to be how we learn our C++. We're going to learn C++, but we're going to learn some interesting computer science ideas, or at least for many of you, you probably already know these, so it'll be review. So it'll make it easier for you if you already have a background in which you understand the minimum spanning tree algorithm or the Dijkstra shortest path algorithm. In any case, those will all be reviewed, and there are also many sources in which you can go to and read carefully about them, notably the Wikipedia. So here's some of the new stuff we've had. We have default parameters in C++. We have variable argument lists in C++. We have the use of const in C++, including const as part of the signature for function parameters. So far, when we've looked at generics, we've only our recipes, our generic recipes, have had a single meta variable, typically a t that we get substituted for. But it's also possible to have generics that are far more complex and can involve multiple types in the generic recipe. And while I've alluded to operator overloading, especially the notion of overloading the bit shift operators to be I/O operators, I'm going to also begin to explain how you do your own operator overloading. So this is new stuff we're going to see. So a little review. How in C did you write a function to sum, for example, an array of doubles? And we've seen such a function in C. A couple of things that we notice is here's a signature for an array. Alternatively, that could have been written in pointer notation. So this also would have worked, either one. Because basically in the C community, arrays are just base pointers. Now we have an initialization of the summing variable. This is going to be the loop variable. And again, this is just a very standard idiom for handling arrays, idiom for arrays. We have a size that gets passed in. That tells us how many elements to sum. So just to remind you again of the dictionary definition, generics relate to an entire group or class. It's general. In some sense, that's what we're using here. It's just a general style of programming. Biology, it means very specifically relating to a genus. Not having a brand name is another designation where we could have generic soap, and that's very often used in the pharmaceutical industry, where you mean something non-proprietary. And then finally, in grammar, it refers to neither masculine or feminine gender. So again, there's a little bit of universality. So generic programming is somehow a universal kind of programming. Writing code that can use an arbitrary type or types in C++ done with a template. And we saw it in the one argument situation. So here again is, let's see how you would do that for the generic sum of an array. That was what we were asking you to do as a little quiz assignment. And we typically, when we're summing something like an array, we want the summing variable to start at 0. But we will also see that we might want to generalize that. For example, we might have two data sets, and we want to pass in one data set, sum it, and then whatever its value, its summable value is, for example, here it would have been 24 in data set 1, we want to continue with data set 2 and sum it as well, starting at 24. How would we do this generically? Here we see some of those C++ features. Here we see ideas that are very standard. Any C programmer could manage this, but immediately you get a lot more power in C++. So again, we have this meta variable, T. Possibly I should have called it summable. That may be a better name. Keep in mind that this won't work universally. It'll work when we see this operation working properly. Now we have here a default value. And what this means is whatever that type is, the summing, where we're summing S, will ordinarily, the usual case, the usual suspects, the usual case, so this means I don't have to specify things when it's the usual case. It's going to be assumed to be 0. But if it's not the usual case, I will have to substitute an actual parameter for this formal parameter. And here also we see this other idea in C++ where we can localize to the for statement through a declaration in this component of the for statement. A local counting variable. So we have in C++ the concept of default parameter. We also have in C++ the concept that we can use const correctness. So we can't do this in C, but in C++, by specifying const here, that means any data sitting in that array is not mutable. That means the compiler can presumably check that that criteria is met, so that you don't inadvertently in this program mess with your array contents. So again, that's good practice. If I leave const off, nothing changes. Nothing changes. So const is really a little added documentation and something the compiler can automatically check. Now, with a default parameter, we are allowed to have two different signatures. Here, the actual parameter would mean S started at 58. Here, by default, because things got left out, S would start at 0. So again, we have to, in C++, really understand what we call the signature matching algorithm. It's a selection mechanism. The compiler uses it and uses it to properly choose and write code. We could, by the way, have had a default to size. We could use more than one default in the argument list. So let's say most of my data sets are size 100 for whatever reason. So then, if I wanted to, this could be defaulted. Now, it turns out, you might want to think about it, I can have a bunch of arguments but if I have default arguments with default values, all the defaults, there can't be a default that skips over an argument because there's no way of positionally determining what is the default value for an argument. Okay, you can play with that if you didn't understand what I said. Think about it. Here's the main program. In that main program, we're going to use that template. There are two different types of arrays. This is an array event. And this is an array of double. And then the compiler knows what to select. And in both cases, there was a default. In this case, it was the sum s equals 0. In this case, it's also going to be s equals 0, but this is going to be in the double domain. So you might realize that that notationally is really 0.0. It's better thought of as 0.0. And the compiler will write that code for you. So again, it shows you the power of templates, the power of generic programming. Elements of the array source are not to be modified. That's the meaning of const correctness. Simple parameters such as size are typically called by value and cannot be modified by the calling routine. So we didn't declare size to be const because there's no need to. That's just a standard call by value and it would be redundant. And this concept is called const correctness and is emphasized throughout the C++ language. All right, as an exercise, take that code and instead of iterating over addition, iterate over subtraction. And as a further exercise to show that you really can manage templates and see their power, write a template function that instead of using an arithmetic operation, does output of the array elements. And I'll leave that for an exercise for you. So the answer is to provide a different operation here. And we could provide arbitrary operations that this would be repeated multiplication. In this case, we provide a subtraction. That would have been the answer. And here is a different form of processing entirely. Pretty simple. Again, we've chosen to use a very standard idiom for processing arrays, and then in that idiom we can choose whatever we need to do when we handle the array contents. And templates become very powerful because if those are universal methods, methods necessary for the contents of an arbitrary array, the template just means we can write it once, debug it on a standard type, and then stick it away in our library for use whenever. So templates so far have been templates of one meta-argument, but there's actually no restriction. But keep in mind that most of what you want to do is templates of one argument. Once you start multiple argument templates, you get into horrendous complexity, unneeded complexity in most cases, and it's a prescription for doing fairly dangerous things that are unanticipated. But in some cases they're useful, and so it's desirable to know how to use it and when to use it. So again, warning, be careful. You really have to understand when you need more of these typically meta types. But let's see a situation where maybe that would be reasonable. Here is code with the two templates. And it's a copy routine. So we want to copy some source data into some destination data. And we don't necessarily want, we could have this as all T, but that would mean that the copy would have to be, for example, an integer array copied to an integer array. And let's notice a couple things about this code. First off, in the signature, the source argument is const, so we have a little bit of const correctness. We're indicating to the user, to the reader, to the compiler, don't modify the source array. Not true for the destination array. Well, obviously, that's what we want done. We want the destination array to have a copy of the source array. And again, we have a variable size, that's how much to be copied, and for the moment, it's conceivable that we would have a default, but it's probably not that useful to have a default in this. There wouldn't be some standard default that would be used more than some very specific value. So it would not make sense to say size here is 100. That would be unusual. And then the other critical thing here we're doing is this safe casting. And this is what, in my mind, makes this a not unreasonable routine. Because if I don't have a safe cast for type T1, casting the object of type T2, then when this code runs, is going to be an error if no safe casting. So, or the compiler will recognize that it doesn't have a safe cast opportunity and provide you a compile time error. In any case, the code won't work, and it won't work in a manner that will be easily detected. And in cases in which it will work, we know that we have a safe way to massage the source contents into the destination contents. So what would be a safe thing? If I had integer data and I wanted to turn it into double data, that would be perfectly reasonable here. Or vice versa. Both kinds of conversions. One is called a promotion, taking the data in the integer domain and turning it into double. And the other is called a demotion. But both are conventionally well understood, handleable by the safe conversion routines, and largely portable. The program as is should work regardless of what computer system it's being run on. So here is a multiple use of template arguments that is not unreasonable. This brings up the question of casting. Again, type safety. That's a big improvement in the C world, in the C++ world over the C world. And one way that the C world was very loose with types is, in that world, you could say things like, double with some kind of expression. Now, whatever this expression was, the C compiler said, force that expression to be interpretable as a double, whether that was portable or not portable. Since there were different characteristics in C++, actually C++ is a wider range of programming, including object-oriented programming, in which certain types in type hierarchies in the OO community, these are called polymorphic types, inheritance structures, have other kinds of conversion opportunities that are well understood. You get into a much richer sense of conversion opportunities in the C++ world, and you have to be far more careful about it. So C++ defines 4 basic types of conversion. The safe cast type is static cast. But then highly unsafe is reinterpret cast. That's sort of what's going on here. Sort of that's corresponding to, but it's alerting you to the fact that, gee, for whatever reason, which is probably a hack, which is, in my view, something you shouldn't do. So if I was your manager, this would be a no. You would really have to convince me that you want it, that there's a good reason to do a reinterpret cast. I would be extraordinarily reluctant to be using that. And then, again, in most instances for me, this is also a no. You can cast away constants. Sometimes you want something that was set to be const to not be constant, so you would make it modifiable. But in my sense, you're mixing up 2 characteristics. Why did you make it constant in the first place? So you're really saying, oh, make that thing mostly constant. I don't want pi to all of a sudden change. I don't want to say, gee, it's going to be pi, but there may be some time I want to tweak that. It's just not how I'm going to think. So again, most of these other kinds of casts should basically be thrown out of your repertoire. Safe casting is okay. The old style casting, while available in many compilers, is deprecated. Deprecated means don't use it. The compiler writer is at liberty of actually denying its use. And then there are some special cases where class hierarchies involved, dynamic casting, where when you're doing some very fancy object-oriented programming, this may be required. But again, I'm not a fan. So I would say safe casting, yes. And the others are largely no. So the other thing that we're going to emphasize in this course is algorithmic graph theory. That's going to be the domain we're largely going to use for examples. And there's several reasons for it. It turns out that graph theory is an underpinning to a lot of the discrete problems of interest in computer science. It shows up all over the place. In artificial intelligence, there are search algorithms that are foundationally graph theory algorithms. In your GPS devices, where you're asking your car to find you a route, you're doing basically very efficient, very complex graph theory calculations. When you're working on the internet and you're connecting packets between machines over the many hundreds of millions of nodes now on the internet, you're basically doing graph theory. So this is a great topic. It's foundational in computer science. It requires a lot of careful thought in the use of data structures. It's not typically, in an ordinary computer language, a built-in data type. It's not a native data type. So one of the things we're going to find with graph theory is thinking about how to implement a graph as a data type. That's going to be part of our understanding of using C++ as an object-oriented language. And hopefully you have some of that background. So you should have some notion of what object orientation is. Maybe you even have experience with a language like Java or Python that has object orientation built in. And that experience will stand you in good stead, but you'll still have to see how C++ uses it. Again, graph theory by itself is just a very important topic in computational science and applicable all over. So the first thing I want you to do, since to some extent I'm hoping this is review for you, is draw the complete graph of 4 nodes. And I'll give you a definition. A complete graph, if you've forgotten that, is a graph in which every edge exists in that graph, in that map. So if you have San Francisco, Los Angeles, San Jose, and Salinas as cities, that would be 4 nodes. Then there's a direct path from each city to every other city in that graph, and that would be called a complete graph. So take a second and try and draw it. So I'm going to draw it for you. And we're going to assume that we are using undirected edges. So there are directed edges and undirected edges in graph theory, but most of what I'll be doing will be using undirected edges. And undirected edges are like roads that are two-way roads. You can go in either direction. So here is city 1 to city 2. Here's city 2 to city 3, city 3 to city 4, city 4 back to city 1. But that's not complete yet. I can also go from city 1 to city 3. And I can also go from city 2 to city 4. I'll do it with a little crossover. Are there any other connections that can be made between these? No. So you'll notice a certain property here. Now, in the graph theory world, this is called K4. And you should be able to, if you want to do K5 now, that would be five nodes, all edges in 5 nodes, K6 and so on. K is just a notation meaning complete graph. So we have 4 nodes. I'm going to label them 1, 2, 3, 4. We could have labeled them as well A, B, C, D, or you could have labeled them San Francisco, Salinas, San Jose, Los Angeles. And then the other property I want you to know about, or another definition, is look at node 3. It has 3 edges out. It has an edge between 3 and 2. I'm going to notationally write that in between parentheses. It has an edge between 3 and 4. It has an edge between 3 and 1. So it has 3 edges, and this is called degree. So the degree of any of these nodes, in fact, they all have 3 edges. So degree of, for example, node 1 is 3. In fact, the degree of any of them is 3. In fact, if I have the graph K4, then the degree of each node is 1 less than 4, 3. And for K5, what do you think? It would be 4. The degree of K5 would be 4. The degree of K10 would be 9. The degree of K a million would be 999,999, though that's going to take quite a while to draw, so I'm not going to ask you to draw K a million. Anyway, that's why we have computers. So this is our answer. I just want to give you a little flavor of where this all came from. So this came from, in some ways, a fancy problem, almost a real-world problem, actually. And graph theory was invented by a very famous mathematician, Euler, Leonhard Euler, 1735. Euler was incredibly prolific, maybe the most important mathematician of the 18th century. And he was studying a problem in his region, and it was called the 7 Bridges of Königsberg problem. And in trying to solve that problem, he used his mathematical genius to figure out an abstraction that let him logically approach this problem of crossing 7 bridges. So let me show you what that problem is. There was a city, Königsberg. There was a river in the city, several forks in it, and there were 7 bridges crossing the river, and they're shown here in the slide. And the typical Sunday afternoon stroll. So if you were young lovers and you wanted to do something on a Sunday afternoon, you decided to stroll in a way that got you across all 7 bridges, and that got you into every area of the city. The conundrum for the strollers was, can I go and cross every bridge once and only once and cover all of these sections of the city? Is there a way to do this? And nobody knew how to do it. And indeed, by converting it into an abstract problem, Euler was able to show that no such path existed. That later, path like that was later called an Euler path in his honor. That's the origins. It's a good story. Those are the origins of graph theory. And graph theory was a mathematical concept useful for many years, used by mathematicians, but not that important to real-world applications until the 20th century. In the 20th century, coupled with computers, many computational problems, including optimization problems, including deduction problems, including matching problems, including looking things up in databases, all could be seen you could get incredible insights into these problems by representing these things as graph theory problems. So when we use graphs on computers, we need to create an internal structure, a data structure for representing that graph, such as trying to represent K4. And what we've discovered in computer science, and again, I hope for many of you this is a review, if it's trivial, you can move on, is 2 major representations. One's called a connectivity matrix, and the other's called an edgeless representation. And there are trade-offs. With data structures, there are always trade-offs. So for some algorithms and for some graphs, one representation would have strong benefits over the second representation. The typical trade-offs involve how much data you need to store and how efficient the algorithm is. So it may indeed be that one representation requires too much storage for a particular problem, and another representation might require too much processing. So we find that both are extremely useful. Sometimes in the same problem, we want to use both. But overall, for those of you who are trying to review this, probably if you've had experience, it's largely with the edgeless representation. The edgeless representation is typically much better when the graph is not full, when there's not large numbers of edges, high degrees. So if you have a graph of like size 100, meaning there are 100 vertices or nodes, and the average degree in that graph is maybe 4. So for the 100 nodes, you're going to have something like 400 edges. That would be considered sparse. But if you had a graph in which there were 100 nodes and the average degree was 50 or 60, then you would have a huge number of edges, and that would be dense. And typically, the rule of thumb is dense graphs, matrix representation is frequently better. Sparse graphs, edgeless representation is better. Most real-world problems are relatively sparse. A representation of a directed graph with n vertices can use a list, for example, an array of n lists of vertices. So that in list I, you're representing for a node I that you've labeled with the number I, each vertex that's directly connected, each vertex that can be reached from I to vertex j. And then some other terminology is you may also want in that graph to have not only edges, but a weight on the edge, a cost on the edge. So think about going from San Francisco to San Jose. Roughly speaking, we're talking 60 miles. You may be a little off there, but I think it's somewhere between 60 and 80 miles. And that would be a cost. You're going to drive in a car, you're going to have to drive 60 miles. That's one way to measure that versus going from San Francisco to Marin, which maybe is 2 miles. So if you have an opportunity to go to one place or the other for some kind of vacation day, and that cost figured in, you're likely to go to Marin rather than to San Jose. And indeed, in route finding, when you try to find, when your onboard computer in your car tries to find you a route, it's generally trying to find you a least costly route, either based on time or based on distance. So that's a weighted graph. In an undirected graph, anytime you have, it was what we were doing with K4, anytime you have a road from, let's use San Jose, San Francisco again, anytime you can go from San Francisco to San Jose, you can use the same road and go back. So a lot of the problems, because we just want to avoid the directed case, but it's not that much harder to deal with the directed case, is we're going to think of two-way roads. But analogously, one-way roads are perfectly fine, and all of the algorithms I will be talking about could readily be adapted to the directed case. So here's a matrix versus a list of a graph. They're actually the same graph. And let me draw directly on here what graph is being represented. I'm going to have nodes 1, nodes 2, nodes 3, and nodes 4. And in this matrix case, it says 1 linked with 1. There is a road. So that is a special road. I'm going to usually not worry about that. That's a loop. Most of the graphs I will be talking about will be loop-free because loops aren't particularly interesting. The fact I'm in San Francisco and I can drive around in San Francisco is a loop. There's also from 1 a road to 2. There's also from 1 a road to 3. There's also a road from 1 to 4. So all those 1 entries mean that I was able to drive in this direction between 1 and 2, 1 and 3, 1 and 4. Now 2 has uniquely 1 edge. It's 2 to 1. Three has 2 edges. 3 can go to 2, and 3 can go to 4. 4 can go to 2, and 4 to go to 3. So that's the graph that's being represented here. And you can see in the edge representation, the list, the edge list, the same information. I now have 4 lists. These are the vertex numbers, the node numbers. And then this is what 1 is linked to. It's linked to 1, that's the loop. It's linked to 2, it's linked to 3, it's linked to 4. 2 only is a degree 1 node. Okay. So you should be able to do what I've just done. You should be able to generate from a graph. Here's a graph. I've actually drawn it here. We were drawing it in real time. I'm not a great drawer of graphs, but you see how the model is. And indeed, you should be able to take a graph of this kind and produce either of those 2 representations. So that's an important skill set. So here's a quiz. Here is undirected graph, meaning that each edge can go in either direction. Generate an edgeless representation and a matrix representation for it. So it has 4 edges and 5 nodes. A little crisscross graph. Okay, take a second. And the answer is, here is a matrix representation. And let's see if this provides it. Now notice, in this case, we have symmetry. I'm going to have 1, 2, 3, I think I'm going to want to put 3 in the middle. I'm going to put 3 in the middle. I'm going to do 5. Okay. I think this will work. So I have 1 linked to 3. And notice I have 3 linked to 1. That's the symmetry. 1 linked to 3, 3 linked to 1. 2 linked to 3, 4 linked to 3, 5 linked to 3, and then 3, there's no loops, and it's also linked to 1, 2, 3, and 4. So that's exactly what we just saw. So all of you should have been able to draw that once you saw the graph in the previous slide. And here is the same thing, and I don't have to change my drawing, but it's just the edge list, which now, since this is what we might call a sparse graph, is degree 1 for each of these nodes. Each of these nodes is degree 1. Notice, by the way, that this graph is what we call connected. That'll be a nice property that'll be of interest to us when we start working on our algorithms. And here's 3. 3 has a degree of 4. All the other have degree of 1, and these are the undirected case. Oh, now we're going to describe one of the most important algorithms in computer science, the Dijkstra shortest path algorithm. Edward Dijkstra is a Dutch computer scientist and is one of the most important figures in modern computer science. He was involved in computer language design, ideas in compiling, ideas in the semantics, correctness of programming, and he invented a number of very, very clever and important algorithms. Dijkstra started his career in the Netherlands at the Mathematical Centrum and later became a professor at the University of Texas in the United States. And he's also one of the very first people to win the Turing Award, which hopefully most of you know about, but if you don't, the people who've won the Turing Award are what the analogy is MacArthur Prizes or Nobel Prizes. We don't have such things in computer science per se, and the Turing Award is considered our Nobel Prize. So in the Dijkstra shortest path algorithm that we're going to describe, we're going to use undirected graphs with weightings, with costs. The costs are going to all be non-negative. And conceptually, what you should keep in mind is a roadmap. And the canonical problem is finding a shortest route from one place to another. So if you're looking for a road trip and you're going between Chicago and Los Angeles and you want a shortest path, you have a very big map, lots of roads. You typically might go to AAA and get some specific assistance, or nowadays you could just use your onboard trip computer. And they indeed, in some important sense, embed the Dijkstra algorithm. And we're going to learn how to program this critical algorithm, and indeed it's going to be our next programming assignment. So the idea is we have a source and a destination, Chicago to Los Angeles, and between the source and destination, we want to find a shortest path. The critical steps in the Dijkstra algorithm are to maintain what I call 2 sets. One is a set of closed nodes. The closed nodes are nodes that have known shortest distances. Now, if we're starting from Chicago, what do we know? Right off the cuff, we know the shortest distance from Chicago to Chicago. That's 0. That's like the trivial case. So the algorithm would start with the source node being put in the closed set, and that source node would have value 0. And then in the open set, we would look for immediate successors of S and place their distance in the open set. So the open set is what's reachable. And at any time in the open set, we have what's reachable, and we have a calculation based on the edge costs from things in the closed set. And what we do, our major iterative step, is we pick the open node in that list whose cost is least. Pick the open node who has least cost. Whoops, list cost, not list cost, least cost. Confusing list and least. Okay. If in this iterative step we pick a node that is the termination node, if we are moving along from Chicago and we've reached Los Angeles, and Los Angeles gets thrown in the closed set, we can stop. The algorithm guarantees that when the destination node is placed in the closed set, the calculation is provably a shortest distance. If the destination node is not the node picked as the next least node from the open set, we compute all the direct successors from that node. So if that node, n has least cost, we look at the edges out of n, and they have a cost. They might be cost of nj, where nj are the determiners of the edge. And n will have a value, which is its value of the cost from S, from the source. So n has some cost, some current cost, back to S. And that cost, whatever that is, S to n, plus Cn of j, is what it takes to reach j. Now, either j is already in the open set. We have like three cases. J is in the closed set. If j was already in the closed set, we don't need to bother with it, because we already know by the nature of Dijkstra's algorithm that we have a shortest path to j. If j is not in the open set or the closed set, then we put it in the open set. We now have a new path, a way to get to j. So we're somewhere past Chicago, maybe we're approaching Kansas City, and we haven't yet reached Kansas City in any kind of path that we've calculated, and we see we can get to Kansas City. That would be placed in the open set with whatever its value is, traced back to Chicago. And the last case is we already had an alternative route. We had a pre-computed route. So J, or Kansas City in this case, was already in the open set, but this new route improves on the old route, because we're trying to search for least costly paths. In that case, we update the path. So we have three conditions: open set, a possibility for updating, or it's already in the closed set. And then if the node D is picked, we stop. There's no further need to look for successors. Or if there's no more successors, we can't get to D. So if we tried to go from Chicago to Honolulu, we would find all sorts of paths to places like Seattle and El Paso and God knows what else, Los Angeles, but we would have no road route to Honolulu. So we would exhaust if we had tried to put into our travel computer, find me a road from Chicago to Honolulu, it would stop. And otherwise, some shortest path tree is maintained in the calculation. And that lets us, when it's done, having stopped at D, not only have the value of the shortest route, but be able to trace back the shortest route. So I'm going to simulate Dijkstra by hand, and I'm going to simulate it on this next map. And I'm going to draw things in red, and I'm going to start with S. And I'm going to want to get us to T. In this case, I'm doing it in a directed graph. So this was just a case that I have manufactured, and I'll show it to you in the directed case. But it shouldn't be any different in the undirected case. So initially, in the open set, S has value 0, and then S can reach A. So this is the closed set, and its value is 4. S can reach B, and its value is 3. S can reach D, and its value is 7. And that's it. The out-degree edges of S are 3. So now we look at the open set. We pick S equals B. So B comes into the closed set with value 3. So in some sense, Dijkstra's algorithm has picked out this. And now B becomes the node we expand from. And so we search B. Now B can go back to S, but that's not a value since S is in the closed set. And B can go to D, so we have to check. If B went to D, it would be 3 plus 4. But we already have D at 7, so there's no reason to update it. And that's the only 2 ways B can go. So there isn't anything new in the open set. So we would come back and we would get as our least value A, whose value is 4. And so now our Dijkstra's shortest path tree would be, at this point in the second iteration, also S going to A with 4. Now, A has some new things we can go to. So from A, we can go to C. The value was 4 plus 1, so now it's 5. And that's the only thing A can go to. But 5 is indeed the best value. So we put in C in the closed set with C's value equal 5. And C can reach E with value 6. And C can reach D, and that would be value 8. 8 doesn't improve on 7, so we don't update that. But we can go CE, and that's value 6. So now we cross out this. We get E. We get it equals 6. We go back, and we find we can go to E. Whoops. No, E already went to 6. Excuse me. We go back, and E is now in the open set. E has to be expanded. So we can look at E to D. Now, E can't go to D directly. That's the wrong direction. But E can go to G, and G is value 8. And E can go to T. So it can go to G for value 8. It can go to T, and that's value 10. Now, just because it can reach T, which is our destination, the terminus, doesn't mean we go there, because this is still in the open set. The only time we're guaranteed a best or least costly path is when something's been stored in the closed set, and there's still values less than 10, so they have to be explored. The next value that needs to be explored is S going to D at 7. So S going to D at 7 makes D equals 7 in the closed set. And then we have D can go to F. So 7 plus 5 is 12. D from here can go to T. So that's 7 plus 3, which is 10, but that hasn't improved the value, so we don't update anything. And D can go to E, but E is in the closed set, so we don't do anything with that either. So here, we go back, we look, we got an E going to G at 8. And from 8, we can go back to E. E's already in the closed set. We can go from G to T, but 8 plus 3 is 11. We don't improve on 10, so we leave it alone. We're done with the updates. We come back, select the node, and now we find E to T, which is value 10, and E to T. So T equals 10. We can terminate. And if we keep our backlinks in this map, we can even find the shortest path. Now notice it wasn't unique. We could have found the shortest paths, which would have been S to D and D to T. That would have also been 10. So this doesn't guarantee any kind of uniqueness, but it does guarantee that we get a least costly path. You should practice with other graphs. And the assignment I'm giving out now is that you will try to do a Dijkstra shortest path algorithm, which will mean that you need to decide on a representation. My recommendation is the list representation. It's a little more flexible, but it's perfectly okay if you do the matrix representation or even do both, depending on how ambitious you are. And that'll be an assignment that I'll be expecting for the next turn-in time. Okay, today we're going to get to a critical topic in object-oriented programming. So C++ so far has been a better C. And as a better C, it still can be used much as old standard Kernighan and Ritchie C was used, an imperative systems implementation language. Nothing changes. We just have improvements. So far, we've emphasized those improvements. But in today's lectures, we're going to talk about how you can become an object-oriented programmer using the methodology that was pioneered by the Smalltalk people at Park in the 80s, and then when pushed by Bjorn Strustrup at Bell Labs in the mid-85 release of the first form of C++, which caught on immediately. It just changed industry's perspective on using one language effectively for most problem domains. So OO lets us vastly expand the usability of the C language. And we're going to take as an example, a very, very simple example. Of why we're doing that is because it's something that you'll intuitively understand. It's a point in the XY plane. We've been working with points ever since grade school. So that's a natural object to talk about. And then if you're following along in the text, the point at which you should be reading now is chapters 4 and 5. That begins to talk about classes and type extensibility, the OO characteristics of C++. So let's review your C programmers. You need to keep this in mind when you go over to OO. So I'd like you to name 3 native types in C. And then if you have the expression 3 divide symbol 4, what is its value? This is all in the context of C. And if you have the expression 3.0 divide 4, what is its value? So all of you are C programmers. This should be trivial. Okay. C, the native types. The native types of the C language, and therefore the native types of the C++ language, include short, int, double, char, long, long double, int star, all sorts of basic pointer types. So these are any of the essential native types of the language. Anything involving those types, you just declare them with those keywords that determine those types, and then you can use the language relatively easily and efficiently if those types are expressive of the problem domain. 3 divide 4 is a 0, and this always is a gotcha. Why? Because divide, when it sees 2 integer arguments, it does integer division. So the full part of it, it just falls off. It has to be in the next answer, 3.0, which is a double literal. It's a constant in the double domain. And when you divide a double by an int, then you're in the double domain, and then you get the possibly intuitive answer, 3/4. So what we're learning from the C native types is type matters. Type matters in very important ways. And we have to be very careful about use of types, because use of types will also define the character of how the operator is determined, and will also define things which we'll talk about later, which are conversion opportunities. All this gets more complex in C++ because in C++ we add to the native types. We extend the native types. That's the heart of object-oriented programming. Object-oriented programming lets us program naturally in new domains, domains that not necessarily have types in the native language that fit the domains. So for example, we might want to write programs that involve manipulation of colors. Imagine having a windowing system, and inside your windowing system you have different menu options, and possibly within the menu options you're using color to have different levels of expressivity. So you might want a color type. This is a simple form of type extensibility. Typically, colors could be defined as a small, discrete set of items. So here we see an enumerated type, which is one form of type extensibility in the C++ language, that has a color red, a color white, and a color green. Now, with these colors, this is basically a form of simple integer type. And the reason we use capital red is that's an identifier, that's an enumerator, it's a enum ID. And capitalization are a convention. They just highlight that we're expressing a form of integer constant. And red, when no value is specified, will be automatically assigned 0. That's in the old grand tradition of the C community. Everything starts at 0. White will be 1 and green will be 2. And that's what we'll do normally. We also will have the ability to override these values by being explicit. We could say white is 3. And that would mean red starts at 0, white starts at 3, and then the sequence continues from 3 to 4. Now, why should we use enum? Some of you have experience in enum. Enum was added even to the C language, and so in many other programming languages, there are enumerated types. It's a multiple choice question. Just take a second. Can you use a named integer instead of an enumerated type to get that kind of constant? Can you use a sharp define, much like in the preprocessor keeping C old style for these enumerator constants like red and white? Or is it best to have a small related set of constants? So which reason exists for using enum? It is quite true that you could just use a const declaration. For example, if we wanted true and false as two related constants, we could say constant true is 1, false is 0, and then we'd have that. We could also use this in old C style, but again, there are safety issues. But enumerated types are even better than either of these others, where there is a grouping of related constants, where you want to think about it as type extensibility and not just arbitrary named integer constants. So enumerated types let you have small sets of related constants, and in C++, we're going to start to see that we can do operator overloading. We can give new meanings to the already existing operators defined in the C language, so that these extended types, these new types, get to have the look and feel of the native types. And that's the secret to good OO programming, making your extended types, your type extension, natural, making it seem like these types are native. Okay, so critical to creating a new type is to follow as your paradigm the behaviors of native types. Native types are types like ints and floats, and you want your created type to mimic those as much as possible. And what we're going to do is try to use a natural type, namely the days of the week, and make that a enumerated type. And this is the central lesson of object orientation. Object orientation is a way to expand a programming language to incorporate new types that were not built into the core of the language. In the early days of programming languages, kitchen sink approaches to languages like PL1 tried to put every type possible that could be imagined at the time into the language. And that was just very awkward and made for a ponderous language. Object orientation changed this and said, let's have some techniques that let us extend the existing types in such a way that it's seamless. They look and feel like the native types. And that's what we're trying to achieve here. So, critical to that is also to be able to redefine operators, give them new definitions for the new types. And that's what we're going to concentrate on here. We have an enumerated type. The enumerated type has Sunday, Monday, Tuesday, Wednesday, which means that the enumerator Sunday has explicitly value 0, and by the time you get to Saturday, Saturday would have the explicit value 6. Also, notice that we have defined within this type a new meaning for the auto increment operator. Now, why did we choose the auto increment operator? The auto increment operator, when used on integer types, changes the type by 1. So if we had an integer type that was 100 and we auto incremented it, we would get 101. Or if it was 107, we'd get 108. And here we want the same behavior. We want to be able to take a day of the week and say, what's the next day? So we can imagine that this is a routine that gets us a next day. If it's Wednesday, the next day is Thursday. And we're creating a calculus on this kind of calendar object, which makes sense intuitively. People know what the next day is, what add one day to that day in the week is, and what the next day is that you get. Now let's look at this definition. We have inline, which we've seen. We use inline because we expect in this calculus to use this operator frequently, and we want it to not pay a high cost and efficiency. And inline gets us that. It tells the compiler, wait a minute, try to inline this code, not to use it as a function call. We have a return type, which is days. Why? Because we want to take a day like Tuesday and return a day Wednesday. We don't want to return an integer type or some other type. We could do something like that, but that wouldn't make sense. So we're taking a day and converting it to another day. And then we have a unary argument, one argument. So anytime we have an operator, and we do operator overloading, giving an operator a new meaning, we are constrained. And one of the critical constraints is, what kind of operator is it? Is it a unary operator or a binary operator? Those are the two kinds of operators you find in C++. You're not allowed to overload the question mark colon operator, which is a ternary operator. So you only have the unary operators and the binary operators, and you can give them new meanings. If you're not using meanings on their, you can't overload them for their existing types, because that would be that would create chaos. So if it doesn't have a meaning, you can give it a new meaning. You give it a new meaning by deciding and taking explicitly what the argument is. The other thing you can't change is you can't change the precedence order of the operator. So if you recall, auto increments of very high precedence, that remains. And let's see the actual semantics. The actual semantics say, add 1, casting it safely to an int. So if it was Sunday, you would add 1 and make it Monday, in effect. And then you would modulo it with 7. Why do you modulo it with 7? Because the next day after Saturday is Sunday. So if you added 1, you would get 7. 7 modulo 7 is 0. So that gets you Sunday. So you're really using modulo arithmetic when you talk about the calendar. So this is the right semantics. And notice it gets the return type days. So it's not creating an integer. The integer is automatically mapped back into, converted into days. Okay. Anytime we have a new type, again, this is part of our object-oriented design idiom. Anytime we have a new type, we would also like to have a familiar way to do I/O, input-output. Remember, the operator, which in the core language is a bit shift, is being used in the output of the language as a writing operator. So this is really like in the C language, a printf, except here we notationally want to use this typically obscure and rarely used bit shift for this other purpose, and in fact intuitively the arrows going in that direction suggest output. And again, you should get used to this idiom. So there are several things I want to point out. The return type is going to be a reference to OStream. We'll see why. That's because we're going to want associativity in the output stream. The operator is a binary operator, so it needs two arguments. One of the arguments is going to be an output stream, and the second argument is going to be the type we want to define the output for, the output operation for. And again, these are traditionally, makes sense, that they are call by reference. They're call by reference because the OStream, we don't want a copy. We want to directly use that OStream. For efficiency purposes, for many other reasons, we just want a referential connection to the output stream. However complicated, this turns out to be simple, so we could have just used call by value, but as I say, it's an idiom, so keep this in mind. Most commonly, the output variable is not to be mutated, so you can't change it. That's why we use const. And if it's something complex, we also want to call it by reference. So it's not locally copied. And then you can see the semantics are very simple. We use a switch statement, and again, this is idiomatic for a switch statement. We do a case. Since these are an integral type, enumerators are integral types. Case is Sunday lets us print out the string sun. Alternatively, if I wasn't lazy, you might have liked to print out the full name. And once you get that case, this is the assignment to out, and then this is what you return. You return the output stream as the value of this overloaded operator. So as I say, normally bit shift, but bit shift is very specialized, so it's not very much used. And then for any newly created type, new type that you extend, there's an expectation that you've overloaded this operator to provide a proper form of output. So now let's make use of all this in a main. We're using our new type, D. We're assigning it one of its enumerator values, Monday. So D is Monday. And we have an uninitialized variable, days variable, E. And now, because we have extended the language, we've done operator overloading. This is really a call on the procedure operator plus plus type days. It's really calling this. Recall the semantics. This is the auto increment operator. This has the right flavor. What does it mean to auto increment Monday? Add 1 to Monday. Get the next day. The next day is Tuesday. So we're going to take whatever the intrinsic representation is for Monday, which is the integral value 1, convert it to a 2. It doesn't overflow in the sense of going beyond 7, 6 actually. So it stays 2. 2 is Tuesday. And now notice that we're also using operator overloading here, in that the first expression that gets evaluated, let me rewrite that, it's C out. This is a binary expression. This expression has an O stream, and it has a days type. And we've overloaded operator bit shift to have a meaning for that. And the meaning for that is going to be D is Monday. So we're going to see in the stream MON printed. Then we're going to, this is going to return the same O stream. That O stream is the built-in standard out. So standard out gets returned, and now it gets combined with a tab character. So now a tab is printed on the screen, however many spaces your standard tab is, and then that's evaluated and again returns the O stream standard out, and then it's evaluated with respect to the days variable E, which in this case is Tuesday. And then again, we return the O stream, and then we put a new line in there so that we skip to the next line. Go to the next line. So we get a natural semantics for our new data type. And we've done it by overloading two operators that didn't have meaning for this. This is, again, critical to idiomatically understanding, even though this is a very simple type. So get it right on this simple type, and you'll be able to carry it over to a much more complex type. Anytime you need to do type extensibility, and this is a principle in object orientation, and one of the great powers of C++, that isn't in all languages, like Java, for example, doesn't have it, is also the ability to create new semantics for the operators in terms of however you've extended whatever type extension you've undertaken. Okay, what native operator is these double less than signs? That should be apparent from what we've just learned. Can the precedence of that operator be changed? If I have a new type, maybe I want a different precedence than the underlining type. How do we know what meaning of that first operator to apply? If we now have it overloaded for very different kinds of types and arguments, which one will we choose to apply? So think about that for a sec. Well, as we mentioned earlier, this is left bit shift. It remains left bit shift. We cannot change meanings in the C++ language. Where things are defined for the native type, they remain defined that way. So that can't be changed. It can't be overridden. So if we had as an argument an integer value shifted by 3, and if you thought of this as the binary number, that's the binary representation of 5, right? So that's 1, 0, 1, that's 4, nothing in the 2's position, in the 0's, in the 1's position, in the 0's position, there's 1, so that's really 5. Then we shifted over 3, and now we have 1, 0, 1 shifted 3 positions, within decimal would be 40. So that definition remains. Precedence and associativity also cannot be changed. So that you have to know. So if in your domain you're coming from something in electrical engineering or chemistry and you're using operators that have meaning to chemists or electrical engineers, and there was a different precedence or associativity for the operator than what is in the existing C++ language, that's something you may have to keep in mind. And then which definition gets used is based on the binary signature. So here a binary signature was int, shift, shift, int. But mostly you're going to see O stream, bit shift, some arbitrary type. And in the case where we have O stream, and where we've overloaded the O stream, the bit shift operator, with a type, then we will have the appropriate input or output behavior, in this case, of course, output. So for input, we're going to do the same thing with right bit shift. So the real insight for object-oriented languages is that they can be universal because you can add types that you can add efficiently. And so you no longer have to invent a special language, much like in the early days of programming languages where you went and you invented Fortran for science and COBOL for business and Lisp for artificial intelligence. Now within a language like a Java or like a C++ or a Python, where you allow natural type extensibility and you allow it efficiently, you get to have the experts in a particular domain do the type extension so that people now can conveniently and naturally program in that domain. And that domain could be anything. Chemists can invent a language and the set of types they need for chemical molecules. DNA people, bioinformatics people can do everything they need in relation to the genome. And so what we really want is to understand how, for your particular widget, for your particular domain, how we can create a widget type. What are the rules? What should be the natural way to build widgets? C, which you're coming from, has a form, but it's a primitive form of type extensibility. So you should already have a bit of experience here. And the experience will inform you in terms of, and let you compare to the more powerful aids that C++ gives you when you're doing type extension. So in C type extension, you typically created a new type by using the keyword struck. Struck changes in C++. That was the critical insight that Bjorn, as a program language designer, had. He said, I'll stay with struck, but I'm going to add things to what you can do with it. And those things are going to be, the critical thing is struck in C would let you have what are called data members. You could say, oh, I want a struck, and I want it to be two items like int AB, and maybe they would define something we would call a pair. And now in C++, I not only have that, but I have the ability to have functions that let me operate on pair. And those functions will be inside the scope. They will be scoped to the struct. In C++, because Bjorn started with struct, he wanted to retain C++ usage. He created as an alternative to struct class. So C++ has redundancy. You don't find that redundancy, for example, in Java. Java, you just have class. They were willing to start more from scratch. Bjorn wanted to keep all the old C stuff around for you, and he extended the meanings of struct, but he created class because class is what you should use when you really want full-scale objects. So, as a C programmer, this should be reviewed. If you had a C-type point as struct, so what we're going to try and create here is your typical point in the XY plane. Here's your XY plane, here's some point. off in the XY plane. We want to be able to manipulate that. Why would we want to manipulate that? Well, we might have geometry problems, or we might be doing some drawing. We might be using a drawing package, or we're the creator of the drawing package. So we have this struct. Struct has basically a struct name. That's in effect now the new type. And it has two data members. And now we want a method in C. This is all C, old C. So let's say we want to do what's natural. We have 2 points. We want to add them together. And the natural semantics for adding them together is the new x coordinate is the x coordinate of the old points, point 1 and point 2, added together, and the y coordinates added together. So if we had 7, 2 here, then adding them together, we would get 9, 7. That would be what plus would mean. We're doing this all in C. So notice it's sort of funky. There's no natural semantics to it. In C++, because we want an additive operation, go back to our ideas that we had when we overloaded days. We were able to give additional semantics to the operator. Again, this is why C++ is going to be better. We're going to be able to encapsulate point better. We're going to be able to give it a more natural look and feel. So the C struct has fields. The fields are only data members. In C struct, we have file scope functions that manipulate the struct, typically using pointer operations. This is the classic way, you might say, the primitive way we have type extension in the C community. So let's turn to C++ and see how much better we can create the new type point. First off, we're going to choose the new keyword class. Now we have point. We're no longer going to need that old trick, the old hack in C with type def. Point, the class name, is automatically the type name. The next thing you see that's different is there's an access keyword. That access keyword can be one of 3 keywords. The 3 keywords are listed here: public, private, protected. For the moment, we're going to leave out protected. It's part of what we call the inheritance scheme. And we're going to leave inheritance for another day. Public and private are what you really need to know for most of your programming. Again, this is one of those wonderful things, what I call 90% rules in programming. If you learn a few simple ideas, they work for 90% of what you need. So you should really concentrate on learning the basics, because that's widely applicable. And then the additional 10% you can learn as necessary. So public, and that's where protected comes in later on. Public just says everybody should visibly see what I'm declaring. So if I say public double XY, means everybody in the world gets to look at X and Y. Private is just the opposite. Private says restrict the access to things that have this class as its scope. Keep it just very limited. What I like to do is say private is part of what I call the black box principle. Hidden away in here is the private stuff. Now notice, if you buy an Apple and you try and open it up, let's say you buy an Apple iPhone, the warranty goes away. You try and open that and mess with it, the warranty goes away. It's a black box. The manufacturer only wants their specialists, their authorized specialists, to work with that black box. So what you get to see is a few controls on the surface. That's the functionality of the iPhone. Do you really care what operating system and what processor is running the iPhone? Most, 99% of the world, do not have a clue as to what the processor internal to the iPhone is, or even that there is a processor. They just know it as, oh, I have it as a phone, or I have it as a mapping device, or I have it as telling me Rotten Tomatoes movie reviews. So they know it as, here are some apps, here's some phone function, here's some camera function. How that all works internally, that's a mystery. Apple doesn't want you to mess with that. So that keeps it a lot simpler. So again, that's a really important principle in building things. Hide away as much as possible that the non-expert, the ordinary user, doesn't need to know, and just give them the public controls, the little knobs or whatever are on the face of the device. So here is class point, and class point is where we're trying to create a new user-defined object. And some of what we want to understand is how to use the OO technology, the object-oriented technology. What are some of its key elements? The overriding principle in the object-oriented technology is to make your new data object seem natural, seem compatible with the existing programming language data types such as int or float. And among the principles we try to follow are data hiding. So private is where we hide representation. In order for this not to impact efficiency, remember when a member function, or in OO speak, a member function is sometimes called a method, is automatically inline. So it's automatically highly efficient. And so this return of X really is just not involving a function call. It just really gets the internal value of the variable X associated with that instance of point. And then the set X, which is also called a mutator method, because it can change the value of the hidden representation, is also efficient. It's really just at that place in the code where you're going to call that member function setX, you just replace it by the simple assignment data object.x equals data object.v, or the v value, I should say, that's being called. So again, if you want to review object orientation, you're supposed to have a background object orientation coming into the class, but you can use something like the Wikipedia to review this information. And if you follow this template, namely use public for the kinds of behaviors you want your object to have, use private for representation. And then, as we will see, you make this as rich and natural a set of class functions that gives you an easy time in using point in your normal programming. So here we continue with the object-oriented paradigm and what we need to do and some of the things that C++ lets us do. And C++ is the most powerful object-oriented language. It's actually multi-paradigmatic language, but it allows, for example, operator overloading, which many other object-oriented languages, even C-based ones, don't allow. And again, that gives us the opportunity to extend the semantics of even operators over to our new objects so that there's a fairly natural understanding of how those new data types will interact with the old data types. There's an expectation that we will keep the interface. So here we have something called a point. A point, as you remember from high school math, is a mathematical object. And if you're doing some analytic geometry, you can add 2 points to turn them into a third point. And the way you add them in the XY plane is to take their X and Y values and combine them. Well, that's a natural operation. It's the operation binary plus. I have to say binary plus because C++ also allows for unary plus. Unary plus is normally a no-op, but binary plus, which on natural built-in native data types like int, we all know you add 3 plus 4 and you get 7. You add 1.2 and 2.2 and you get 3.3 in the float or double domain. So plus is a natural operation. You should only be overloading it. Idiomatically, you only want to overload operations where there is an existing semantics, which generally means they must be mathematical objects. You don't want to overload your general widget where somebody doesn't understand what a plus for 2 widgets are. I mean, what if you take a Swatch watch and you add it to a Apple iWatch? What does that mean? It's hard to conceive of. So you wouldn't want to be using overloading of operators in non-algebraic, non-mathematical domains. But here, plus has a perfectly good sense to it. And indeed, if I was somebody who was going to be dealing with points constantly in my programming, I would want the ability to use the arithmetic and mathematical notations, including those operators. So we see what the semantics are, and they're exactly what you can imagine from your high school math. Now, we also want to overload the output operator. And this is very important. So study this because this is a critical idiom. Anytime you have a new data type that you've created, a new object that you've created, you generally want to overload this. Again, it's an expectation. It's a community expectation. So if you're the designer of this new object and you're going to give it to other people on your team, they're going to expect the I/O to work on it. Well, you have to give that I/O semantics. And here's the semantics. We print a paren, we print out the X value of the point, we print a comma, we print out the Y value, we print out a closing paren. So exercising this on some point, we might see on the screen 3, 4. And that would be the point with the X coordinate 3 and 4 in the XY plane. Now, critical to this is to look at the function signature. So the return type is an O stream. So that means you're taking, and the operator overloading is a binary operator, and it's a binary bit shift operator. So even though it's natural for us in C++ to always think of this as an I/O operation, it isn't intrinsically. Intrinsically, if we have 2 data types like 2 ints, we're forced to use it as a bit shift operator. However, where we have an O stream as a first argument, as here we do, and in this case we have the object as a second argument, then this function signature makes us select this version. Don't forget, this is a form of operator overloading. And the signature matching algorithm that the compiler uses says, do I have an available definition for this? If I don't have an available definition and I attempt to do something like this, I'm going to get a compiler error. But if I have an appropriate available definition, which is use it on a stream, an O stream, and then apply it to a point, then this is the behavior we're going to see. Now, critical is that the O streams are both passed in by reference, and the return value is an O stream by reference. Why? That suppresses any kind of copying, so that's efficient. And we want to return this operator because we want, in typical I/O, to use this multiply. You see it here. It's really a binary operation, and the binary operation goes something like this. Out is the stream, and then you print, the action is to print left paren. And the result is really that you get this again as out. See, you get the same O stream as out, but you've had this print behavior. So you're going to print first this, then you're going to get an O stream, then you're going to print 3, then you're going to get an O stream, then you're going to print comma, and so on. So those semantics are call by reference. But look at this. This doesn't have to be written this way, but it's expected to be written this way. Sometimes for simple types, this could be call by value. You would see the same behavior. However, it's just useful to call your data object, because your data object, your newly created object, might be something very complicated. And again, you want it efficiently passed, and you know it's not going to be mutated. So the const shows that it's not mutated. And passing by reference suppresses call by value semantics, so it doesn't get copied locally, which could be an expensive operation. And then you just print the underlying value. Again, this is a very important idiom to understand. It's most useful. Once you understand it, you can apply it to any of your own programming. Anytime you create a new class, you want to be able to design a program like that. And remember, you return out because of the binary operator. You want to reuse it in a stream like this, a stream of operations like this. Then its use in main, just to test this, and again, if you're working at home, you should try this out. You should add operators. You should think about it. You should run your own version of it. You should extend it. It's the only way you're going to really get to make use of this. We declared a point, 3525. We declared another point, 2545. We output those 2 points. So what's this going to look like on the screen? Well, hopefully, if I have what I did before right, we're going to see 3.5, 2.5, all in parentheses with this comma there. And then we're going to, we're going to have A equals. That's this expression. And then we're going to have B equals. And then the same thing. We're going to see parentheses 2.5, 4.5. That's what's going to hopefully show up on the screen, and then we'll have the new line. And then if we do the sum is going to, in effect, deal with all these operations properly. You could have parenthesized that, but because of operator precedence, this will take precedence and occur before the left shift operator. So this is plus has higher precedence than shift. and you will get a plus b. A plus b is going to end up with 6.0, 7.0, and that will be sum. Hopefully, that'll be your result. You should try that at home. So, what have we learned? User-defined types. Using point and main looks very much like a native type. It looks like we used double. It looks like we used int. It looks like we used char. This is your key goal in object orientation. To be a good object-oriented programmer, when you've created a type and when somebody understands the intuitive semantics of that type should readily look like an ordinary C type, an ordinary C native type. And we accomplish this by having point have properly overloaded semantics that gives them an appropriate look and feel like a native type. Now, when we stick methods in the class, those methods are frequently going to be accessor methods, and sometimes they're going to be what are called mutator methods. As a senior professor, I'm allowed 1 or 2 errors a lecture. So that shouldn't have been val, that should have been v, or alternatively, this should have been val over here. This is what we call a mutator method, because it changes the underlying value of what a point is. And this is purely an accessor method because it gets us the value. And class members, this is the critical thing. When we're building a class, we have access to everything. We have access to private, we have access to public. Everybody has access to public. But we have access to private, or when we go over to inheritance, we'll also have access to protected as well. And the way we get access is through this dot notation. P1 will have its 2 doubles, x and y, defined. So P1 dot x and dot y are available to get x. That's why when P1 activates getX, when this method getX is activated by the object P1, it returns the hidden value for that particular object instance. So what lessons do we want to take when we go to build an object? Object construction is needed for OO. Built-in objects such as the native objects, double, fixed arrays, they're all built by the compiler. But a big part of C++ mastery is to get the skills so that you can write the code, you can write the class, you can write the class methods, the member functions that have you build the object. Crucial to building the object is a very special method. That method is called, it's given a special name, it's called a constructor. Rather intuitive, constructor, construction. So when you want to build an object, you need something that builds it. The compiler knows how to build native objects. The compiler needs instructions, and what you intend to do when you're building these new objects, the objects, the domains, the widgets that you are going to use, you're extending the language use into new areas. So here's point. The key idea is that only constructors have as their names the same names as the class name. All the other methods have to have different names like getX and setX. But when you see inside a class what looks to be a function and its name is the class name, then you automatically know it to be a constructor. And the constructor also has the ability to take different argument lists. And when there are several special types of constructors, and we'll go into that in a second. But the standard special constructor is called the default constructor, and it's the default constructor because it's how to build the object when you give it no arguments. So here is a constructor where you give it no arguments. And when you build it, you say, oh, a point in which I give it no arguments. Well, that's just going to be the point that's in the XY plane at the intersection of the two axes. That's going to be the special point, 0, 0. And that's intuitive. That might be what would be expected. Normally, when you have native types and you leave them uninitialized, the compiler frequently initializes them for you to zeros. And this is a sense of using some standard null value for the initialization. But here you have to give proper semantics, otherwise X and Y, the secret parts of the instance, the secret data members for the instance, wouldn't necessarily have an initialization. Now I'm showing you how to do this, the semantics, in two different ways for the moment. The second way involves the special keyword this. This is what we call the self-referential pointer. One of the things that's always something that's wonderfully confusing in mathematical logic, or indeed in computer science, is where we get self-referentiality. Famous logical puzzles about villages in which every man is bearded and only the barber is allowed to shave men's beards, and the barber is bearded, and you have to ask the question, who shaves the barber? So is that in a logical or impossible situation? Anytime you get self-referential, wonderful series I've been watching forever is the British science fiction series Doctor Who. And Doctor Who, as a pun, plays on the whole question of self-referentiality. Doctor Who. And indeed, in Doctor Who, he's a Time Lord, and he's floating around in the cosmos. He frequently comes upon himself in certain special episodes. So you get all sorts of paradoxical self-referential situations. So again, self-referentiality, that's difficult. In order for a member function method to access its own members, it needs some special mechanism. So either X and Y are known to be inside that class, or they can be pointed at self-referentially through this special this pointer that always exists for any object created. And we'll make use of it, and we'll see why it's important. Okay, that was a taste of constructors. There's also an analogous special method called a destructor for destroying an object. So anytime we want to be able to create things, we want to be able to destroy them. We want to be able to return resources to the operating system. It's very important to keep our environment clean, manage our environment carefully. It's a major topic for those of you following in the text. It's very important to read Chapter 5, and I will continue next time with this material. Today we're going to get deeper into the object-oriented programming style. So we're going to look at more C++ classes and how to build them in an object-oriented manner. We're going to look again at constructors and destructors, which are these critical methods that both build and deallocate the new extended data types. And then we're going to discuss our next significant homework assignment, and that's a homework assignment based on graph theory. So again, all of you came in having a background in computer science, roughly at sophomore year level at least, and you may well have already seen standard graph theory algorithms, so this may be familiar to you. In any case, I will review all that material, so even if you have forgotten it or haven't in the past had an adequate background, we're going to really understand Dijkstra's shortest path algorithm, and that's going to be the basis for our second homework assignment. Okay, objects. Objects could be anything. So here in this little example, we're thinking of shapes. Shapes could be boxes, polygons, text shapes. There can be operations like delete on them, operations that involve counting the shapes. And so if we wanted to build a windowing environment, what would be our set of widgets? What would be the operations? What would the user expect, the user of this package of routines? How would we properly design things and keep the internal details hidden away? All of that is what you have to think about when you're an object-oriented C++ programmer. Again, a best guideline to doing this thought process is to know what happens in the language for native types. So with native types, we have to fully understand what happens when we declare something, even a simple object like an int. What does it mean to say int I, j, initialized to 3? Well, we typically do that inside block scope. Block may be inside the main function, or it may be in one of the auxiliary file scope functions. So we're declaring here, we're allocating, we're initializing. Now, for a simple native type, all this happens automatically on the stack. We have to replicate that for our user-defined types for our objects. And again, as we started with last time, we saw we had a special method for doing this called a constructor. All right, so just for review purposes, in the C language or in basic C++, what is supposed to happen here where we have nested blocks? So here's a main. We have two declarations. I is initialized to 9, j is initialized to 3. We're going to print what goes to screen, so that's what we're expecting you to do. This is going to be very similar to the kinds of exams I give. This is a question that I could readily put on our final exam. And then secondarily, we have an internal block. It's not, here's the internal block, the nested internal block. I actually would have preferred an indenting style. This is not, you should reformat that if you're going to try the code so that the internal block is indented so that you can visually, that's again a convention, but it makes it more readable. You can visually see the inner block. And so in the inner block, there's a redeclaration of int I. And we're asking what that prints versus at the outer block. And the answer is the inner block, the outer block has 9 and 3, but the inner block has what you might call I inner, which was recalculated to be 5, and j was left. J just got passed in because there was no inner block J. So that's really J outer. And then over here, we have outer again. And when we go to the outer block and we print it, we see it, value 9 was retained. So that should all be in your knowledge base already. From an allocation point of view, I and J are placed on the stack. Inner block, I inner is on the stack. I outer is hidden. Then we have block exit. I inner is destroyed. And then we return to the outer block, and we have again I9 and J3, which are the outer block variables that are still on the stack. So let's return to our object point, and let's again look at its constructor logic, and we're going to see how to write that default constructor. So here's point, and critical to building new objects in the object-oriented world is to write special methods called constructor methods. And always important in constructor methods is the default constructor. And the default constructor is a constructor whose signature is empty. Now notice, the constructor always has the class name. That's how you determine that this is a constructor. And here's the empty signature. Now notice in here, it looks like I have two arguments, x and y, which I do. But that actually, both arguments have default values. So this signature by itself covers a lot of ground. It's a very useful, what you might call, abbreviation, because what it's covering is a signature in which you could replace, you could use point with no arguments, point with one argument, and point with two arguments. In the no argument case, the point that was created, so if we had declared something like point R, no arguments, R is going to be created with internal representation x equals 0 and y equals 0. In this case, if we had a point Q, with one argument, it would invoke this constructor, and that would mean that you would have the data value 1.1, 0.0. And then if you had the two argument case, you would have the data point 1.1, 2.2. Now we're going to see, and we're going to talk a lot more about constructors, that there are other very important constructors. And almost always when you build a new object, you have to use the default constructor, but you also have to build something like a copy constructor, and you frequently have one argument constructors, which can also be used for conversion possibilities. You might even call them conversion constructors. All of those are very critical and should always be thought about when you create a new object like a point. Now, the other thing critical to this that you might not have seen before is the use of initializer list syntax. Notice that the actual semantics of this constructor, as found in the code body, they're empty. It looks like nothing gets executed, but that's not true because this initialization happens. So instead of it being assignments inside of here, and you could make these assignments, and we'll show that later in a later lecture in this segment, that you will be able to use the self-referential pointer this. You'll be able to say something like this, arrow x equals x. But you can't always do that, and you can't always do that because there are special cases where, for example, the hidden representation is not mutable. It could be a const value, and you can't assign to a const value. So you couldn't use semantics that were in here with assignment. Instead, you must use initialization semantics. So it's very important to understand where initialization semantics are preferable and where they must be used. We'll go on to talk more about this. Again, remember that this pointer is self-referential. We talked about that already. There's a keyword, this, that has that as a special meaning. And again, we'll see all of that in the next slide. We now have three different constructors for point. Two of them, all three can be used to define the default constructor, but the last one is the best use of C++. So here we're just using ordinary assignment. Here we're using this pointer so that this pointer is grabbing the member and the member is getting assigned. Here we're using initializer list. And initializer list means that these values are initializations. Because they're initializations and not assignments, and here there were assignments, it turns out that we have a far larger range of things we can do with this last and best way to do it. So this is my preferred. If, for example, we had a widget in which one of our hidden members that we needed to initialize was a const. So we had a const int special, let's call it. And that was hidden away in private. It would have been illegal to use the constructor style of 1 or 2 because that involves assignment. Assignment means we're mutating the values stored in this item. But this is initialization. Initialization, much like with the native types, if we have a const int special and we assign it 5, that means it's going to be 5 throughout the range of that declaration, throughout the scope of that declaration. We're telling the compiler it can't be modified. Called const correctness. That's a very good thing to do. That helps us and prevents us from writing buggy code. So the same thing is going to be true with an object. Remember, everything in the native language we want to replicate in building objects. And we may also want to have the ability to have members that are const. And members that are const means that we have to have the ability to initialize them. So, as I say, initialization is preferable to assignment. And only in the constructors, are you allowed this initializing syntax, which makes sense because that's the constructor's job. The constructor is to build the object and initialize it. Anytime we were to call P, Q, and R as a point, all would call the constructor a void signature. Now, of course, you'd have to write that default constructor, the all called the default constructor, and you would only choose one of those. You can't write all three because you'd have an ambiguity. And they would call the constructor with the void signature. Now, just because you have a void constructor doesn't give you all your opportunities. It's also useful to have multiple ways to initialize objects, multiple ways. Let's look at initializing point with this signature. This says I have two doubles in my argument list, and the argument name is going to be X, so the arg name is X. But X is going to be assigned to the member. So this is the X, that's the argument, and this is the X, that's the member, used to disambiguate. Otherwise, I could have said point, double, XYZ, comma, and then I wouldn't need this disambiguation. I would say XYZ is equal to X because I would know that that's the only thing in the range of the method. That X would then have to be the self-referential X. But once I have an argument, that argument name takes precedence over the self-referential name. And the way you disambiguate it is through the use of pointer notation and the this pointer. So that's very important to keep in mind. Sometimes the use of the this pointer is unavoidable. So summarizing, the this pointer lets ambiguity be resolved because X equals X wouldn't work. It would just be assign X to the argument X, and nothing would happen to the self-referential object, the X part of the object. But even better would be to use initializing syntax. And the reason why that's better is we don't have the same ambiguity problem. This X and that X are clear. In the initializing syntax, this has to be a member. And this has to be some expression, which can be the argument. So this provides for the disambiguation automatically. And we don't have to, we can avoid the use of this. They're semantically equivalent. Constructors are very important. They have several functions. They initialize. We've been talking about initialization. They allocate, especially when we get to very complex widgets that require going to the heap and getting memory. We'll see that there will be the use of new in those more complicated widgets. They also convert. So constructors of a single argument give you a prescription for what basically a static cast. So if I have a prescription from an int type to a point, it lets me take an integer value and convert it to a point or a double value. So anytime I have a signature of a single argument that's a different type from the object being constructed, I'm also providing, in C++ terms, a conversion operation. Also, the other thing we can find that good programmers will do is when they have constructors, especially when they're debugging, because they may want to avoid this for efficiency purposes, they can put in checks for correctness. By that I mean the constructors can make sure that when they initialize state, when they give values to members, that those values represent legal values in the range that they want. So if you're thinking of an experiment in which you are working with liquid water and you need to initialize its temperature, well, we know in Fahrenheit that liquid water is between 32 degrees and 212 degrees. Below it freezes, above it boils. So if we were to assign a temperature to the liquid water widget and it was somehow out of that range, we know we've given it an illegal initialization. So there's also the possibilities in object-oriented programming using constructors to test consistency, coherence, the fact that legal values were provided in the initialization. Now, you're coming from the C community. In the C community, when you wanted to manage the heap, again, hopefully this is review for you, you use malloc, sometimes calloc. Malloc was a memory allocator found in the C standard library. And when you allocated from malloc, you got a certain number of bytes off the heap. The operating system provided you the bytes. Why did you do that? Well, you may have needed something dynamically in the computation. The typical reason to use calloc or malloc was, I don't know how much data I'm going to process. I have a very large file. The first entry to the file tells me how much data is sitting in the file. So it tells me I need to process 400,000 Social Security numbers. Now I need something that can store 400,000 Social Security numbers. Well, that means I need a very large array. So dynamically, during the computation, by calling malloc or calloc, I can access the heap, assign to a pointer, which we can think of as a base pointer, that much memory, and then use the dynamically allocated object. And then good programmers don't allow for memory leaks. And so when I no longer need that memory, I would deallocate it. And the standard way I deallocate in C is to use free. Free and malloc and calloc are replaced, unless you're using much older style stuff, which you would have a special reason for, with the keywords new and delete. And the keywords new and delete provide memory management operators, heap management built into the C++ system. Now, this heap is dynamically allocated memory, but unlike Java, is not garbage collected automatically. So you have to be very careful, more sophisticated than you would be in other languages where memory management involves automatic garbage collection. What's the upside to it? The downside's obvious. You can get memory leaks and you have to do more complicated coding. The upside is you can be more efficient. So here's some simple uses of going to the heap. We basically have two critical forms of the use of new and the symmetrical use of delete. One is to get an array of items, which is going to be very often the case. So if we look at this, we have a pointer type. Its base pointer is char star, pointer to char, and I want some dynamically assigned value, size, might be gotten from some other part of the computation. So maybe I have a text that has 1,000,000 characters in it. I need to process 1,000,000 characters. Size's value is 1,000,000. New is going to go to the heap, give me an address. That address is going to be the base address for the 1,000,000 characters, assigning to S. If I only want a single element of that type initialized, then I can do it with new event, and then in this case, 9 would be the value stored. So this is one item, this is many items. And then if I deallocate an array corresponding to the two things up there, I need the special notation brackets for deallocating an array, and I don't have brackets when it's a single element. Fairly simple, but something to keep in mind. You have to make sure that you use these two items consistently. Now, we've talked a lot about constructors. Why? Almost any kind of widget has some kind of construction that it needs. It needs, at a minimum, initialization. However, destruction is much more trivial. Typically, destruction has nothing to do with uninitialization. It has to do with retrieving largely memory for the object. The memory for the object might have been automatically allocated on the stack, in which case we may not have an automatic, we may not need to write our own destructor. But anytime we're using new, we will immediately think about wanting a destructor. Anytime we use resources, system-limited resources such as heap memory, we would want to call a destructor. And the destructor has special syntax as well. And the critical part of the special syntax is the tilde. So if we had a deallocation for point, it would be tilde point. And we can't overload the signature as we can. We can't have we can have multiple constructors, but we can't have multiple destructors. Destructors don't get called with arguments. So the destructor always has the empty or void argument list. And then you have your semantics. And very typically, that's going to involve some form of delete. What if you forget destructors? A lot of people forget destructors. When I was first doing C++, and this is now in the 1980s, there was a colleague from another university who came around and gave a talk on his research. And he had also decided to use C++. He had previously been using C, and he liked all the new stuff. So he had this very complicated set of routines. And he was dynamically allocating lots of memory throughout. And I was still a relative novice, and I was worrying about memory leaks. So I asked him, well, what do you do about writing your destructors and making sure everything's working properly? And he said, oh, I never worry about the destructors. I don't write them. But that's okay if you don't worry about memory leaks. Remember, memory leaks generally won't show up in your program malfunctioning. The memory typically gets reallocated by the operating system when your process ends. And most of these systems have that built in, like a Unix system. However, if you're using large amounts of memory and you're frequently going to the operating system, it can easily slow down what you're doing. So you really want to, if you're a high-quality C++ programmer, get into the habit of properly writing your destructors. That's just a very important and useful skill. So let's see a widget in which memory allocation is important. It wasn't important in the way we define point, but here's a classical data structure. We see in this slide the section in the text. So if you want to reference the text, go and look for a single list element in the text. It's on page 168. And certainly you've all had in your background some programming of a single linked list. So recall, in the case of a single linked list, we typically have a header pointer. We typically draw it. It's like a little train of boxes with arrows, and then it would end with something we also call a null pointer. So this would be canonically, if you've studied computer science, one of your classic expandable data structures, dynamic data structures. And there's a single linked list. You'll find that there are, of course, other things. If you wanted, you could also have a doubly linked list that has other navigational possibilities. We'll see that when we take up the topic of the standard template library, that list in the standard template library is indeed a doubly linked list. So, constructor. Here's the default constructor. The default constructor has the head point at 0, so that's in effect the empty list. There's no little boxcars to point at. 0 is the null pointer. Now, if we start building a list, it'll turn out that we want to call the destructor to return or delete the boxcars. So delete is going to call a special method. You might call it an auxiliary method, and that auxiliary method is going to race through the structure. And as it races through the structure, it's going to return each element back to the heap. Okay. So conceptually, hopefully, you've seen this kind of notation and you've done this kind of coding previously. So here's a standard list structure operation for a singly linked list. It's called prepend. What prepend does is it puts an element on the front of the list. On the front of the list. The underlying element here is going to be a character, and we start by building a new S-list element, so that comes off the heap. When we use new, when we use the operation new, largely this will work, but if for some reason there is exhaustion, we will get an exception thrown. In modern C++11, that exception is going to be a standard exception, bad allocation, and that's going to, unless it's handled, cause an abort. So you can either handle it or cause an abort. And then typically that's quite safe. Now here, to do the prepend, we have to create a new header, update the header by adding the new character into the data position in the new list, and then we update the head. So if we had a list head that conceptually pointed at something where we had stored the character, let's say, lowercase a. And then this was the null list, null pointer. So we'd have a single element list. And now we want to insert or prepend the character B. We would end up with H pointing at a new element, a new S-list element in which the object, the data being stored is the character B. And then this was pointing to what was in effect the older S-list, and that had A in it. So that's prepend. And if my little boxes that I drew worked right, prepend would work right. I think I've tested this. You can test it and see that it indeed works. And now let's look at the destructor. Okay, we have our special way of naming a destructor. It uses tilde, only used in destructors. Otherwise, we use the class name. And we're assuming this is written in the file. So it's not inside the scope of the class, so that's why it's using scope resolution. And just for purposes of playing around with the stuff and seeing how it works, I'm going to use this during debuggings so I know when the destructor is called. So this is very useful if you're having trouble having a good intuition about how this happens. It's very worth writing that out so you can see dynamically when you run the program when the destructor will be invoked. This will get printed to your screen, and you can try and figure out when this will be invoked. And then there's this auxiliary function, which I haven't shown you how to write yet, which should march through the list performing deletions. So part of what the course is going to give you expertise in is algorithmic graph theory, because it's a very, very good subject, because graphs themselves are widgets, complicated widgets that have very different representations and many ways to try and implement and get efficient for particular different instances. And so we can see a lot of the OO ideas and a lot of the uses of C++ effectively when we try to implement these algorithms in C++. But also it gives you some background in doing further and more complicated programs as this course and its sequel progresses. And one of the classic algorithms in computational graph theory was invented by the very famous Dutch mathematician, computer scientist, Edward Dijkstra. So we're going to see how to use Dijkstra's algorithm, and your homework is going to be to implement Dijkstra's algorithm and use it on a randomly generated graph, which you'll also have to implement. We'll also show you how to do a very similar but simpler problem based on an algorithm that I invented many, many years ago. Originally, I implemented it in a much earlier programming language called PL1. And it's the problem of finding out whether a graph is a simple one-connected component graph. And we're also going to have some drawing lessons. We're going to be drawing graphs as we go through and simulate these algorithms. So this is the set of ideas we're going to need to do the remaining homework in this class. So here's an unconnected graph, and that unconnected graph is a graph of 7 nodes. We might label these nodes 0, 1, 2, 3, 4, 5, 6. That would be traditional C labeling, namely we start from 0. We might label these nodes A, B, C, D. You'll see all these labelings in the graph literature. Or you might see them as nodes on a graph. Maybe this is San Francisco. And this is Los Angeles. All of these are possible. It's unconnected because we can't go from any node to any other node. We don't see any path in this unconnected graph between San Francisco and Los Angeles. We just see nodes. Now, here's what we're going to show as a connected graph. So I have left the same labeling. And now I'm going to add what are called edges. So these blue lines are what we call as edges. The little circles are nodes, the little blue lines are edges. When you think of edges, think of roads. So here's a road from San Francisco going to Los Angeles. For us who are Californians, that might be 101. Here's another road from San Francisco to D. Maybe D is San Jose. Maybe this is San Diego. So again, you have familiarity in the ordinary world with graphs. They're basically just road maps. And they're road maps in which the cities are nodes and the highways are edges. Now, I'll draw a few more edges. If you looked at this connected graph, the reason it's connected is I can find a path between any two of the cities, any two of these nodes, or another term for nodes is vertices. So if I want a path from San Francisco to San Diego, I'll use this little wiggly line and show you here. Oh, there's a path. So that whole graph is connected and indeed a single component. Now, how can I get a computer to draw a graph? Drawing a graph by computer is actually fairly efficient. And the critical thing will be to generate, using a representation for the graph, an internal representation, a number of vertices. So we'll have to decide on the size of the graph, and then we'll have to decide what edges will be placed in the graph. And this particular algorithm I'm going to show you that'll generate a randomly generated graph will use the heap and create a two-dimensional representation of the graph. So let's see what that means. The overall graph is going to be a pointer that ultimately stores Boolean values. What are Boolean values? They're the values true or false. If I have a graph that has edges, let's say they were like what we just saw, 0 to 6, and I have true in one of the matrix entries. So let's say in element 3, 4, I've stored true. This is going to mean that the edge from vertex 3 to 4 exists. That's what's being created by this little routine. The way it's created is I seed the random number generator. I hope this is all review, otherwise you'll have to review how a pseudo-random number generator works. I create a graph, in this case, of the appropriate size. It's a graph that has 7 nodes. And then for each node, I have to have a row, a Boolean row. So these are the rows. That's what's being created here. And then these are all capable of storing a Boolean value. So the heap has allocated off the heap through this for loop. I've created a 2-dimensional array whose base pointer is graph. And now I put edges in, and I'm going to put edges in according to a density. What do I mean by a density? Density is the probability an edge exists so that can be 0 or it can be up to 1. That's what the density, the range of densities there are. 0 would mean that I'm never going to put, if this had been 0, no probability would be greater than 0, less than 0. And so I'd never put in an edge. This is the act of putting an edge in. 0 would lead to no edges. 1 would lead to every edge. The term here is complete. A graph that has all its edges, all its possible edges, is called complete. So we have a for loop. The for loop marches through the 2-dimensional graph. If I equals j, that means if it's on the diagonal, we automatically put in false. Otherwise, and this is symmetric, this turns out to be the undirected graph. If the probability, in our case, we're looking at a density of 0.19, so roughly 1 in 5 times I'm going to stick an edge in. And probability is just some function I'm computing using the random number generator. You may have to review that, or you may have to look at the code that's online for the probability function. That will generate a randomly generated graph of the given density. So here's a few questions. Density is 0, the graph has no what? Density is 1, the graph is what? The C word. If density is fixed, say, to some size, and the graph gets larger, what can we say about it? How likely it is to be connected? Take a second to look at that. Okay, as we just said already, 0 means the calculation says no chance. You're never going to stick an edge in. 1 means you're always going to stick an edge in, so it's going to be a complete graph. And now if the density is 0.1 and we have a size that grows, so let's say we have 5 nodes, density is 1. 0.1, I should say, 0.1. That means 1/10 of the time in a 5-node graph, we're going to stick an edge. Well, that's not going to happen often. 5 nodes, that means, roughly speaking, we're going to throw in an edge 50% of the time for that particular node. Well, that's not going to be connected, so it's very unlikely. Let's say we go to 50,000 node graph whose density is 0.1. So if you're following me, the 50,000 node graph, and we have lots of 50,000 node graphs in the real world. Just think of the map of all the cities in the United States. And if you're thinking about the map of all the cities in the United States, how many roads are there out of an individual city? Maybe there's 20 roads out of an individual city. That might even be a big city. So a density of 0.1 in a big map is not all that. This would mean 0.1 would mean that on average, we're going to get 5,000 edges per node. Here it was on average 1/2 edge per node. 1/2 edge per node for a small graph is going to leave us unconnected. 5,000 edges out of a 50,000 node graph is going to leave us with a humongous number of paths in that graph, and it's very likely, almost certainly, with probability approaching 1, going to be connected. So if you have a good intuition about what we've been talking about with these randomly generated graphs, and this is going to come up in the homework I'm assigning you, as the graphs get larger, namely the number of vertices, the number of nodes in the graphs get larger, having a particular density makes it more and more likely that there are paths between all the nodes. Okay, so while I'm assigning you a homework problem that's Dijkstra's shortest path algorithm, I'm going to show you some processing of handling the is-connected problem. They're related. To some extent, you could, in fact, use Dijkstra's shortest path algorithm in one form to find whether a graph is connected or not. But the simpler one should give you ideas about how to do the Dijkstra algorithm. And this goes back to my own work back in 1968 when I was a graduate student research assistant at the Stanford Linear Accelerator Center, and I was being asked to use this very new programming language called PL1, which is more or less out of favor now, but still available. And the interesting thing about PL1 was it was an attempt to get a universal programming language. PL1 was supposed to be IBM's ability to having to do away with special purpose languages, and IBM was finding that it wanted to be a hardware company, not a software company. It wanted to sell big machines, which generally filled up lots of space and cost lots of money. And software was an irritating expense. And so the fact that they had to provide machine language compilers, macro preprocessors, COBOL compilers, Fortran compilers, sometimes ALGOL compilers, that was just a lot of different software they were supporting. And they just felt, well, why can't we get a universal language? And that will simplify our task. And they tried. And the way they tried was, unfortunately, what I call the kitchen sink approach. So they took everything they had in all these different languages, threw them all together. There was a lot of redundancy in this language. You could do things in a COBOL manner or a Fortran manner. There wasn't an obvious PL1 manner to do things. And that's in a way why PL1 didn't survive the object-oriented revolution. Object orientation allows you to have a much simpler idea of what a kernel language is, in our case C, and then expand it by letting the programmer add classes whenever they needed yet a new domain, a new set of widgets to work with. Now, the algorithm I'm going to describe goes back to work that I did and was documented in some reports at SLAC. But later, it was generalized in a very important way by Tarjan and Hopcroft, and is a foundational algorithm called breadth-first search. and you can certainly read about that. So this is also a vital algorithm that you should be familiar with. Breadth first search, and can find it in the Wikipedia. And what we're going to do in trying to find out whether a graph is connected is we're going to start arbitrarily with some node. And since everything in C starts at 0, and we'll probably use a labeling system that says we'll have node 0 up to node n-1 or up to node size -1. We will assume that node 0, think of our map before, San Francisco. If I'm sitting in San Francisco, I've reached San Francisco. So San Francisco is automatically connected to San Francisco. So we're going to have this initial set, and in that initial set, we'll put the node 0. Then we will look from San Francisco and see where are the adjacent cities we can reach. And this will be what I would call a closed set. And in what I'm going to call an open set, I'm going to put nodes reachable from San Francisco. So if I could reach node 3 and node 7, those will be nodes in the open set. Now, what if there was no way out of San Francisco? Maybe there's been a huge earthquake and all roads have been busted. What does that mean? It means the graph is disconnected. I can't get from San Francisco to San Diego. So I could stop. So if I have a closed set automatically with the starting node, and if there's no edges out, well, then the algorithm would stop and report that the graph is not connected. However, if there are ways to get out of San Francisco, namely I can go to Los Angeles or San Jose, as was in that early map I showed you, those nodes with their names would go into the open set. And then each time I would go to the open set and pick off a next node. Maybe in my algorithm, I'd pick the node with the lowest number, take that node and drag it over, place it in the closed set, and look again for what places I can go from node 3. And maybe I could go to node 4 and node 2, and they would become new entries in the open set. So the open set would contain nodes that can be reached from what was put in the closed set, with the proviso that I don't need to go back to something in the closed set. If there's another way to get back to San Francisco, that's not of interest. So the open set will only have nodes that are not in the closed set. The calculation will stop when one of two things happen. Either, and this is, I'm not talking about German there further, either I can't reach all the nodes, in which case the open set is exhausted, the closed set has yet to contain size and nodes, all the nodes on the map. So I'm not connected. Or all the nodes, the set of nodes that are now in the closed set are, in fact, there are a size of them. And then we can stop, and the graph is connected. So that's our algorithm. That's what we're going to implement. We go back and we have our matrix representation of the graph. We have it as a Boolean matrix representation. We have the size of the graph. And we're going to keep track of close and open. And here is where open of 0 is true. That's like saying San Francisco is originally in the open set, and it'll be the first, since it'll be the only thing in the open set, it'll get automatically selected, placed in the closed set. So at this point, the open set has node 0 on it. It could work if any other node is placed in it. There's nothing special about 0 to determine whether the graph is connected or not. Nothing is yet in the closed set, and each iteration will add one node to the closed set and possibly many nodes to the open set, or maybe not. The open set doesn't get added to. We're still going to the open set each time as long as there are entries in the open set, and we have yet not worked out whether the graph is connected. So add to close. While I'm keeping track of C size, it's the size of the closed set. The old size is the C size. We then place something in the closed set, meaning one element is placed in the closed set, so we auto increment it. The closed set has that element being true. And then we go and look for things in the open set. We got to put into the open set anything that's already in the open set that stays in the open set, or anything that's newly reachable. Recall, this is just our note. This is true if an edge ij in the graph, and this is just logical OR. So this is the logical OR operation. So open is true if open is already true, or there is now a new edge that previously couldn't reach J but now reaches J. We are done if we have all the nodes in the closed set, or if no nodes are available in the open set. If all the here connected, we're connected. Here we're unconnected. And these are our termination cases. And keep in mind, how many iterations are we going to do? We're going to do no more iterations than size. Because in size, we either get a new node or we fail. And if we fail before then, we failed before size. And if we keep getting a new node, we get everything up to San Diego, and we're finished. So we only have to do this the size of the graph. So a fairly straightforward algorithm. Okay, so I'm going to explain a lot more about Dijkstra's algorithm, how to implement it, how to do your homework, and that'll be in our next lecture. Well, welcome. Today's lesson is about complex aggregates. We're going to focus on a list type. Of course, that's a very standard data structure. It's what we sometimes call a self-referential data structure, and that a list is the head of a list followed by a list. So you use list in its own definition. And it's a more interesting aggregate because in some sense it's an unbounded aggregate. You keep adding elements, so you need to be able to access memory. This kind of memory is heap memory as opposed to stacked memory for ordinary variables. So studying this has several benefits. First off, the list data structure that we'll see today, which is a single pointer list, is in the standard template library. So it's not like we need to create it ourselves, but in order to understand what goes on in building these more complicated library-based aggregates and how they can be used and what's efficient about them, it'll be useful to do a simpler version ourselves. This will let us, if we need to, create variations for ourselves, because not everything is in the standard template library. The second thing we're going to see is more complicated constructors. Constructors, again, that use the heap to allocate, and then, because it's very important to properly manage these resources, not have memory leaks, we'll also learn how to properly deallocate and return resources, namely use destructors. So this is a very, very central and important lesson, and it'll pervade more of the advanced topics that we're going to do with the rest of the course. So on this slide, we can see, I actually show it both in, let's say, the use of struct in more of an old style, where, again, struct is the aggregate type developed in C. And then, of course, Bjorn Strustrup, when he reinvented the language or extended the C language, initially called it C with classes, and then the more clever term C++. So struct morphed into class. Again, this is review. Struct just means everything is by default public. So here we don't have a keyword public. It's just implicit up here. But of course, nowadays, this is what we prefer. We tend not to use struct unless it's a very simple, plain old data type, as in C, then we might use struct. So here we have a public, we have a base simple constructor. We see it has two defaults. It has an integer n, which is going to be, if we think about this, what we're going to ultimately have as a struct element is something in which we're going to store data. In this case, it's just going to be an int, could be 3. By default, we're going to store a 0 there. And we're going to also have a pointer, which conceptually is something like this, a memory address. And by default, it's going to be a value z. Or in modern C++, if you have a C++11, you could as well call this the null pointer. We'll see that as well. We're going to try and transition you in this class to the use of the most modern C++ constructs as well. So we have data and we have a next pointer, and those are the two fields that get initialized. And this constructor, with its defaults, of course, allows us to have a number of signatures. In fact, since it defaults, it would also be the empty signature, so it could be used as the default constructor. I'll take a second, and in the previous list constructor, the list element constructor, what is 0 used for? Okay, take a second to think about that. As we pointed out already, the answer is, and this is a very important answer, answer, the pointer is a 0 value, which is the null pointer value. And here, as I stated, the newer practice is to use the keyword NULL-PTR, null pointer. And the reason for that is its improvement over an ordinary 0. The 0 is really an integer value. It can be cast, but it's really a 0 as historically a integer. So to use it as a base type for other things is basically to work with conversions. Also, just to keep in mind, there is a macro called null, so that's also conventionally seen. And this is an improvement over both older practices. Let's more generally look at the list, which makes use of the specific list element. What we want to think about in the list, and again, lists, really important to think pictorially. So for a list, you tend to have some kind of header pointer. That's the head of the list. You also might have a cursor. A cursor is just something that tells you where you are in the list. So you can imagine that a list is something like this, etc. Sometimes we draw, as in electrical engineering, a little ground diagram. We have a head. So conceptually, this is our list. It has data in the first elements, and then it points to next all along the line. And if we do interesting processing of the list, and frequently when we go across the list, when we crawl across the list, we'll either do it through iteration or recursion, and most frequently we want some cursor to tell us where we are. For example, we might want to do a find algorithm. Let's say we want to see if in our list we have a friend, we're looking up the friend, is John in our list? Maybe there's data associated with John. So we do a search element by element for John's personal data until we find John. And when we find John, the cursor is pointing at John, and we can stop. Maybe we'll continue the search later on from the cursor. So an extra cursor sitting there, rather than restarting at the head of the list, can add to the efficiency of your operations. Also, we're going to see the notion of a cursor is generalized in the standard template library. Some of you should already be using the standard template library. For example, I've recommended earlier that vector is a really important, maybe the most important container class in the standard template library, and is very easy to use for anybody who's already familiar with C. It just replaces, in most instances, an ordinary C array. So in the use of the standard template library, there is a generalization of what you might call a cursor, and those are called iterators. And the standard template library is all based on the use of iterators, which I say we'll talk about extensively later on. Again, everybody out there should know what that is. Let me hear what you're saying. Oh, there's somebody saying it's the default constructor. It's a default constructor because its signature, again, is void. And it creates a cursor that's empty. Again, this is older code. It'll work on most of your compilers, but I might prefer in the newer standard where it's available to just use null pointer. Now I'm going to have a number of methods, a number of member functions that's going to make the functionality of a list available. So one of the things about a list is a standard operation is inserting at the front. So we have a list, we decide to manufacture a new element, and we want that new element put on the front. So we're going to see how to write the code for creating an element and sticking it on the front. If we want to get an element, the cursor is pointing at some element. So get element is just return cursor D. D is a data type. So D is an int. Again, later on, I'm just going to give you some thought about this. In the standard template library, this is going to be a template. And as a template, it's going to be able to instantiate regardless of type. And so instead of int in the standard template library, you're going to find that that's going to be replaced by, if you want to think of it, a meta notion, the meta notion of type, so that it can be used to generate containers for arbitrary values. Here's advance. Advance is very simple. It's your basic list operation. If I'm sitting at the cursor, this is next. I look at next, assign the cursor's next value to the current cursor. So that means cursor moves over to here. And we'll also see how to do a print. So let's look at prepend. Remember what we want to do. There's two cases. Now this is also, again, idiomatic. So if this is review for you or new for you, it's really important to absorb it, because once you absorb this kind of idiom, you can do far more complicated things, because most of the things involved in aggregates involve ideas of this kind. So we typically have two important cases. We have the simplest case. The simplest case is where we have an empty list. What's an empty list? An empty list is a pointer, a head pointer, that is pointing at the null pointer value or the 0 value. So we can test it. Again, if you want to be consistent with C11, a little better type safety, just test it against null pointer. That's the empty list case. If it's the empty list, we have to create the list. So the list wasn't around. So we create it by using new. Again, new is the keyword that lets us get to the heap. It says, get me a list element whose value, this is your data value, is n, and this is the existing head. So now we replace head with the existing head, which actually had a value of, and we also start the cursor there. So at the end of this operation, this transforms into, we get this off the heap, n is stored there. The old cursor, which is again the null pointer, is here. And now what was head is pointing there, and what was cursor is pointing there. So that's the simple case, but it needs to be checked on and done. And then the general cases, there's a pre-existing list. And all we need to do there is the cursor's left alone. And in the general case, we just replace the old head by the value of the new list element. So let's look at that case. Let's just draw it quickly. Maybe I'll get rid of, let me get rid of this so I can draw it again properly. Draw it in blue. So in the second case, we have head, we have some general list, we have a cursor, which could be pointing anywhere in the list. Now we manufacture the new element. And it has this value h stored in it. Well, h is just pointing there. And then the real h is now assigned the address to what's now the new first element. Now, I hope by now you're getting used to my terrible handwriting. But okay, anyway, everybody should be able to draw this diagram. It's really important when you are dealing with these kind of complex aggregates conceptually to know what they're doing. Very helpful. So that's prepend. And let's take a quick quiz on that. For yourself, draw how prepend of 5 would work if you had an element that would have value 5. How would that work? And in that, assume there's a pre-existing list that had 2 elements. So take a second. Okay. Let me get back and see what they are. There's 7 and 3 and the null element. So let me draw it. So here's the existing list with its head. We now create a new element, data element 5, and we're creating it with the old head. So the old head is really this address. And then we break that connection and assign that address using the fact that new returns the address on the heap where you manufactured that list element. Okay, let's look at print. So print is, again, an idiomatic or conventional kind of operation that occurs over and over in list processing. And it's when you want to do chaining throughout the list. Here are some of the things to keep in mind. The first thing you want to do is this sets your chain to the beginning. So this is going to be an iteration. The iteration is going to start at the head, and then this is the critical idiom. And once again, I want to show it with what you might do with a C++11 compiler. And as you chain, you're going to print out this value, a comma base. So if we do the thing we just had done, we would print 5 at this point with a comma. Then we'd advance the header to the next element, and we would print, forget whether that was 3 or 7, but let's say it was 7. And then we'd go again, we'd test on seeing whether we had the null pointer. And finally 3, and then h equals h of next, that would hit the null pointer. We'd do the null pointer test, and we'd be out of the loop. So you can see by setting a loop where you're using the null pointer as a sentinel, the null pointer being where you're at the end of the list, and the header as the beginning of the list, and then some processing, you can go through the list as a container in order n time, where there's n elements of the list. And it's very efficient. So if you have to search a whole list and perform operations on a whole list, you don't lose anything over and above what would be indexing through an array. Now, what you should know how to do, I'm not going to show it here, is this kind of processing can also be done with a recursive routine. The idea in the recursion would be the base case of the recursion. If you recall a recursion, you need a base case. The base case would be check for the null pointer. If it's a null pointer, you would exit. If it wasn't the null pointer, print whatever is being pointed at, and then advance a cursor. So the general case is print and advance. So you print and recur, advancing the cursor. And you also should know how to overload your bit shift operator to produce the expected output behavior when you call an O-stream operation on a list. Those are things you can practice. Now that we have this list, let's just see a very simple use of it. Declaration, default. As we know, the default will make A and B be a null pointer. So that's what's happening with these defaults. We're invoking the default constructors, which basically are creation of null pointers. Now we do a prepend, and then we do a further prepend. And if we were to follow the logic, at the end of this prepend, we're going to have 8 and 9. 9 is going to be grounded, and A, or the header of A dot H, is going to point at the first element, which is now the element storing 8. And we can go and do an additional, we could print that. Printing that, we would see 8, 9. And then here we're doing a loop where we're doing a whole bunch of prepends. And here we're prepending to B. And notice that we're doing the prepends of values that are squared. So we're getting from 0 up to 39 squared. So we're going to see something that will end up looking like 0, 1 squared, 2 squared, so 2 squared is 4, and so on until we get to 39 squared. And that'll be, the header will be B, and that'll get printed. So if you wanted to try and figure out what gets printed, it should come out looking like that. Whoop. Well, I've given you pretty much the answer, but you should still do a little testing and see how you could make sure what would be produced and draw what would be produced in the previous code. Okay, so now let's try to develop a more elaborate list. When you go to use the same kinds of data structures in the standard template library, you're going to see a lot of additional member functions, methods, because this is so much in common use. The people who develop it, the library programmers, the professional library developers, they want to give you a significant amount of functionality. There's no reason to force you, if everybody is going to have a need, it should be in the standard library. So what characteristics are you going to find in things that might be in the standard library? It's very typical to find lots of constructors. So that constructor we almost always find is a default constructor. Another constructor we almost always find is a copy constructor. When I get to advanced topics, I'm also going to show something that's very, very new, which is called a move constructor. So for those of you who have access to a C++11 compiler, it's very worth reading on the Wikipedia about move constructor. That's a very advanced topic, quite new, and not necessary for the basic programmer. So we're going to leave that alone till much later in the course. And then here's another constructor that's useful because frequently we want to move material from one kind of container to another. So if we had a simple array, as shown here, and the reason it's const is because we're not going to mutate any of the element values. We have a size of that array, and we want to take something of that size and create a list out of it. So that's another, this is something that lets us transfer data from another container. And then good citizenship requires that we have a destructor. And again, remember what a destructor looks like. It always has this little tilde symbol, and then just like with the constructors, it gets to use the class name. Now we're going to talk about two kinds of copying. And that's going to also give us some real sense of how to make, for complex aggregates, how to worry about trade-offs, robustness versus efficiency. So we're going to also, on the next portion of this lecture, talk a lot about deep versus referential copying. Okay, so we're going to discuss a really important topic, which is the topic of how to effectively copy things. And the two major forms of copying that we find in computation are what are called deep versus referential or shallow. Deep. Well, we have a slide here. It's just pi is transcendental. That's, in effect, a deep notion. In fact, it goes on forever without any pattern or just easily discernible pattern. Mathematicians now for centuries have looked for ways to study and understand the patterns behind pi. So it's a relatively deep notion. We'll compare it to what I might call shallow. Mom just throws in a lot of apples, makes a very tasty pie. Shallow can be good too, so I'm not trying to say that deep is better than shallow. There are different things going on. Now, think about the days that you were actually using the library as a library with physical books. The library kept the Encyclopedia Britannica in the library and then allowed users to come in and use that library. Why? Well, it's very expensive to reproduce the Encyclopedia Britannica. So since it's a super expensive resource, they kept one resource and allowed people to go and use it in a way that they couldn't mutilate it, damage it. They tried to, keep it pristine. And many people could use it. After all, there are a whole bunch of volumes. You could, however many volumes, that would be however many simultaneous users you could have, because they'd be affecting different parts or reading different parts of that one copy. On the other hand, if I had enough money or resources and I needed, let's say, the article on Alan Turing in an Encyclopedia Britannica entry, I might go in and make a deep copy. By a deep copy, I mean I might Xerox it. I might reproduce that copy. Now I have my own copy, and so with my own copy, I can underline it, make notations without affecting the original copy, which had to be kept pristine. So with a deep copy, we have something expensive where we, in effect, manufacture a second version. With a shallow copy, we have multiple users who sort of, if you want, remember in the list example, we had cursors. So everybody could have a cursor into the Encyclopedia Britannica, use it at different points, because none of them are going to be making changes. So deep copy, shallow copy, questions are questions of utilization, cost, and modification. Now, in the remaining part of today's lecture, we're going to talk about deep copies. So the deep copy is the safest. I can turn over a new copy. I can manufacture yet another digital version of what you need, and you can go off and use it in whatever way, shape, or form to your heart's content, because your use of it, even if you modify it, isn't going to affect my use of it. So that's the high-level view. Now, when we're doing copies, what we want to look at is the copy constructor. So it's going to be the copy constructor that, in effect, will determine whether we have a shallow or referential copy. So in the notion of a referential copy, if you think of a list, and let's say I produced a big list. Maybe it has tens of thousands of list elements. And I want to now use it in two different ways. Well, as long as I'm not going to modify it, I could make the shallow copy by creating yet another pointer to that list and navigating the list with two separate, if you want, cursors or pointers. And yet both copies, the pseudo copy, the copy where we have a further pointer to it, is very cheap to do. Really, the referential copy is just the need there is just a single pointer, which is a simple variable, typically 4 bytes, and an address value. However, if I'm going to require that several people use it and they may be modifying the copy, I'm going to have to take the tens of thousands of elements and reproduce them. And then the copy constructor is going to have to be something that goes to the heap and remember that idiom where we marched along with that while loop in the print. So earlier we looked at the print method, so you could go back to it and you would see, well, I'd march along, and for each element in the new list, I would create an element. For each element required in the new list, I would go back and copy the element in the old list. So here's such a copy constructor. Again, here's a simple case where everything is just null. So it's really easy to copy a null list. Very simple. And again, you can see the copying is going to be proportional to the size of the list. And once again, I'll just remind you that if you have a C++11 compiler, also null pointer is an appropriate initialization. And here is the equivalent of, this could also be done with a while. So we have a cursor, a list head. While the cursor is not equal to 0, we chain and create. So we're going to need something with a new here. I'm going to let you write in the code for it. And that's going to be, again, deep copy. Because for whatever this list is, the existing list, the existing header, the new list, head 2, is just going to march along. There's going to be a cursor here. It's going to copy each element in turn, march along until it's done. Here's the internal code. We create the new list element, we do a link, we keep moving, and that inner loop will let us create the entire list. So again, this just fills out the code for the copy constructor. You can follow it along, you should test it, make sure you understand it, and you could do it in other ways as well. With while loops, you could practice to do it with a while loop. You could practice to do it with a recursive format. Now, when we have these aggregates, we talked about good citizenship, and good citizenship for the aggregates means that anything we create off the heap, anything where we're using new, and new is going to get us lots of stuff off the heap. We also want to deallocate. And the nice thing about C++, a little different than the allocation deallocation model in C. If you recall, everybody here's a C programmer. There, your allocations were malloc, and your deallocations were free. Here, we use new, and the deallocation is delete, and basically we have new and new of something new of a type, or new of a type with an array of elements of that type. And then we have the corresponding deletes. We can either delete P, or we can delete P of a vector allocation. The system will do the right thing in either case. So it's very convenient. And so there's really no excuse to have a memory leak. By the way, for those of you who tend to use Unix and Linux, is a very good open source program that lets you see whether you have memory leaks, and I very much recommend that you use this program if it's available for you, and make sure that the program is reporting that you have no memory leaks. That will also vastly improve your practice, because the more you think about your allocation and deallocation and have an appropriate model of what's going on, the more careful you're going to be in doing your C++ programming. Let's use this. Again, this will call your default constructor. Here's an ordinary array. We're calling that constructor in the more elaborate class list, where we take data and convert it over to our list. So in this conversion, we would expect to see something like 3, 4, 6, 7, minus 3, 5, null pointer. That's your 6-element singly linked list. And this conversion for E, so this is the D list, the E list has 10 elements, but we don't see 10 values. Remember what happens. Well, you have an initializer like this, the remaining values are actually zeros. And here on the A list, we do a couple of prepends, and then we start printing out, and you should be able to follow the logic of what gets printed in all these cases. So you should be able to know what gets printed and also when the destructors get invoked. You have a list. There are a number of things you can do with that list structure. You should really understand how it works. You should understand when deletion occurs. You can try to create lists on the fly off the heap. You can new lists, and then you have to principally delete lists, or when the lists go out of scope, then the destructors are automatically invoked. If you want, you can put into the destructor some prints so that you can actually see when things are invoked. That's very useful if the whole concept is new to you. I recommend playing with that a lot. And then the other thing that would be very useful, recall that I asked that everybody here have a background in basic computer science and data structures. So all of you with that background should readily be able to convert that singly linked list to a doubly linked list. Okay, so now in this next topic, the standard template library, which indeed has lists, actually it actually now in C++ 11 has both a singly linked list and a doubly linked list. But the principal data structure it has, and the thing I want you to study the most, is vector. Vector is the most used type. Vector, again, from my perspective, is where you get 90% of your value. So if you learn vector, you'll get 90% of the value in the container in understanding container classes. Or as I should say, sequential container classes. So normally in C, we did everything with these very raw native arrays. Native arrays, they were very primitive. They're really And remember, C was a systems implementation language. It wasn't to be used for a lot of data processing. So Ritchie did not put a lot of effort into making arrays convenient to use. So an array was really just a pointer, and then the pointer was provided with some allocated memory. The allocated memory could come off the heap through a calloc or a malloc, or the allocated memory could come off the heap through a specific stack-based declaration where there was an integer constant amount of memory known on stack entry. So it was a very simple scheme because he didn't require it as system implementation language. But that's far too limited and too error-prone for doing very complicated data-rich computation. So one of the first and most successful kinds of containers is an abstraction of an array in which you not only have the ability to dynamically size the array, you have ways of making sure you don't get any kind of indexing errors, because you also can know where the beginning and end of the vector is. And so one recommendation to becoming a real C++ programmer is abandon your use of basic C arrays and turn all of that processing into vector. There's also a list. A list is another sequential array. Then when you go for a list as opposed to an S list, you get doubly linked lists. And the doubly linked lists look like the code we just looked at, except you would have a data element, you would have a previous pointer, and you'd have a next pointer. And this lets navigation go bidirectionally. So this could be navigated bidirectionally. And that makes a lot of algorithms more convenient, because sometimes you want to stop and then you want to back up, and you don't want to have to always be starting at the beginning of an array, the beginning of a list. So the list is very good for operations like insertion and deletion. It's not so good when you have to get to an nth element that's somewhere deep in the list, because that's an order n computation. There, a vector, which is an order 1 computation, which is very efficient to look up the nth element, dominates. So vectors tend to dominate in the general world of data processing because you have this ability to random access. But lists have very important uses where you need to not only expand but possibly shrink and insert, and you have a fair amount of insertion and deletion, and then the balance is tipped, the efficiency balance is tipped from vector to list. And more complex operations, truthfully, will use both types of these container classes. So that's, again, available in STL and something you should get very used to understanding and using. Okay. If you're out there on a forum, you may want to discuss some of how we are working on homework 2. Remember, homework 2 is to do a Dijkstra's algorithm on shortest paths, in which you generate your graphs at random, and the graphs are not only generated at random, but they have a density. The density means the average number of edges over how many edges can be in a complete graph. So in a complete graph of size n, you can have n minus 1 ordinary edges out of any node, And if you wanted a density of 10%, you would have 10% of that. So if you had 101 nodes, 10% would be you would have 10 edges on average for each node. And that would be a parameter into our graph generating algorithm that we're using to test Dijkstra's algorithm. So we're on a new topic. Everybody should have completed the Dijkstra's algorithm, which was our second assignment and really our first major assignment. So you should have a fair familiarity with how to process graphs, the notion of turning a graph into a class structure, an abstract data type. So you're getting a lot of benefit from using graphs, which are very, very useful throughout algorithms, computer science study. And again, hopefully for most of you, all of this is review. So we're using material you should have already learned and isn't novel, but if it isn't review or you've forgot a lot of it, there are excellent articles, especially in the Wikipedia, on all these algorithms, on the basic graph theory, including the algorithmic graph theory behind things like Dijkstra's algorithm, today's algorithm, which we're going to talk about and will be the basis for the next homework assignment. So it builds on Dijkstra. So in some sense, it should be easier because now you're past the jitters. You've gotten your programming legs in terms of this complicated aggregate, and you're just going to add a new algorithm. And the whole course is structured to build algorithm by algorithm towards the end of the course. We're hoping you're going to all be able to implement this very interesting game, hex, which can also be represented largely as a graph. So today, the main topic is minimum spanning trees, basis for homework 3, and we're also going to study, again, object orientation, how important object orientation is when we use a language like C++. What are the ideas we bring to the table to do good C++ programming? C++ is way more than an object-oriented language. It's got multiple tools in its bag, and it has the ability to do generic programming. It has the ability actually to do functional programming in terms of C++ 11. So it's multi-paradigmatic. C++ is multi-paradigmatic, but a really great strength. And the thing that has it replacing C was the shift from ordinary imperative programming, that was C, to encapsulation based on the object-oriented paradigm. And we'll see that with a very simple but very useful example called class point. So homework 3. You've already built the graph abstract data type. You hopefully got the Dijkstra algorithm to work. You got it to work on automatically generated graph based on densities and size. You computed an average length in such a graph. Saw how all of that could work. And we're going to add this next major algorithm, again, extremely useful. Minimum spanning tree comes up in many, many areas of computer science and electrical engineering. In some sense, it's maybe at the heart of the internet. The way the internet works, one wants to have a minimum spanning tree so that from particular foci, you can get your messages, packets, whatever, out to arbitrary other foci. Minimum spanning tree, a definition. So again, we're going to have a graph in which an edge has some arbitrary positive cost, an edge. So we might have an edge from A to B with, let's say, cost 7. And we have a whole graph built of edges with costs. First off, we have to know what a spanning tree is. A spanning tree is just a set of edges that in effect is a tree. Remember, we in computer science frequently use things called binary trees. Binary trees would be spanning trees of graphs if the graph had inside it a binary tree. So a spanning tree is a set of edges within the graph that connects all the nodes of the graph and where there is no cycles. So an immediate implication of that is if we have a graph of n nodes, a spanning tree is a tree with n minus 1 edges. Now, I'm also going to, in this homework problem, assume that edges in the spanning tree can have different colors. It's going to make it a little more sophisticated, and I'll add to some of the ideas in how you learn C++ programming. It'll enable you to use an enum type or a class enum type that class enum type is yet another novel idea in C++ 11. So if you have a C++ 11 compiler, we may talk a little bit about a class enum type as opposed to the earlier pure enum type, which remains. And so we're going to assume that an edge can be red, it can be red edges, there can be blue edges, there can be green edges. And we might, when we specify our minimum spanning tree problem, decide on, well, do we want a minimum spanning tree in which all the edges are green, green and MST. Or maybe we would have blue and red and an MST. So for the same graph in which there were colors, we could have multiple answers to the minimum spanning tree. So as I say, it just makes the problem a little bit non-standard, not as easy to copy the code off the internet, adds a little flavor to it. And actually, it'll be a flavor that will be useful in many later and more complicated venues. So first, let's take a little quiz. If we have an enumerated type, here's a simple enumerated type, color. This is different than, as I say, C++ 11 will have a class enumerated type. Why were the colors capitalized? The enumerators have internal values. In this case, what would be the value of green? And if we wanted, and this is a new type, so again, object orientation is all about adding types to the basic native types in a way that is compatible with the basic native types and fulfills the expectation of the C++ community. And the expectation in the C++ community is that the I/O, what you might call pseudo operators, the operators adopted to, in this case, the bit shift operators, adapted so that they do I/O, can be overloaded. How would we overload to print red? So take a few minutes and see how you'd answer those questions. Well, first off, the reason that we use capital is just a community convention. So whenever we have things that we think of as constants, this even goes back to the old C style, where when we didn't have enumerators, we just did this using macros. So the minute we see in our C code some big all caps identifier, we think, that must be some kind of standard constant. In this case, the values go sequentially 0, 1, and 2, so green ends up 2. And then if we were to implement the code for overloading the operator, recall that it has a certain idiomatic format. We're always going to call by reference this complex construct, the O stream. We call the new type that we want to overload, and then we're going to return. What do we return here? Everybody should know that that should be return of out. Why is that again? So that we can properly use C out something. And that in effect, these are expressions that evaluate to the same O stream so that you can use that output repeatedly. Here's some new novel stuff, fresh from the new standard. There are what we call strongly typed enumerators, enum classes. We're going to see why we need them. Let's say in the old style, I could have had enum color and enum traffic, and then I'd have two specific uses of red as enumerators. And they could actually get confused because they weren't strongly typed. They're, in essence, some kind of integer. And they would be comparable if I wanted to. However, when I turned them into this newly strongly typed enum, and that happens by, instead of just calling them enum, calling them enum class. So it looks somewhat the same, except now I have class. Now, the two enumerators are distinct. They're not comparable. They have type distinction. Since they have type distinction, they're much safer in code. We can't get into trouble with conversion opportunities, for example. New topic. We're going to discuss in detail the minimum spanning tree algorithm. So the minimum spanning tree algorithm was actually discovered, this is found out later because it was fairly obscure. There was a Czech mathematician named Jarnik, and he wrote a paper where he in effect had this algorithm in 1930. But engineers and computer scientists attribute the first algorithm that uses this method to Prim, who published and rediscovered the algorithm in 1957. We're going to compare this algorithm to a competitor algorithm that was also discovered roughly in the same time by the the discrete mathematician, computer scientist Kruskal. So I'm going to explain both algorithms. You'll get a chance to either implement one or both. They're not completely equivalent. They're equivalent in the sense that they will give you the right answer, but in some circumstance, one could be more efficient than the other. But one doesn't dominate the other completely, and so it's actually useful to have both implemented. Prim's algorithm starts with a single vertex. You could imagine that you pick vertex A, or if you're using a C-like notation, you have vertex 0. You would start with a single vertex, look for something that was a minimum weight edge out of that vertex, and place it in and build your tree. So you would start by saying, let's say we go to node 0, look for the minimum weighted edge out of node 0. What if there is no edge out of node 0? No edge out of node 0, then there's no way for node 0 to be connected to the rest of the graph. If there's no connection to the rest of the graph, we don't have a minimum spanning tree. We have what's called a disjoint or a disconnected graph. So you should keep that in mind when you write your algorithm. In some instances, the graphs that you'll be looking at will not have a minimum spanning tree, and they need to report that somehow. They need to report that with some other kind of standard value, like some very large maximum integer or a sentinel value. Maybe it would be negative to indicate that it was that the graph is disconnected, or not a number value. In any case, it is possible. You have a graph. It doesn't have to be connected. If it's not connected, it won't have a spanning tree. If it is connected, namely, any vertex can reach any other vertex, or any node can reach any other node, then there will be a spanning tree. And if there's a spanning tree, there has to be a minimum spanning tree. So Prim builds the spanning tree one node at a time, connecting the node to the existing tree. So it builds the tree from an existing single component tree. That's going to be the difference between Prim and Kruskal. Later on, we'll see with Kruskal that it builds the spanning tree potentially by creating a forest, and then as the forest grows out, the forest connects up, and then you end up with one component. I think the Prim algorithm in some ways is maybe conceptually a little simpler. Okay, so let's quickly go through how Prim is going to pick off edges. I'm going to just draw them conceptually and then keep track of their value. So if the start edge is A, the start node is A, there are basically two places to get to, E and F. E is the one with the shorter distance. So that means I'm going to go from A to E. And as we go, we're building a spanning tree. So we might think of that spanning tree as the existing or closed set, much like we built a shortest path tree in Dijkstra. And so we have the existing AE closed set, and we're looking for what we can reach. So that started with a value of 2. And the thing we can reach now is we can go to G, which is 4. We can go to D, which is 6. We can go to I, which is 4. We can go to F, which is 2. Ah, that 2 is the best. So let's pick that up. That gives us a second value of 2. And now we have, we've added F in here. F gives us some other possibilities. That possibility is F to I, which is 5. But the best of these is one of the 4s. We can tie break, and we can add that 4, the E to G. And now we have a new possibility that's actually the lowest value, which is 3. So we would go along G to H. We'd add H into our built-up tree. H is 3. We can see that we're picking things off in what's called a greedy manner. I want to point that out. This is like Dijkstra. It's one of these categories of greedy algorithms. Now we have G to D, H to D, which is 5, but the best is one of the things we saw earlier, H to I, which is 4. And that lets us have an I to D, which is also 4. And now we're done. We have 6 edges. We have a full spanning tree. And because we did it in this greedy manner, here are all its individual costs. And if we add them up, we get 4, 8, 11, 15, 19. So the total minimum spanning tree cost in the prim method leads us to a spanning tree of 19. So repeating for prim, we start at A, we look for what's the least value edge out of A. That turned out to be, or we could call it the nearest edge, that turned out to be E. And then we keep going from what we built as the set of nodes that are already connected. We pick the next node that's not connected to the existing tree, and we pick the smallest edge there until we have n-1 edges, and then that's our result, or until we don't have the ability to select anymore, and the graph is disconnected. So we can't have a disconnected situation. And you can see from how we've structured it that there's no way we can get loops. We never look back into the pre-existing set of nodes that we have already linked. So that means that we'll see in Kruskal we have to also figure out a way to avoid loops. We don't want to, even though there might be a small arc, we don't want to end up with a situation where if we picked, something that was 2 here and something that was 3 here, and then we can go on from here or here, but this thing was 1, for example, and let's say this was a minimum. We don't pick this one because these 2 guys we already had that. So we don't look back into any of the existing tree. So we just have to keep track of where we haven't yet gone. What are the nodes where we haven't yet gone? If we remember the Dijkstra thing, you might call that the open set. And the closed set might be existing tree. So we're building a tree, there's an existing tree, and we have to look at nearest node that's in the open set. That's another way to think of prim. Okay, so now you've seen how to do prim. We've seen it on a graph that should let you be able to do an arbitrary graph. Let me give you a little quiz just to check your insight on the algorithm. So, for example, we could have every edge have unit costs, the same cost. And if there was such a graph where every edge was cost 1 and it had 10 nodes, and there was indeed a spanning tree, what would the minimum spanning tree cost be? Okay, hopefully you should be able to get that. And now you should be able to generalize it. So what's the same question if we have an arbitrary size graph, n? The graph has n nodes, is connected, has unit cost, what would its spanning tree cost be? So think about that. Indeed, if you remember your mathematical induction, you could even make a proof out of this. So anything that would have a connected graph, we would need 9 edges in the 10 nodes. Therefore, 9 would be the minimum spanning tree cost. And then in general, if we had n nodes, a spanning tree would have to have n minus 1 edges, and therefore its cost would have to be n minus 1. Let's just apply prim one more time. I need you to be very solid on this because this is the last homework in this first half of the class, which is this sort of where there'll be a natural break before we, in the second half of the course, take up game playing. So in order to program this properly, you should always be able to hand simulate. Without hand simulation, you're not going to be able to think of your own code, think of its correctness, and implement it properly. So we'll do this one as well. Let's do prim on it. I'm going to start with A again. By the way, is it necessary to start with A? Could I have started with G or C? Think about that. So I start with A. I could have A goes to H, A goes to B. Clear that it's AB. That's a 4. Now we have the mini tree AB. We can go to C, we can go to H, that's 11, that's 8. We could, we have 2 8s, so we have the possibility of a tie break. Let's do that one. So that is the one that we've already done. But notice we could have tie breaked and gone A to H. Maybe I'll do A to H after and see that we get the same result. And now we have the possibility of an 8, a 2, a 7, a 4. 2 is the best. So we do a 2. Now I have the possibility of a 4, a 7, the previous possibilities. 4 is next. Now I have a 7, another 2. 2 is clearly the best. Now I have a 10. 1 is obviously now possible. That's the best. So we're always keeping track of, in the open set, what is our next, what are our set of choices. 7 is now the best. And the only thing in the open set is E. And we can get to E from F with 10 and from D with 9. So 9 is the best. And now we're done. Let's add that up. That's 12, 14, 18, 20, 28, 37. So prim has given us 37. Notice we don't necessarily always get the same one. We could have, at the point that we got A to B, we could have gone to H. Let's make sure we get the same thing. So I'm gonna redo this. 4 again was required. Now I go to H. That gives us an 8. Now I can do a 1. Gives us a 1. Now I can do a 2. Gives us a 2. Now I can do a 4. Gives us a 4. Now I can do a 2. Gives us a 2. Now the best is a 7. And now I do a 9. So that gives us the right number of edges and the same set of costs as before, notice it gives us a slightly different minimum spanning tree. Nobody said the minimum spanning tree has to be unique. It just means that the cost has to be unique. But there can be many minimum spanning trees with a minimum cost. Okay, here's pseudocode for prim. So many places to find the pseudocode. Frequently, pseudocode like this comes from the Wikipedia, and if you're programming, and you shouldn't just be sitting at a terminal and just banging away code. You should be writing at a high level what you need, and pseudocode is a good way to start. Have some kind of fairly careful pseudocode that is readily translatable into direct C++ code. So we have a graph G with edges E. The edges are represented in the form of pairs, V1 to V2. We are, by the way, using undirected graphs. We've been using undirected graphs throughout the class. If you want an interesting alternative is to write all the code so that it can also work with directed graphs. Don't recall that an undirected graph effectively, when I'll just show you, in a directed graph you generally say vertex 1 is connected in this direction to vertex 2. In an undirected graph, you don't have an arrow, and instead that would be the equivalent of two directed edges. So for every edge that was going in one direction, there would be an edge going in the other direction. In the directed representation, undirected representation, we don't draw the arrows. In the real world, it means every street in your street map is a two-way street. And then we have this basic loop where we're searching for the next smallest distance, and as long as there's the next smallest distance, we add it until we're done with, that's the size of the needed number of edges. So after we've established the graph and set up the fact that we have an empty minimum spanning tree, we start picking distances, and because it's pseudocode, we're not actually showing this, but we're going to have to include something that gets us the shortest edge. We may want to maintain this as a data structure. Sometimes we could have a priority queue, if some of you know this idea. Of edges and pick off the next smallest edge. So we need some way to get at the next smallest edge. And then we add those in and update and keep going until we're done finding, as I say, this is just a characterization of prim and pseudocode. Prim and Dijkstra are called greedy. Greedy algorithms are something that work efficiently because they generally have a very simple concept like pick something locally that's best. And greedy algorithms, if they work, are very good because by picking the best thing locally, you generally have a very cheap computation, and yet knowing that by proof that gets you the global minimum or maximum lets you have what's called a very highly efficient way. There are lots of greedy algorithms that don't guarantee that you get a global optimum. For example, well, we won't study it here. A more interesting and difficult and still what you might call unsolved problem is the traveling salesman problem. The traveling salesman problem is almost like the minimum spanning tree problem, except that you must produce a spanning tree in a graph that's linear. What do I mean by a linear spanning tree? It's, let's say you started with A. The tree structure is going to end up looking like this, with the final node here. And if I just go to a next node and a next node and a next node that hasn't been visited in this form, and I find and I choose a minimum, there is no guarantee that the overall path, the overall linear tree, is a minimum. Indeed, what's well known is that can fail. So this is a very efficient algorithm, but it only finds an approximation, a heuristic approximation to the traveling salesman problem. The traveling salesman problem is an NP-complete problem. So the deep suspicion is that there is no polynomial time algorithm on a normal computer that can always solve the traveling salesman problem. So it remains very interesting to try and design things that work very well, that are both efficient and either give you an optimum or near optimum solution. So that's a problem I've studied, for example, in my own research. Maybe some of you will want to do that as something optional. Now let's turn in the next segment to the Kruskal version. So we'll also talk about, at a high level, what is it that Kruskal does and how it differs from Prim. So Kruskal doesn't necessarily compute a single component. Prim computed a single component, and the greedy idea was take the next small edge that adds to that greedy existing component. Kruskal instead creates a forest, which are a set of trees. So each vertex can be thought of to start off as a forest of n nodes. They're not yet connected. And then when you add an edge, you take two of the trees in the forest and you turn them into a single component. And so you're adding shortest edges. You can sort of view that the Kruskal algorithm could take the set of edges that are in the graph and sort them, smallest first. Now, if you had the shortest, all the edges of the graph can have n squared edges. You have a sorting problem there. So n squared, you would end up with something like an n squared log n computation to get the edges sorted as to length. Now you have a sorted list of edges. Why not be able to take the first n minus 1 edges and create that as your minimum spanning tree? Think about that. That would get you a minimum. So it's clear that those would be the smallest n minus 1 edges in the graph. The reason it wouldn't necessarily give you a spanning tree is some of those edges may create loops. So you wouldn't get new edges as you would. You don't get a new node put into the closed set as you do in Prim. So you're forced in the Kruskal pseudocode to check whether you've created an internal loop. So you can take the next shortest edge, stick it into the existing Kruskal forest. If it doesn't create a loop, you're fine, and you can go and get the next shortest edge. But you must check if that next edge is inside a pre-existing Kruskal component, then you have to discard it and move on. Okay, so that's the algorithm. Let's apply it. Here's yet another spanning tree, and this time we're going to do Kruskal. So we would start off, and we know that AD is value 5, CE is value 5, DF is value 6, AB is value 7, BE is 7, EF is 8, BC is 8, BD is 9, EG is 9, FG is 11, and DE is 15. So this is our sorted list of edges. Well, we have no problem. All of the nodes are disconnected at this point. And so we know we can add this. And now we have our first Kruskal component, AD. And let me write out the fact that that's a 5 there. Now we go back to the list. Notice the next thing we're going to select is CE. Right? Different than prim. Prim didn't work that way. Prim would have to select DF because it connects up to this component. Kruskal picks the next in the list. It's knocking off these in the list. That's a component that has nothing to do with a pre-existing component. Now DF is next. So that's 6. Let me remember to get all my values. AB, 7. Each time in my mind, I'm checking whether I have the edges sitting in a Kruskal component. It's not. BE is 7. EF is 8. Notice, I can't draw EF. Why can't I draw EF? It's the next smallest. Because it would create a path. I use a different color for it. I use red. It's a loop. So that can't be used. So that's thrown out. BC is thrown out. The next one is BD. BD is thrown out. EG is okay. And we're done. That's it. So we have a minimum spanning tree dealing with Kruskal, which built it as a forest. We have 16, 23, 30, 39. MST 39. And as I said, if we wanted to try this, let's do it very quickly and with prim and see the difference. I'll start with an A. Let me get, that's a 5. Now there's a 6. There's a 7. There's a 7. There's a 5. And there's a 9. So Kruskal, so prim would work by building out the component, but would get us the exact same tree necessarily. I think and that would be the same minimum spanning tree as well. Quiz. How would you change this algorithm to find a maximum spanning tree? Maybe you want to build a tree in which everything is the most costly. That'd be a little unusual, so that's not normally how the problem is stated. Okay, let's look for a solution. Same structure, but instead sort with largest first. So you can see the logic of largest first. If there was a spanning tree, you'd get a largest spanning tree. Again, it would have to be a tree structure. It would give you your largest values. Okay, next topic. We're going to get back to some core C++ ideas. So we've outlined the methods you need for the homework. You can either use Prim or Kruskal or do both. Compare them if you have energy and time. You're going to add that to your pre-existing homework where you've already done graph algorithms. Try and refine whatever you learned from before. Maybe your graph structure will be more elegant. And now that you've learned more C++, you can rebuild even your basic graph class. But in any case, the new problem is to do a Kruskal or Prim minimum spanning tree. And now we want to introduce further ideas from C++. The critical ideas we want is a very neat idea. It's something that hasn't been put into Java, for example. There are arguments over whether it's a good idea, but in lots of arenas, it's a very valuable idea, and that's called operator overloading. That's where we provide new meanings to existing C++ operators. And we've already used this as a very rich idea in the I/O community, in the I/O package, where we have operator overloading of the left bit shift for doing output. And we're going to show how important yet another idea is that we haven't seen yet in C++, which is using friend functions, especially when we want to provide operator overloading. Okay, high-level principle. User-defined types should be indistinguishable from native types. Operator overloading is a mechanism that allows us, and conversion, those are mechanisms that allow us to implement this principle. What do I mean by that? In the native language, if I have two ints, we all know what A plus B means. But let's say I decide to add from a library or whatever a rational number. For those of you who don't remember your high school math, a rational is just a number represented by two integers, q divided by p. So 2/3 is a rational, 3/4 is a rational, 7/11 is a rational. Pi is not a rational. Remember the notion the other day of pi being transcendental. It can't be represented precisely by, there are ways to represent pi. There's a nearby rational. For example, 7/22 is a fairly good approximation to pi when you have two small integers. And you can approximate pi as closely as you want by rational, but you can't make it exact. Anyway, if I all of a sudden had some kind of package for doing rational arithmetic, I might also want to be able to have C plus D, because mathematicians can add rationals. Again, if you remember your grade school work, they probably told you how to do this kind of addition. So your rational overloading of the plus operator would lead you to provide the algorithm for doing rational arithmetic. But rationals can be used much like integers and doubles. So you might also expect that you should be able to do A plus C, where A was a normal int and C was a rational, and have a resulting conversion, and convert the A to a rational. So now your rationals, this new thing, this new class that you've invented, gets used as conveniently as a native type. That's part of the OOP principle. When you add a type, you want to add a type in a way that is consistent with pre-existing types in the C++ world. So we're going to add a type. We're going to add the type point. Point's a very simple type. Here's a point. We're going to think of a point as a pair in a two-dimensional world, x and y. Maybe that's the point 1, 1. As with good OO, we're going to hide representation. So the actual underlying representation will be a pair of doubles. So we can also have the point 0.5, 0.5. Really, we should be thinking of that as 1.0, 1.0. So we're going to use doubles. We're going to have a bunch of constructors. Here's a constructor. That's a constructor of one argument, which basically takes an argument, makes it the x value, and leaves the y value as 0. So a point here is going to, like if I want to have a point whose value is initialized with 3, I'm going to end up with the point 3, 0 through this constructor. This is going to be important because this is also what we call a conversion constructor. So here's a point, S. We can think of it as having value 0, 0 if we define that class properly with a default. And now we have a double 3.5, and we say assign to S D. Now D is a double, and we don't have a logic for assigning a double. So there needs to be a conversion. So D needs to be converted to the point 3.5, 0. Once it's converted, then we can have the assignment. Now, if we wanted to make that clearer, we could do it via an explicit assignment. But actually, this works as well. Why does it work? Because C++ allows for implicit conversion. In fact, I'm going to go back to the previous slide because I'm going to show you something that you can keep in mind. If you didn't want that behavior, you would have to add the keyword explicit. And explicit, in a way, turns off implicit conversion opportunity. So there's lots of times that you don't really want that to happen because adding conversion opportunities in this language it's very sensitive because conversions allow signatures to be matched, they allow expressions to be evaluated, and you don't want that to happen inadvertently. Now, what about converting a point to double? Well, we know how to convert double to point. The way we convert double to point is we write a conversion constructor. So the argument, the double argument, becomes an argument of value to instantiate some of the underlying data in point. But we can't write a conversion constructor in the native class double. Double is a native type. You could think of it as having its own code somewhere in the world. It's really just built into the compiler. But there isn't a way to inform the compiler that I want to change the rules about double. So, because there's no access to that code. So C++ does provide an alternative, and you see the alternative here. You can, inside the class point, so again, we see that we have scoped resolution to point, by providing operator double, the type to be converted to, we allow a point to be converted to a double. Now, whether that makes sense, whether that's a good idea, probably only should be used where it's natural to the semantics of that type. What do I mean by natural to the semantics of that type? With somebody who is used to, a draftsman who's using two-dimensional objects, two-dimensional coordinates, points. If you told him that I wanted to convert a point to a double, would he know what you meant? If he doesn't know what you mean, if he doesn't know that you intend to use the distance the vector is from the origin, which is basically what we're doing here, then it's a bad idea. Then you should probably provide something that's explicit, like the length of a point from the origin. You should have a name type. So these conversion opportunities can easily lead to obscure programming, and they frequently should be very heavily justified, and the justification should come from the domain in which the type is used. But it's available. So now you can have what might be called a narrowing conversion, and you could turn a point into a double, you could turn a point similarly into anything else by providing it with whatever this type name is, a type, and some semantics to convert to that type. And then you have conversion opportunities. Pretty powerful stuff. Oh, we've already talked a little bit about that. I've already pointed this out. Again, C++ 11, some of the earlier compilers already implemented this, allowed an explicit keyword. Once people started doing rampant operator overloading and conversion, it was soon discovered that things were happening subtly that nobody expected. And so the explicit keyword got introduced so that that could be turned off, that opportunity could be turned off. Now, remember that in C++, one of the big changes from C is you have function overloading, right? So in C, if we wanted the sum of an integer array, we had to call it sum of int array. If we wanted the sum of a double array, we had to give it a different name. We had to distinguish the name, even when the code read the same. C++ provides a number of ways to keep the name for something that where we're doing conceptually the same work using the same code. The two principal methods are ordinary overloading of functions. So we can call both the adding of arrays of ints and the adding of arrays of doubles, or even the adding of arrays of rationals, sum. And then they get discriminated by their signature. Let me just, right? If I wanted, I could say double, sum, double, int, sum, int. The code would probably look the same. I can even do this with templates. And the compiler has to have a way among the meanings available to it to choose which meaning. Otherwise, it becomes ambiguous. So you can as a compiler error message, get the fact that the compiler is confused. Now, the compiler has a very complex and detailed way it has preferred selection. So exact match is always preferred. If it is passed in a set of arguments and it looks at their type and it says, oh, I have exactly code for those types, then it picks that. No problem. Everybody understands that. But now we have all these promotions available. So again, just like with square root, remember square root is in the standard library, in the math library. Square root will work on an integer, even though it's intended to work on doubles. Why? Because the integer will be promoted automatically, silently to a double. So again, what happens is in overloading, standard promotions, which are the safest kinds of promotions, are preferred over anything else. And so if there's a signature and it requires a standard promotion and there's no exact match, then this would be tried. The next in line are standard type conversions, including demotions. Then there are user-defined conversions, much like those conversions we defined on point. And then there's a match to see if there's an ellipsis signature, and that's the worst. Now, if you're following any of this in my text, there's description of it, page 198 to 200, with a detailed example using rational numbers. But it can be very complicated. And you can see where you have all these additional user-defined conversion opportunities that you have to be very, very careful. Hence the introduction of explicit to avoid silently ending up with execution of code that was unintended. Friends, next big topic. We have these things called friends functions. There's a couple of friends there. My own cats are named Googly and Napster. They're friends, though they're more frenemies than friends. Cats, being even domesticated cats, seem to be fairly territorial, so they do hiss at each other. And they especially fight over their food bowls. But the critical thing about friends, and that's going to be true in C++, is if you're a really good friend of mine, I'm going to let you look at my private stuff. I'm going to let you look at the private implementation of my class. That gives me the opportunity to act on your class almost as if I was a member function. So a friend function has access as if it was a member function, but it's not a member function. If it's not a member function, that means it has no access to what? Think about that. There's one thing that member functions always get, ordinary member functions always get, that functions that are called with arguments on the class don't get, and that's the this pointer. Remember, a member function is activated through the this pointer. Friend function gets to treat the private parts as if it was a member function, but doesn't get to directly access, because that's not passed in, an argument through the dot notation. Here's our class point, and again, because it's the object-oriented idiom, we want the behavior of the bit shift operator to be used for I/O. Again, here we see the I/O signature. That's our idiom. We need this call by reference. We pass back out call by reference. We have a non-mutated object passed by reference. And its semantics are that we're going to print a point looking like this. So what we would see as output for a point that had hidden representation 1.0, 2.5 would be paren 1.0, comma 2.5 paren. But this is going to fail. So if we were in regular code and saying cout, blah, blah, and the point name was q, we would get a compiler error, and the compiler error would say you wouldn't have access to X and Y. Why? X and Y are private. This is an ordinary method. It does not have the ability to access hidden representation. Can't make use of this. Well, OO says that this must remain restricted, data hiding principle. So the way around this, well, one idea you could try is to make this a member function. But recall, a member function has a default first argument. The default first argument has to be an object of type point. But for this to work in the syntax that's expected, the first argument has to be an O stream. It has to be, in most instances, an O stream like cout. So we can't make it a member function. A member function would solve the problem of getting access, but it wouldn't solve the problem of having the wrong argument order. And C++, courtesy of Bjorn, invented a way around to this kind of access problem, and that was to create friend functions. There's where friend becomes important. I use this special keyword, friend. That informs the compiler that it's got these privileges. It breaks the normal data hiding. So it should be used very carefully. Friend should be used very carefully. We allow it to have these important access privileges. Unlike a class method, it does not have the dot argument. So now we're going to pass in both arguments. We're going to pass in an O stream and a point. And they'll be passed in through the argument list, which is another thing to consider. Because when we pass stuff in through the argument list, they're subject to conversion opportunities. So that's another point, very important and subtle point, that deals with the use of friends when we overload operators. Friends overload operators by having the arguments always go through the parameter list. Member functions overload the arguments by having the first argument be the class argument, namely a this pointer argument that is not overloaded to have conversion opportunity. So only a second or other argument would have a conversion opportunity. That leads to a different behavior. Even when we can overload the same operator and have the choice between friend overloading, member function overloading, we frequently choose friend overloading. I'm going to make that point a couple of times because it's a very subtle and important point. We do that to maintain symmetry. The friend overloading lets us use the argument list. The argument list means for binary operators, we get all the conversion opportunities symmetrically on both arguments. Okay, here is a member function overloading of the operator plus. So think of what you're doing. You have 2 points. Let's say we have 2, 1, and a half, 0. And we want, maybe that's an A and that's a B. And we want to be able to, because that's what we are used to as mathematicians, be able to write naturally A plus B. And we can see what we want that to be, that result. Let's call it at C. We want C to come out 2.5, 1. And the way we do that is, if we're overloading this with the notion that we have A plus B, we really are calling through the this pointer A and through the argument list B. That's really how this is getting activated. So that's why X and Y are without, and those fields are discriminable. See, these are really this points at x plus p of x. And that leads to the 2.5. And similarly for the y. Okay, that starts, if you understand everything I just said, you're really getting all this. If you don't understand what I've just said, you've got to work with this. You've got to do your own stuff. You've got to overload operators and see how that works. So this is very critical that what I just said is clear to you. So here you've seen how to overload the binary plus using a member function. And here I'm just repeating what I said on the other with a different example. I have 3 points. I'm adding to A, B plus C. A is going to end up being 2.5, comma 7, right? But if instead that operator got overloaded in a way that we used a friend function instead of a member function, its invocation would instead call a friend function, and both B and C would be passed in instead of a this pointer and an argument. This would be arg1 and arg2, and they would be completely symmetric. So in the completely symmetric case, all the available conversion opportunities. So for example, remember, we can convert an ordinary double to a point. So that would mean, if you're following me, that if D was a double and I did D plus B, this wouldn't work for member overloading. And that gives you the reason why you want it as a friend function. Friends are really important. They're really important, especially when you're doing operator overloading. They're important in other considerations too, when you have two very strongly linked classes. Got to warn you about operator overloading. People get infatuated with it. Why? Because it's a way to have a secret calculus. Everybody loves making their own secret notation. That's okay. If you're just playing with the stuff and you're not in a company and you're not using it professionally where other people will need to interact with your code, do operator overloading to your heart's content. Maybe you can even come up with something close to APL if you remember this hugely powerful early IBM language. A man named Iverson invented a language in which there were super powerful overloaded operators, in effect, that worked very well with linear algebra calculations. And from what I recall, I may be wrong about it, somebody can write into a forum on this, I believe you could write out a linear programming algorithm using the Iverson notation in relatively few lines of code, whereas if you had to use the language of the day, such as Fortran at PL1, it would be a considerable amount of code. So you'd have this enormously dense, powerful operator language, and this could be replicated with operator overloading. But using this, one expects to conform to the rules of math. You generally are going to use it in domains for which people know what the meaning is. You don't want to have to explain that plus is something that it isn't. What does times mean in a domain where you are talking about clocks? Let's say you decide to design a package called a clock, and clocks have minutes, seconds, and hours. Well, it's pretty easy to understand how, I have an appointment a half an hour from now, so I want to know what time that's going to be. But now what's the times operator going to be? Can I multiply 2 clock times? Is that reasonable? So you got to be very careful. And you need to be comprehensive. So you're not going to go and overload plus in a normal domain in which minus is understood as being the inverse operation. So normally you're going to overload the complete algebra. You have to do what's expected, you have to do what's natural, and you have to do what fits in with the native C++ types. Okay, here's a quiz for this section. Not all operators are overloadable. Most operators in C++ are overloadable. Some operators, like scope resolution, remember that's colon, colon, that's not overloadable. Why? Well, that would cause catastrophe. If you gave it a different meaning from what it needs to be, which is scope resolution, it would, for one thing, it's very hard to imagine what that meaning could be. So it's not overloadable. Another operator that's not overloadable is the ternary operator, and there is a single ternary operator, and what I'm asking you is to explain what it is and why it's not overloadable. Answer, the ternary operator is question mark equal. So the typical thing is you have some, let's write out something just so you remember. There are many people who rarely use this operator. You say something like A less than B, question mark, A colon B. So these are the three arguments, arg1, arg2, arg3. In the normal language, it says test this for truth. And if true, this is the true result. And this is the false result. So many people prefer to just do these things with if or else calculations. The reason that this isn't overloadable is Bjorn didn't want to bother with it. It's already not that used an operator. It's generally not an operator you expect in any algebra. It would be ugly, so it's not overloadable. Maybe there's some other reason. Okay, that's it for today. We've packed in a lot, and I will see you next time. Today we're going to delve into the architecture of the standard template library. The standard template library we've already been using. We've been using it with container classes such as vector. Vector is very, very useful. If you've been doing much with it in your homework, you will see that it's a big benefit over the C standard way of index collections, which is a relatively primitive form of array. So STL has an architecture. Once we understand that architecture, we're going to have a much better way to use it. We're also, in understanding the architecture, going to learn how to extend the STL library. Now, one of the topics I'm going to start emphasizing today and in the future part of the course and successor course is going to be new developments in the C++ standard. C++ has been around since 1985, originally released at Bell Labs with the C-Front compiler. It immediately got a lot of attention in industry and got widely adopted. And then things got added to it. The last major standardization occurred around 1998, so that's 15 years ago. And most of the practice that we have had in industry and most of the practice that I have shown you is based on 1998 C++. But in 2011, the Standards Committee made major additions, major improvements to the language and major additions. Among the major additions were the expansion of the standard template library. That allows us to effectively, without having to create our own new libraries, use libraries from this new standard. An example is the threading library. So threading has become more and more important as we have multi-core computers, multi-processors, clouds, and the ability to have a community standard in threading. It wasn't that we couldn't do threading. We could do threading even in the old C community. We could use POSIX threads, for example. Now, built into a library is a standard. So we're going to start discussing some of the new C11 features as well, and that will be a big emphasis in the second half of this course. To understand the architecture of STL, I like to picture it as a three-legged stool. So STL is sitting on containers, algorithms, and iterators. And they all interact. They've all been thought through to benefit each other. The components of the three-legged stool are containers like vector and list. List and vector are what are called sequential containers. In sequential containers, we know what the first element, the third element, the nth element of a list or a vector is. So we think of it as storing things in compartments that are indexed. On the other hand, we have other kinds of containers, such as sets and maps, and those are called associative containers. And there, the major form of lookup is no longer an index, but instead is an association between a key and what the key lets you get to, the contents. So there's an association. In the real world, if I were to give you a friend's name and maybe ask you for the friend's address, that would be an associative lookup. Then there is the ability to search through those containers. And that ability is going to be provided by what we call iterators. Iterators are ways, they're conceptually very close to pointers. So if you want to think of an iterator in the C language, think of a pointer. Pointer lets you get access to an array or to parts of a struct. And in this case, pointers can be generalized and given other properties that make them more convenient, more systematic. And there will be, at the end of the day, 5 major categories of iterators, which we'll also explain. Finally, what we want to generate out of STL is convenient algorithms, algorithms that are very applicable across all sorts of domains so that we don't have to keep inventing the wheel. Why should we have to continually invent sorting algorithms, finding algorithms, accumulating algorithms, partitioning algorithms? We're using those all the time. And if you are a student, those are probably a lot of your exercises, and you get to learn how to discriminate between good ones and bad ones. That's a lot of what your learning is in your basic computer science classes. So you might learn how to write a bubble sort and learn why a bubble sort is not as good as quicksort or a heap sort. You might learn how to deal with permutations and use random number generation and see what the qualities of a random number generator are that make it useful and reliable in the kinds of programs we're displaying. So all those things, in this case, are going to be provided by professionals within the STL standard. Great, great labor saving. Okay. Name 2 standard sorting algorithms. Hint, hint, I just mentioned them. What is their expected time? What is their worst case time? Take a second. Everybody has learned bubble sort, a very simple routine. Bubble sort is an n squared routine. We basically interchange elements where if the adjacent elements are out of order, we swap them, and we go through the whole sequence continuing to swap. And if we do that right, the typical bubble sort lets us get one element at least in order at the end of that list. And now we can bubble sort the remaining elements, which are n-1 after the first pass, and then n-2, and then n-3. And if we look at the order of that computation, it ends up being order n squared. On the other hand, quicksort, a sort invented by Tony Hoare, if it's working well, gets us an n log n sort. And just remember, n log n is very, very much more efficient than n squared, because let's say the log of 1,000 base 10 is just 2. So we would have something like 20,000 abstract operations as opposed to 1,000,000 abstract operations if we were to use bubble sort. So we get enormous savings by having a relatively efficient, or at least in the average case, efficient algorithm. Recall how quicksort works. Quicksort works by taking an element and then using the element and dividing all the elements, comparing it to, and hopefully they divide in 2 halves, and these are the less than elements. These are the greater than elements. This is the element that does the partition. So it's sometimes called a partition sort. And if it divides it roughly in half, it gets you your log n behavior. Hopefully, again, this is something you all have had in your background. That was expected when coming into this class. If not, you should look it up. Then after you've done a partition, you now repartition recursively each of these lists. And again, if they're roughly half the size of the previous list, you end up with this logarithmic behavior in dividing the lists. And each time you have to go through n elements, so you get the n log n behavior. Its worst case occurs if the partition element ends up, for example, partitioning in this very bad way. There's no elements below it. Let's say the partition element itself was a minimum. So all the remaining elements are above it. This is just 0. And now you partition this, and you have the same behavior. And this would only give you one element in the ordering each time, so you'd get, again, worst case, n squared. That's not going to happen in a probabilistic large situation, and there are special ways to do sampling that make it even less likely. So let us look at an example using STL, using a vector, using from the standard library IOStream, which of course we've used. The namespace std indicates that what we're dealing with is indeed a standard library. Again, if namespace was something else, it might be a local corporation library. You might have using namespace AT&T. If the AT&T people wanted to create their own versions. So here we have vector. Vector is a template. That's why it's a standard template library. Remember, template is all about generic programming. So STL is heavily invested in using templates. Indeed, 2 of the techniques that STL takes advantage of to get some of their efficiency and generality is the use of templates throughout and the use of inlining throughout. STL as a major design criteria is to try and get things that are nearly as efficient as they can be, even if they were hand-coded, especially hand-coded. Now here's some example code. This is a usual idiom. It's an idiom both for vectors, but also vectors can be treated like arrays. Now, this was used for initialization, and this is more a C-style idiom. Here, you're getting a C++ style idiom. And here you see that you have this notion of iterator, this generalization of pointer. We also sometimes call it a cursor. Understand that it's looking at a position. We have these special functions, Vm, so that Vn is always sort of the sentinel. So end end identifies where we are finished with our computation, where we're finished with our sequence. So it's like less than 100. 100 there is the sentinel. That means we can look up through 99. So there is no VI of 100 where there would not be a V of 100. V of 100. 100 is instead the sentinel. It's one past. So think of it as one past, one element past. And we dereference P, which gets us the contents of whatever that container is, and then we use it in whatever way we want. In this case, it's just for output. So again, here are two of the standard idioms. Both are in use in our coding style, but we want you to move on to this, and we'll hopefully explain why that has value. But STL relies a lot on this second idiom throughout its code. So the iterator logic is fundamental to the use of the standard template library. As I stated, P is conceptually a pointer, has two endpoints that define its range. Begin is actually the starting element and stores a value, but Vn doesn't store a value. Vn is a sentinel that says we're one past where we should be. So we're always testing Vn with a not equal logic. The P not equal to Vn is what's very typical. Now, lo and behold, C++ 11 allows for new features and allows us to change the idiom up in a more convenient way. So I'm going to start showing you that. And we're going to start having a combination of the older style. And I want you to keep in mind that in the next few years, we're going to see more and more compilers which are compatible with the new standard. And you should be able to start really taking advantage of it. Hopefully, currently in wide use, starting to be in wide use, is the current version of the GNU compiler. So I believe that's 4.8, and I believe that does implement most features of the new standard. So what are we seeing here? We're seeing how to collapse what is a fairly cumbersome declaration, a lot of typing. that's quite appropriate. I'm talking about keystrokes, but I'm also talking about having the right type. And it's frequently easy to make an error or forget something in this kind of complicated syntax. So now, auto has a new meaning. This is not its meaning in the original C language. The meaning in the original C language is deprecated. Deprecated is legal speak in programming language standards committees for no longer supported. So the meaning of auto has been completely changed. And auto now means infer type. So that means that the type must be inferable. I mean, auto isn't going to work if there isn't a way to understand the type. But if there's a way to understand the type, and there is, this is an expression. The compiler knows what type this expression is. It turns out it's vector int iterator. So at the point where the compiler knows what that type is, it just, instead of having to specify it, you just say auto. Much more convenient. Let the compiler do the work, and let the compiler do the work safely. In the very early days, it was what was called a storage specifier. Auto in the early days of C, that's worth remembering, was a storage specifier that said, put this automatically on the stack. And indeed, in most instances, nobody used it because it was redundant. You would just say int I rather than auto int I. So the old use was never in use. You could go back to Kernighan and Ritchie's, the original C programming language book, and try and find a use within the book of auto. And as far as I know, they didn't include auto in any real code throughout the original book that defined the language. So here's some more examples of how auto could be used. They're fairly straightforward. There are indeed way more complicated ones. And you can see how inference works. The first one, it's an alternative to saying int I. The second one's an alternative to saying double. The third one is an alternative, in this case, to say double. But let's look at the third one in more detail. So in general, whatever D is would have a type. And if it was a type that was fairly complicated to specify, then this avoids respecifying what might be a complicated type. It might be some kind of template, iterator type. Could be anything. So as long as we know the type, we can infer it. Now, we couldn't just say auto I, semicolon, right? No information to do the deduction. So that would lead to a syntax error. So again, auto should become something in your repertoire because it makes things simpler for you. So just so you can check, here's a very simple use of auto again, and you have to tell me what type is inferred for the variable C. The answer in that previous case was, of course, C is a char type, C-H-A-R. Now, new topic. When we get a container class from the standard template library, we also get a lot of additional functionality. Again, recall, we're replacing a primitive container array with a much more sophisticated object, an object that's going to give you more flexibility, and it's going to be much safer to use. Those are the two things you're going to buy with vector. Maybe you will take a very small amount of an efficiency hit, but in large measure you won't. And indeed, we're going to see in the new standard a fixed array type as a container, which also will, with greater efficiency, in some cases, also be useful to replace the simple array type in C. So here are some methods. V.size gets you the current size of container. That's important because containers can be resized on the go. One of the most useful functions of the container is, gee, I can, of course, when I declare the container, give it a size. That's frequently something that can be passed into the constructor. But I also have the ability, if I'm adding an element into the container will expand. So I don't run out of room as I would in an ordinary C array sense. I need a whole number of constructors. Again, remember in our little lecture on object orientation how valuable it is to have a large number of constructors. Constructors make it convenient to initialize a data type, and they make it convenient across a whole bunch of needs. So these are some of the critical constructors you're going to see, and you're largely going to see them for almost all kinds of sequence containers. So vector is just an example. I chose vector because vector it has 90% of your value in studying the container classes. The knee-jerk reaction when you need a container, a sequential container, is to pick vector. You almost should have a reason not to. You should have a reason why you need a list or a deke instead of a vector. So vector is going to be most of where you're going to get your value from the standard template library. So here's a constructor where you just build an empty container, and then as you add things to it, it's going to expand. Here's a container that's of a particular starting size. And here's a container in which there's not only a starting size, but a value for its initialization. So let's turn to an example we'll use throughout the segment for a simple vector. Vector is the most important container class. It's the go-to sequential container class. When we're using it, we have to get it from the standard library. So in effect, this is std vector. And we'll walk through this code and just see how effective it is. And again, largely people are replacing ordinary old-style C arrays with vector because you don't lose on efficiency and you gain in a lot of safety advantages and in flexibility. So here we're going to ask how big a vector you want. The vector itself will have its own constructor classes which enable it to go off to the heap and obtain all the storage necessary for a particular data type. So we're asking how many elements. You could say 10 or you could say 10,000. Of course, that will affect your running time and whether there's enough storage available on your system. If it got too big, the storage gets too big, you're going to see some kind of bad allocation exception. So we ask through standard in for how many. Here we type something in, like we might type in 1,000. And now, this is the data type. So all of this stuff is a template. All of this is a template class. And for each template that is used, you're going to get code. So if you need a vector for int, you're going to get different code for vector for double. So keep in mind that that can affect what might be called code bloat. So here you're going to get everything to do with int. That's going to be the underlying data type that will be stored in the vector container class. And now you will dynamically use the constructor of one argument to build a 1,000-element integer sequential data type. And now we're just going to deal with one very simple thing that this program does, and that is printing out that data. And you can imagine that there's going to be more code. So how are you going to print out the data? And again, with STL, the standard template library, the critical idiom to understand is that all its containers can be used with iterators. So your logic, if you're going to extend in an STL-like manner, you have to understand the iterator logic. Remember, iterators are a pointer type. In old C, there was only a very simple primitive pointer. Iterators extend that concept, but keep the idea of pointing at where things are. It's a pointer type. Now notice the definition, the declaration of, we're going to declare in this for statement a local variable. The local variable is IT. Its type is tied to what it's iterating over. So we have it taking out of the standard library a vector of ints. So if that had been float, it would have to be float there. If that had been char or string, it would have to be those types. And then scope resolution, and then the word iterator. And so all of this is a type. And this says this is the type associated with that so that the right thing can be pointed at. And then within these classes, there are location primitives, begin and end. Begin is where that vector starts. So again, think of it as a generalized memory primitive, which is saying what's the location of the start of this vector. And then end is a sentinel. It says, oh, you're at the end. You can think of it as some kind of generalized zero, but this is a test on the as a sentinel. So keep walking through. Remember, iterators can be auto-increment, and that just means get the next location. So this for loop is all about starting at the beginning, going to the end, and visiting each location once and only once, and then with each location, use it to initialize your vector. So you're initializing your vector from standard in. So if you were to run this code from your local computer, you would see on your screen how many. You would tell it how many, and then it would say the contents of, and then it would ask you to initialize, and then you'd have to write more code, a further iterator, to print what you filled the vector with onto standard out. So you could extend this so that you can show it processing your input and then printing out your output. That would be a nice extension, a nice exercise for you to see if you understand the whole iterator concept. Now, this iterator concept, we'll see in a later point, can be hidden. It's an underlying mechanism, but it can be hidden by either using things like the for range or by using ways to hide the complexity of the declaration with the new meaning of the keyword auto. So in our vector program, in the last segment, you saw that we used this very complicated declaration for the variable it, the local iterator variable. And that's where, again, auto is so important, as was mentioned earlier. Auto is not at all what it started out to be in old C. In old C, it was a storage classification. In C++11, auto is a type inference mechanism. So here, the compiler looks and says, it has to be of an appropriate type for data begin. And if you remember, data begin is where the beginning of that vector, which was storing a bunch, for storing a bunch of integers is. So it would infer that whole standard vector int : iterator logic. And you don't have to write it. And it's quite transparent as to what is going on. And you're back to just using it, a sentinel, and then auto-incrementing the pointer type so that you can march through for how many elements and fill your vector. So here's all the STL value. We've used the iterator idiom. The iterator idiom for the vector makes sure we go correctly across the whole container. We don't have any possibility of making indexing errors, right? That's a value. Anybody that's programmed in C knows that we get seg faults or some other fancy message at runtime if somehow we index out of the range of the array. And this is a way to avoid that. So this is one of the very strong values of moving over to the iterator idiom and the range begin and end. And again, I say you'll see that over and over in the STL library. And as part of the idiom, we see the auto increment of the pointer throughout, and then we see the dereferencing and processing of the item. And you can just as well imagine that instead of this process, this could be processing start P in a very complicated way, taking each element in time and doing something with it, not just this rather rudimentary printing it. You could even call a whole function on it to do some fancy stuff with it. Okay, quiz, avoiding bounds errors. For int I equals 0, I less than or equal to upper bound, plus of I, sum is sum plus data of I. Can you find something wrong? Think C, think what's wrong if this is the conventional C idiom. Upper bound is normally not tested with that. It's normally tested with this. So this is going to get you one past where you look, and going one past is going to result in some kind of runtime error. And again, conventionally, this is thought of as an off by one error. And that's what we're trying to get you to avoid. So again, to demonstrate how powerful STL is, we're going to use the STL iterator standard library. We're going to use a file stream library, and we're going to do something where we get data from a local standard file. So there you can be processing arbitrary amounts of data. It's just some experimenter has given you the weights of elephant seals. That's what we do out here at UCSC. We are right next to the breeding ground of the elephant seals, and you decide you want to know what the average weight of elephant seals are, and you have a bunch of data which is integer data. It turns out actually elephant seals can be up to 6,000 or 7,000 pounds. Especially the males get to be quite a bit bigger than the females. So if you're a biologist and you are tracking a lot of this, this is very useful. And this is very common, again, in all sorts of data science. You have some big files, you're processing them, and you're trying to find key important statistics out of those files. How do we do this? Well, the first thing we do, which is, again, very simple because of STL, is we have an IF stream, a data file, and the local name, the local file name. So that's going to be called data.txt. We have an iterator for the type of data that will be stored there, which is going to be an int. And we have two pointers, a start pointer and an end pointer. And the start pointer is going to be initialized to the beginning of the file. So the file's name locally is data.txt. Start points at wherever we go to open that file, and end will end up being the sentinel for the end of that file. Now here's what's fascinating about STL. Here's a constructor type, and it has two arguments. One of the arguments is they're both iterators. They're iterators to something else, namely an iStream. One is the start of the iStream, and one is the end of the iStream. So this is going to generate fancy code that you don't have to use. That's why it's so powerful. It itself is going to do an initialization out of that text file of all the integers found in that text file, and it's arbitrary, so we don't know in advance how many we need. And because vector itself is an expandable sequential container, the system will build it, and that data is all going to end up sitting here in the internal variable data. Now we can process the data, and notice let's say in this case we want an average. So we're going to sum the data, initialize the sum to 0. We're going to use our use of auto to get the right type for the iterator. That's the start, which had been initialized to the beginning of the file. And we're going to go to the end, and we're going to do the sum. And then we can print out the sum, and then we can find the average of the sum. Of course, I use 1.0, so it ends up in the double domain, and you should all be aware that we could have just as well done that with a static cast. Okay, here's a new little topic, and as I said earlier, we're going to start injecting new features from C++11, which you should start adopting into your own practice because they're going to make your programming chores easier. There's a claim in the C++11 standard that the new version of the language is easier to use than the old version of the language. Now, on the surface, that may seem a little absurd. Why do I mean it may seem a little absurd? Well, the new standard adds about 60% more material to the old standard. The old standard took about 800 pages to describe. The new standard takes about 1,300 pages to describe. Normally, when you have something that's another 500 pages long to describe, you don't call it simpler. You call it more complicated. And indeed, there are things in the new language that are fairly complicated. But there are many things in the new language, such as you already saw with auto, that gives you, if you adopt them, a much easier way to write code, a much more natural, more intuitive way. And here's another one of them. And that is the range-based for statement. So that's our little tip of the day, our new C++ 11 tip of the day, which is this new for statement. How does this new for statement work? We have a declaration in the for statement. Then we have the explicit character colon. Then we have some expression. And finally, we execute a statement. And of course, the statement can be a brace and close block. So it can be, it's a single statement, but of course you can make it as complicated as you want through, as usual, using a brace and close block. Here's a simple example of its use. For double D, recognize that double D is obviously a declaration. So we've identified a variable D that's going to be local to this range for statement. And then we have an expression. We're calling the expression, in this case, data. For example, data could be an array of doubles. And it could be an array of doubles which was declared, let's presume that it was declared as double data upper bound. So it's some, if upper bound's 100, we have 100 pieces of data. The data sitting in each element is a double. And you can see now what that for statement is supposed to do. It's supposed to add up all the elements in that array. And the way it adds them up is D, and D in turn marches over data. And you could think of it as D is being assigned data of I++ in turn, where somehow I was some index or cursor that was marching through that. So typically, data is going to be an aggregate. D is going to end up being an individual value taken from that aggregate, and you see nothing about a range. So this is even simpler than begin-end. Begin-end is implicit. Begin-end is implicit. So this further simplifies the STL idiom of saying for an iterator, auto of P equal data begin, and P not equal to data of end, and then you would do P++. So instead of that whole thing, you have a much simpler statement, and you avoid even mentioning the iteration. What can be used in the expression where you have a range for? It can be an array, it can be an ordinary sequence container, it can be a string. Think about a string. A string is a series of character elements. So it's a specialized container. And conceptually, you expect them to have begin-end members. So where you have sequence containers with begin-end members, or strings or ordinary arrays, all of those are subject to the range for. Let's look at another example. It should be lowercase. So here, this is again a declaration. The declaration is a reference declaration. Notice also that I've used auto to infer type, so I'm using now several of the new ideas from C++ 11. So it would have been just as suitable to have said double ampersand. In effect, it's just a way of getting the compiler to see that that should have been double. But again, you could say this is going to work regardless of type. And now, rather than do summing, I'm mutating this value. And because I'm mutating it, that's why I needed the reference declaration. So again, this is a very standard idiom now with the for range, and it's a standard idiom when the effort, when you're going to, in your processing, affect the elements that are stored in the container. Okay, now let's turn to another example and study yet another example. Again, all of us out there have pretty much, or at least in most instances, students, myself, we learn from experience, from practice, from seeing example code. And once we see an example rather than some abstract document, we know from that idiom, that example, typically if it's archetypal, it then lets us understand the technique and absorb that technique. So in this example, we're going to read in a series of words from a file, and we're going to read them into a vector, and then we're going to sort them. So you can imagine that you're a humanities professor and you want to verify that a certain play was written by Shakespeare, or maybe there was some controversy. And some of the methods you might use is to see the usage of words, how often they get used. Shakespeare, where every author seems to have patterns and usage patterns, and there are statistics you can again apply to their text and use those statistics to verify that it's likely that it was Shakespeare. These techniques also get used, for example, in the Bible to figure out whether there are multiple authors and where there seems to be stylistically changes from parts of the text to other parts of the text. And again, we're going to demonstrate how powerful STL is. So this, if we were to try to write this in old style C, or even in the original pre-STL C++, we would have had to write many more lines of code. All of that code would be subject to difficulty. It would make for pretty low-level routines that could have lots of runtime errors. But here we have the ability to just reuse code. Reuse of code is a silver bullet that allows us to quickly and efficiently write large pieces of code. Again, we need to know what kinds of STL libraries we need: IOStream, Iterator, FStream. FStream, again, is for the files. And now we're going to also choose to use algorithm. So algorithm is where, in our case, there's going to be a sorting routine. And again, this would have required a bunch of lines of code. The sorting routine, as you'll see later on, we'll talk a little more about it, is based on Hoare's quicksort algorithm. And again, the container class, our most useful container class, is our vector class. So we open word.txt, so we can imagine Shakespeare, some play, Hamlet's play is sitting in a big document. You can find this stuff all over the internet. You get some big file and it has words in it. And we need an iStream iterator that's going to migrate over and visit that file. And we're going to use what we used before, which is two pointer types, a start and an end. The start will point to the initial place in the open text file, the word.txt. So word.txt is a local file, contains the information we want to process, and that information is going to be a series of strings. Words are just strings. And again, we can use this kind of constructor to basically go off to these pointers, which are now pointing at a file that's to be read, and will initialize this vector. And critical to that initialized vector is the actual reading of that file uses white space to distinguish individual strings. So we don't have to write, for example, some elementary routine that would crunch characters looking for white space to separate out the individual strings. And we also get the ability, because string is a dynamic type, to represent small words like a and the from large words like polysyllabic. So arbitrary strings, which in this case are hoped to be words, can be dynamic. And here we go and start processing those words. So words are read in, and now we're going to use our for range statement. Again, a very powerful feature that simplifies a lot of coding in modern C++ 11. So what does the for range do? It looks at, in general, some kind of container, and visits everything in turn, so we can't get a range error, and decides what it needs in visiting the individual items. So auto is going to pick out an individual string. So auto is going to use the compiler to infer what the appropriate type is, and then all we want to do, for example, is print out and see what's actually in that file. So this stuff is just going to print out that file. So if the file said the quick brown fox, that's what we would see on the screen. And each of those words would be separated by a tab character. And here we invoke the sort, standard library sort out of algorithm. Sort's a two-argument thing. The two arguments are iterators. So if you look at the logic of STL, anytime you see an STL algorithm, it's generally going to work with iterators, because it's the most powerful logic. That's how all of this was designed to be very integrative. And again, we use our for range, and this time after the sort, we're going to see something different. So if it was just the quick brown, these would be reoriented. I think we actually would see the brown quick. You can check me on this. And the reason we'd see it in that order is the, which is the first letter, has lower ASCII value than the uppercase the has lower ASCII value than the lowercase B's and Q's. So the for range idiom simplifies how we visit a container class. The sort is STL, so it's an extremely efficient algorithm we don't have to rewrite. And once it's sorted, we can do interesting things like frequency counts. So again, try it. See if you can do some other things. Another thing you might do is maybe it's inappropriate to distinguish between capitalized and uncapitalized letters, lower and uppercase. So maybe you would want to, before you want to maybe process the file so that everything is lowercase. So that would be an exercise. Change everything to lowercase first, then process the file. And that's all. This is very powerful. You can see that we're getting a lot done in manipulating a text file with rather little effort. If you know STL, it just brings a lot of firepower and lets you write very concise but very understandable and remarkably correct code. Why? Because all of these subpieces have been thoroughly checked out. So conventionally, that algorithm, quicksort by Hoare, is called with an iterator range. And again, I told you we're going to see this a lot. We're going to see an iterator range. This is going to be a specific iterator, a starting iterator and an ending iterator. So we could have sorted something that was a shorter range. We didn't have to pick the whole file of vectors. We could do something else, but this would be very typical, the starting iterator and the ending iterator. The other thing we have to know about this is this algorithm requires random access. So these iterator values must be random access for this to work. If it wasn't random access, this would fail. And notice in my comments on the slide, see if you could try to write your own code, if you're up for that. Write your own quicksort and compare it timing-wise and see if you could do better. This is remarkably efficient code. And it's done by professionals in this library. And they know the libraries wouldn't be used if they were easily improved on. The professional use requires that use be highly efficient. Next major topic is going to, again, be architectural. We're going to describe in more detail what the iterator hierarchy is, iterator categories. You can see in this slide that an iterator and the iterator characteristics are you have methods like begin and end. In this case, you're seeing this is a list. Your typical list allows for bidirection, and that there's a previous pointer and a next pointer. So if you are at a particular position in a list, you could do position plus plus and move over, or you could do position minus minus and move backwards. And again, this specifies the range. This is the start of the range. This is the end sentinel of the range. So again, very important to grasp that diagram. This is in terms of a list, but it would be similar in terms of a vector or similar in terms of a double-ended queue. There are basically in STL 5 major categories, and the categories are strongest to weakest, if you want to think of that. So this is the strongest, random access. This is the weakest, what we call input. Let's look at the weakest first. The weakest allows you to read and only look at information once. Read in a single pass. What could that mean? Think of an input file. Input files are used for reading, and if you read through them, you get to the end of the file, and then you're done. The cursor goes away. The second weakest, which is very similar, is for output. In output, you can write to the file, so the file can be modified, but again is single pass. The third weakest, sort of intermediary, is forward. In a forward iterator, you can read and write, so you can do both operations, so you have more operations. But you can also act on it. The file doesn't disappear on you. It can be used multi-pass. So the construct you're operating on, like a vector or list, is staying there, unlike thinking of a file read that disappears on you. So it can be multi-pass, but it's one-directional. That's what I mean by 1D. I don't mean one-dimensional. I mean one direction. Bidirectional, which we saw in that little diagram, is again more sophisticated. Multi-pass is allowed, and you can go to a previous element as well as the next element. And finally, random access is strongest because you can go anywhere. And you can go anywhere in what is known in analysis of algorithms in order 1. You can do an address computation anywhere into what is indexable. So you can think of that as something where it's an indexable container. The canonical one being a vector, or in the C language, an array. Now, when we go to design algorithms, we always keep in mind what iterator category we want to use. And we always want to choose, and we'll try to understand it, but let me say this first. I'm going to repeat it. If you study this in detail, if you go to study, you'll have to study the library on your own. The library is enormous, but it's very important conceptually to keep in mind that when you design an algorithm, you design the most efficient version of the algorithm that allows you to use the weakest iterator category. So, restating that, in STL, the design principle is to use the weakest iterator that accommodates the most efficient algorithm. We've seen quicksort. Quicksort requires random access. Without random access, you can't do quicksort. As a consequence, it cannot be used on a non-random access container such as a list. Indeed, list, for example, has a special sort routine. It's not that you can't sort a list. You could do it in one of two ways. You could transfer the contents of the list to a vector, for example. That would be one way, and then call the ordinary sort on the vector, and then reconstitute the list. So there you're destroying one list, rebuilding the list, and using vector. But it may be simpler to just call the specialized sort on a vector, which will not be as efficient. Can't be. It won't be as efficient. It doesn't have random access available to it in moving stuff around. Now, why random access? Well, remember, we want an order n log n computation for quicksort. And if you call, quicksort is also called partition exchange. We have that partition element. We identify two elements that belong on the other side of the partition, and we swap them. For the swap to be efficient, this is sitting in I and this is sitting in J, and we need to deal with that in random access mode. If we deal with that as a list, we can do that, but then that becomes an order n computation. So each swap would be order n. In random access, each swap is order 1, and that gives quicksort its n log n behavior. Let's go through the iterator hierarchy a little more carefully. There's the input iterator. The input iterator must allow the elements to be searched in a forward direction one by one, requires the operator plus plus to be defined, advance the iterator, and also requires that you will be allowed to dereference the object that the pointer is pointing at, that the iterator is pointing at. When you have an input iterator, canonically it's for accessing elements sequentially in an input stream. and that requires a rather minimal set of operations. It's similar to using what's called the find of an element in a collection search sequentially. Also, input iterators can have equality and inequality defined. So if you think of, because it's in the standard algorithms library, find, and we have some basic sequential, let's say we're looking for the element 6, we could start at the begin, and then move along until we hit find. And that's going to be perfectly efficient. We don't need any random access. We don't know where something is, so we're going to have to look through the set of items. But we only need to look through them once. If we go through them more than once, what's the point? That would be extra work. So looking and trying to find something in a list. So think about a pile of note cards where you're keeping addresses for your friends and they're unordered. The typical algorithm would be exactly this. Find. I would go to my little note file and keep sequentially reading through them and looking for a particular element. I would look for, where is Laura Pohl's current address? And I just would continue to look that up, and find would do it. So find can rely on the weakest possible iterator, the input iterator. And that's how it would be defined in STL. Here's an example using an input iterator. And it's using the numeric library. So again, there's algorithm, there's numeric. These are the different kinds of methods that get produced generically through the use of STL. That's the three-legged stool again. And accumulate will be sitting in the numeric library. And accumulate, in this case, is using an input iterator that's at the start of this IF stream. So we have a file. File is sitting somewhere. It's a data file whose name is data in the local directory, which has some series of numbers, which are integers. And we want to add all those numbers up. So let's say there were the 6 numbers, 6, 4, minus 3, and 19. The file had 4 elements. We have an iStream iterator, which points at the beginning of the file. And we have something for the end of stream, the end of file, in effect. So this is the equivalent of begin and end. And then we accumulate starting with the value 0. So this can be an arbitrary value. For example, if we have a whole bunch of files to look up and add up, we may want the last value to be the starting value for the next accumulate. Accumulate is just going to add 6 plus 4 minus 3, that's 7, plus 19. So we're going to end up with, in that case, printing out 26. All very compact, all done without worrying about indexing. Highly useful because operations like this occur all the time, and accumulate, as we see, only needs to run through it once in one direction, just like find, and so it can make use of the weakest iterator and still be highly efficient. So if you were to look at the signature for accumulate in the library, and you'll see, look it up in a standard or go look it up using the Wikipedia, you'll see that its signature involves, they'll probably say something like input iterator there, and then some kind of value. Again, because it's all generic, right? These are input iterators of a general type. So this is some type in general, so it can be an arbitrary value. And usually by default, that starts at whatever is the natural zero. For that type. But it could be some other value that you're starting. That's accumulate. Very useful numeric routine. People are doing accumulate over and over again, so what's the point of writing your own version? No point to it at all. Okay, take a little quiz, see what would happen. What is the output from this little code segment? So we saw that the starting value was 5. It wasn't 0. And so it was 5 plus 1 plus 2 plus 3 plus 4, so 5 plus 10, so that's 15. So the answer is 15. Okay, let's do something a little more complicated and something in which we've used in our homework assignments. So in the assignments, I've talked about generating a random graph, and the random graph has what's called a density, and the density is, roughly speaking, how many edges per node are available. So if I have a density of 0.5, density will be between 0 and 1. 1 would mean that we have what's called the complete graph. Every possible edge is included in the graph. 0 would mean we would have a completely disconnected graph. We would have nodes but no edges. Half would mean that if I had a graph which had 100 nodes, on average, there would be 50 edges per node. That would be a reasonably dense graph for something that large. And it's very useful to use random generation techniques, because when you start applying graph algorithms to hard problems, it's hard to get real-world data. So at University of California, Santa Cruz, my colleagues have a huge project in designing the internet in the sense of making internet connections reliable and optimal. And the internet has hundreds of millions of nodes, or maybe even billions of nodes at this point. And you can send packets reliably all through the internet. And there has to be some design criteria. How is an organization going to build its own local internet? Or in the case of the military, you might have to have a dynamic net, because the connections are going to involve things in which there are catastrophic failures. Let's say your tank is shot up, and it was one of your internet points. Because nowadays, the battlefield is electronic. So there's just tons of research in how to create both static and dynamic networks that make the internet efficient and highly reliable and inexpensive. And those characteristics are hard to come by. The data is hard to come by, and so you try to simulate it, and frequently you simulate it with the right set of random parameters. So here's something very basic, and it'll also show a small amount of use of some of the techniques we've already talked about. We're going to borrow stuff from the standard library. In C++ 11, we might want to replace rand. Rand is very basic. And C++ 11, one of the places where there's significant improvement is a new set of standard random functions that get you all sorts of interesting characteristics. So I hope you go and examine that. And maybe at a later time we'll talk a little bit about that. And this is a simple thing that provides a probability, and you should see why it provides a probability. First off, rand is in the int domain. Rand max is the largest possible value that can be generated. So this is going to be, well, this is unsigned. And this is the largest possible value. So this is always going to be less than 1. But if they both were in an int domain, these would always lead to zeros. We don't want that. So we force that value into the double domain. We cast it into the double domain, and then this becomes a mixed computation, and then indeed we get a fractional value, which would be between 0 and 1. So that's the probability we want. As a probability, we want something between 0 and 1. Here's the density. The density we're going to get from the user, be inputted. We want some value inputted, such as 0.5. We also want a size. So let's say this was the default. If we asked for a size, and this could have just as well been 0. So we're getting a new size. Let's say we want 100. So we'd have to type that in. And now we're going to create a graph, and we're going to use basically a Boole matrix. So the graph is going to have, in effect, a 0 if there's no edge, I and j no edge, 0 or actually false, and if there's an edge, there's going to be a 1, I and j having an edge, true. We're also going to allow colors. So that makes the problem a little more interesting. So edges are going to be able to have colors. Think about your navigation computer on your car. My navigation computer allows the streets to be freeways or local streets. And it allows me in computing a route to say avoid freeways. How does it know to avoid freeways? Well, freeways are blue and ordinary streets are green. And so it's going to look at the subgraph, namely the subgraph of edges which are only green if it wants to avoid freeways. Recall that anytime we use a random number generator, we want to do something about initializing a seed to avoid routinely getting always the same behavior out of the program. So this is a standard practice to seed the random number generator using something from the real world, which would start at a different value. Here we construct the different components. We're basically constructing 3 matrices. So this is a cost matrix, like how if I and j have cost 5, you can think of that as 5 miles. Here's a color. Maybe I and j will have the color red. and this is whether I and j exist. So we're building the data structure to let us represent the graph, and the graph representation in this case is a matrix representation, not the edgeless representation. So for those of you who want, you can try to do the same thing, but do it with an edge list. Here's where we create an edge. Think of this as flipping a coin. The coin is weighted to give me a probability between 0 and 1, and then test whether the probability is below the density. So if density was 1, all these probabilities would be less than 1. But if density was down near 0, then the probabilities would largely be greater than the density, and so it would be a relatively sparse graph. So we're testing to see, and the fact that this is symmetric means that the edges are undirected. So we're generating undirected edges of a particular density. And then we're testing if the edge exists. So this is Boolean. Then we do a color and a cost. We're going to have 3 colors, so we use the modulo operator and we'll get values 0, 1, or 2, and those will be the equivalent of the colors. And we'll have a cost. In this case, it'll be probability 30, so times 30. So the values of the costs, if they're integer values, will be between 0 and 29, I think. I don't think we can get to 30. And then I'm going to print this to an output file. In the output file, you should try this yourself. Take the code from the site, and you'll see that you'll get a code that has these characteristics, that will have certain costs. For each edge, we'll check again to see that the edge is true. And if the edge is true in those files, we'll list the cost and a color, and we'll have them as output. Okay. Okay, we're at the end of part A of this course. I hope you've had a good time and got to really make use of C++ and enhance your programming skills. You've also learned how to do things with graphs and graph algorithms. And then part B is going to be the next class. I hope to see many of you in part B. And there will be more advanced parts of C++ in part B. And we'll try to see yet some newer C++ 11 features as well. And the chief work of part B is to build a game. And to build a game, the game is a well-known game that's hex. And the reason part A was so important to this is not only that you learn how to program effectively in C++, but hex is a game that is well represented by graph theory. So all of this graph theory should go into understanding and building this major project.